In this context, it is important to remember that our legacy is not just about achievements, but also about mistakes from which we can learn. As we go to sleep, it is worth contemplating the endless possibilities that the depths of time and space hold, and how we can use this knowledge to create a more sustainable future. In the waters off the coast of Peru, researchers have discovered underwater ruins that may be the remnants of an unknown civilization, further highlighting how little we know about our history. Earth has existed for billions of years, and its history is a true epic of changes and transformations that have occurred on its surface and within its depths. Over this time, our planet has experienced incredible events, from the formation of continents and oceans to the emergence of life in various forms. Over billions of years, Earth has gone through numerous geological epochs and catastrophes, such as mass extinctions and volcanic eruptions. These natural cataclysms have shaped the landscape, creating mountain ranges, valleys, and plains that we see today. This entire process can be compared to a giant mosaic canvas, where each element is the result of countless interactions and changes. For example, the movement of tectonic plates has formed the highest mountains on the planet, such as the Himalayas, which continue to grow even today. Life on Earth, however, emerged much later than the planet itself. The first organisms that appeared on Earth were single-celled and lived in oceans that covered a large part of the planet's surface. These simplest forms of life became the foundation for subsequent biological evolutions. An example of this is the oxygen catastrophe, when cyanobacteria began to produce oxygen during photosynthesis, which changed the composition of the atmosphere and paved the way for the emergence of multicellular organisms. Over millions of years, life has evolved and new ecosystems have emerged on the planet, where plants and animals adapted to various conditions. The appearance of the first vertebrates, such as fish, was a significant stage in this evolution. Over time, some of these species began to move onto land, leading to the emergence of amphibians and ultimately reptiles and mammals. Humanity, unlike this long and complex history, has existed for only a few 100,000 years. We are merely a brief interlude in the infinite history of Earth. However, our impact on the planet has become noticeable in just a few decades. As a species, we are capable of altering our environment at such a speed and scale that it is frightening. Global warming, deforestation, and ocean pollution all are consequences of human activity occurring against the backdrop of Earth's multi-billion-year history. Humanity, although it appeared on this planet relatively recently, has already left its mark, which may be irreversible. Such a contrast between the short existence of humans and the long-term evolution of Earth makes us think about our place in this world. For example, in recent decades, there has been a sharp decline in the number of animal and plant species, which is causing concern among scientists as it could lead to a new mass extinction. Astronomers and geologists also emphasize that Earth will continue to experience many changes that are independent of our desires. The shifting of poles, earthquakes, and volcanic eruptions will continue to shape our planet. Humanity has only been a brief part of this great history, and perhaps we will not be able to cope with the consequences of our actions. Scientific research shows that in the next few decades, climate change could become catastrophic if no serious measures are taken. Research conducted by scientists from different countries shows that there are already signs that ecosystems cannot cope with rapidly changing conditions. Each of these changes is a new page in the history of Earth, which continues despite our existence. Humanity can study, work, and try to change the course of events. But in the end, Earth will continue to exist in its infinite cycle of changes. We can only observe how the history that began billions of years ago continues. There are many signs of how ancient civilizations interacted with their environment, and this interaction has always been complex and multifaceted. For example, the Sumerians, who lived in Mesopotamia, used irrigation for agriculture, demonstrating their understanding of natural cycles. They left behind cuneiform tablets, on which they recorded not only their agricultural activities, but also their views of the world. Similarly, the ancient Egyptians built their pyramids, taking into account geographical features that preserved their legacy for thousands of years. Each of these examples underscores how humanity, throughout its short history, has tried to understand and adapt to the long history of Earth itself. The age of Earth is approximately 4.5 billion years. This colossal period of time allows us to ponder how slowly the surface of the young planet cooled, which in its early existence was hot and unstable. The appearance of the first oceans was a pivotal moment in Earth's history. Around 4 billion years ago, as the crust cooled, water vapor condensed, forming oceans that became the foundation for the emergence of life. This event did not occur instantaneously. The process of forming water bodies took hundreds of millions of years, during which time Earth's atmosphere gradually filled with gases such as water vapor, carbon dioxide, and ammonia. Initially, the atmosphere was toxic to living organisms, but over time, thanks to photosynthesis performed by ancient cyanobacteria, it changed, becoming enriched with oxygen. This process, which began around 2.5 billion years ago, laid the foundation for the emergence of complex life forms. It is important to note that throughout this period, Earth experienced numerous catastrophes, such as meteorite bombardments, volcanic eruptions, and temperature changes, which played a crucial role in the planet's evolution. For example, around 600 million years ago, there was a mass extinction event that resulted in the disappearance of around 95% of all species. Nevertheless, it was precisely this colossal time span and the diverse conditions on Earth that allowed life to adapt and develop, ultimately leading to the emergence of intelligent beings. Humanity, as we know, appeared only around 200,000 years ago, which is just a small fraction of the time that has passed since the formation of Earth. In this context, we can see how insignificant our experience is compared to the age of the planet. Earth has undergone numerous changes, and each of them created new conditions for life, ultimately leading to the emergence of humans. Humanity, with its ambitions and aspirations, exists only for a fleeting moment in the scale of cosmic time. But this moment became possible thanks to billion years of evolution. 4.5 billion years. It is not just a number, it is a period during which entire worlds were born and disappeared. The geological timescale is an incredible tool that allows us to visualize and comprehend the magnitude of Earth's history. If we were to compress the history of our planet into a 24-hour day, billions of years of evolution and change would fit into this daily cycle. Earth formed approximately 4.5 billion years ago. If we consider this period as a single day, the planet's formation would have occurred around midnight. The first simple organisms that appeared in Earth's waters did so around 3.5 billion years ago, which would correspond to around 3 in the morning. Over the following billions of years, evolution proceeded slowly and gradually. Multicellular organisms began to develop around 800 million years ago, which would be around 8 in the evening. The appearance of the first vertebrates, such as fish, occurred around 500 million years ago. That's just around 10 in the evening. Around 300 million years ago, at 9 in the evening, the first amphibians appeared on Earth. The dinosaur era began around 200 million years ago, which would be around 11 in the evening. During this period, around 66 million years ago, a mass extinction event occurred, marking the end of the dinosaur era. This happened just a few minutes before midnight. The first mammals appeared around 160 million years ago, and the first primates around 50 million years ago. Humanity, as we know it, appeared only around 200,000 years ago, which would correspond to the very last seconds before midnight. This means that all the achievements and events we consider significant have occurred in just a few moments in the context of the entire geological history. We, humanity, are entering this world at the very edge, where everything before us has passed through billions of years of evolution, formation, and destruction. In this context, our lives and achievements seem insignificant, like sparks against the vast backdrop of cosmic eternity. Humanity, with its cultures, wars, and discoveries, occupies only a tiny fraction of time, while Earth continues to rotate and billions of years lie ahead, waiting for their turn. Research shows that even the oldest civilizations, such as the Sumerians, appeared only around 6,000 years ago, which would be the last minute before midnight. The question of the existence of life beyond Earth has always intrigued humanity, and this interest does not wane even in the face of constant progress in the fields of astronomy and astrophysics. The Fermi paradox, which arises in the context of discussions about extraterrestrial civilizations, raises a significant question. If there are so many planets capable of supporting life in the universe, why do we not see any signs of intelligent life? With more than 100 billion galaxies containing trillions of stars and even more planets, the probability that life exists somewhere in the universe seems high. Considering only our own galaxy, the Milky Way, astronomers estimate that there may be around 100 billion stars, and according to modern calculations, more than 20 billion of them may have planets in the habitable zone, where conditions are similar to those on Earth. However, despite all these numbers, we have not yet found any convincing evidence of the existence of other intelligent beings. This leads to reflections on how long civilizations can exist and why they disappear before reaching a level where they can interact with other worlds. For example, we know that human civilization has existed for only about 6,000 years, and even in this short period, we have faced threats that could have destroyed us, such as nuclear wars, climate change, and other catastrophes. If we assume that civilizations arise and disappear at the same rate as ours, this could explain the lack of evidence of other intelligent forms of life. Additionally, even if other civilizations exist, they may not reach the level of technological development necessary for interstellar travel or communication with other worlds. Moreover, the time intervals between the emergence of civilizations could be so great that they simply do not intersect. Scientific models show that even if a civilization reaches high technologies, it can quickly self-destruct, as has already happened with many species on Earth. In this context, it is worth considering how often we see such examples in the history of the planet. Over the past 500 million years on Earth, there have been 5 mass extinctions, each of which destroyed more than half of all species. The last one, which occurred approximately 65 million years ago, led to the extinction of dinosaurs and paved the way for the emergence of mammals. Thus, every time a civilization reaches high technologies, it also faces threats that could lead to its destruction. It is interesting to note that even if other intelligent life existed, it might choose not to reveal itself to avoid interference from less developed civilizations, which is also one of the possible explanations for the Fermi paradox. In such a case, we could be witnessing the existence of many civilizations that have decided to remain unnoticed, preserving their independence and safety. Scientific research shows that even on Earth, there are many forms of life that lead a hidden lifestyle, and this can serve as an analogy for extraterrestrial civilizations. Taking all these aspects into account, the Fermi paradox continues to be one of the most intriguing mysteries that the cosmos presents to us, and at present, we do not possess sufficient evidence to provide a definitive answer to this question. Scientists continue to search for signs of life, and perhaps in the future, we will find solutions to this puzzle. In this context, it is worth noting that in the 21st century, active searches for exoplanets began, and over the past 10 years, astronomers have discovered more than 4,000 planets outside our solar system, opening new horizons for research. The Silurian hypothesis proposed by scientists Gavin Schmidt and Adam Frank is a bold concept that challenges traditional views on the development of civilizations on Earth. Schmidt and Frank, working in the fields of astrophysics and ecology, suggested that a technological civilization could have existed on our planet long before the appearance of Homo sapiens, approximately during the Silurian geological period, which lasted from 430 to 400 million years ago. At that time, Earth was inhabited by various forms of life, including early fish, trilobites, and land plants. But the existence of a complex technological civilization, according to the authors, could have been possible in conditions where the atmosphere and climate were more stable than they are today. Schmidt and Frank explored various scenarios in which technologies could have developed, including the use of resources such as carbon and silicon, thereby questioning our understanding of what makes a civilization a civilization. They analysed data on climate changes and the biosphere to determine which conditions could have fostered the development of intelligence and technologies. In this context, they turned to the concept of planetary ecology, which studies the interaction between the biosphere and the geosphere, potentially providing insights into how life could have adapted and evolved in various conditions. The research also addresses questions about how such civilizations could have disappeared, leaving behind only faint traces that are difficult to detect in sedimentary rocks. Schmidt and Frank use analogies with modern ecosystems to illustrate how technological societies can be vulnerable to climate and ecological changes, leading to their extinction. They emphasize that in conditions of global changes, such as climate catastrophes, even highly developed civilizations may find it difficult to survive. In their work, they also refer to the existence of other planets where similar scenarios could have developed and consider the possibility that on other exoplanets there may have been or may exist civilizations similar to the hypothetical Silurian civilization, which did not leave clear traces in history. This idea of the existence of previous civilizations on Earth raises many questions related to the understanding of human history and our place in the cosmos. The research by Schmidt and Frank opens new horizons for discussion and study, highlighting that our understanding of the development of life on Earth may be much more complex than we previously thought. The scientific work published in the journal Scientific American in 2014 attracted the attention of researchers and the general public, contributing to the start of active discussions about the possibilities of the existence of other civilizations in the past. An important aspect of their hypothesis is that it encourages us to rethink historical chronology and cultural achievements of humanity, as well as to consider how we can use the lessons of the past to address contemporary environmental and social problems. Given that the Silurian period was a significant milestone in the evolution of life on Earth, the hypothesis of the existence of a technological civilization during this time becomes not only an interesting scientific question, but also a relevant challenge to our perception of history and the future of humanity. Geological processes represent complex interactions between various components of the Earth that shape landscapes and change them over millions of years. These processes can lead to the complete destruction of traces of ancient civilizations, leaving only vague hints of their existence. Ancient cities, temples, and other structures built from stone, wood, and other materials are subject to the influence of multiple factors such as erosion, precipitation, and temperature changes. For instance, if we consider the impact of precipitation, it can wash away the soil in which the remains of ancient buildings are found, eventually leading to the complete disappearance of archaeological layers. In this context, it is important to note that the degree of geological processes' impact can vary depending on the region. In some areas, such as mountainous regions, high levels of precipitation can accelerate the processes of destruction, while in drier regions, traces of civilizations may persist longer. It is also crucial to consider that many ancient cultures used local materials for construction, which over time are subject to natural changes, leading to their destruction. For example, limestone, often used in construction, can dissolve under the influence of acidic rain, resulting in the loss of structural elements of buildings. Ancient technologies and methods used for creating architectural objects also do not protect them from destruction. Many constructions were not designed for long-term use in conditions where geological processes are actively at work. This can result in even the most magnificent monuments, erected thousands of years ago, becoming victims of time and nature. Ultimately, for researchers and archaeologists, it becomes increasingly challenging to find evidence of the existence of these civilizations, as the traces of their cultural heritage can be hidden under layers of earth and precipitation that accumulate over centuries. Using modern technologies such as ground-penetrating radar and satellite imagery, scientists attempt to identify places where ancient settlements might have been located. But even these methods do not always provide accurate results, as geological processes can distort their orientation and structure. Preserving archaeological finds requires not only meticulous study, but also an understanding of the dynamics of how geological factors interact. For example, in some regions, the uplift or subsidence of the Earth's crust can affect the location of monuments and their preservation. Numerous studies show that even small changes in the surrounding environment can have catastrophic consequences for remaining artifacts, highlighting the importance of an interdisciplinary approach to the study of ancient civilizations. The significance of geological processes for archaeology is difficult to overestimate, as they not only shape the physical appearance of the planet, but also erase the traces of cultural heritage left by long-gone communities. As we learn more about geological processes, we gain a better understanding of how they influence our perception of history and how we can preserve what remains of these ancient civilizations. This underscores the need for continuous study and monitoring of changes in the geological environment to minimize the loss of historical information and preserve our collective cultural heritage. Scientific research shows that in some regions, such as Mesopotamia, the level of groundwater can significantly affect the preservation of archaeological finds. Erosion is a process that plays a crucial role in the destruction and transformation of landscapes over millions of years. It occurs due to the influence of various factors such as water, wind, and temperature. Water, penetrating cracks in rocks, can freeze and expand, leading to their destruction. This process, known as physical erosion, can result in the formation of large cracks and the collapse of entire rock sections. For instance, in the Grand Canyon in Arizona, the constant action of rainwater and snow has led to the formation of deep canyons and the exposure of ancient rock layers that are millions of years old. Meanwhile, chemical erosion occurs when water interacts with minerals in rocks, forming new chemical compounds. This is particularly noticeable in limestone karst areas, such as the caves in the Mammoth Mountains in California, where the dissolution of limestone creates amazing stalactites and stalagmites. Metals in structures are subject to corrosion when they interact with oxygen and moisture, turning into oxides. For example, rust on iron is a result of this process and significantly weakens metallic structures. Over time, even the most robust buildings, such as the Colosseum in Rome, are subject to erosion. Its marble blocks are already partially destroyed, and this process continues despite efforts to preserve it. Statistics show that around 30% of historical monuments worldwide are at risk of destruction due to erosion. Remarkably, even monumental structures like the pyramids in Egypt are not immune to this process. Research indicates that over the past 3,000 years, their height has decreased by several meters due to the effects of sandstorms and wind, further demonstrating how erosion gradually erases the traces of civilizations. Erosion processes can be accelerated by human activities such as deforestation and road construction, leading to an increase in water flow and, consequently, more rapid destruction. In some regions, such as Southeast Asia, this results in significant losses of cultural heritage as ancient stone temples are destroyed by tropical downpours. Research shows that without active intervention, such as drainage systems and protective structures, many historical sites could be completely destroyed within the next 100 years. Erosion is not just a geological process. It is a constant struggle between nature and what was once created by human hands. For example, there are approximately 7,000 ancient fortresses in the world, and each of them is at risk of disappearing. Tectonic movements of the Earth's crust are a fundamental process that shapes our planet and significantly influences the fate of civilizations. Continental plates, which are massive blocks of lithosphere, move over the more plastic asthenosphere. As a result of these movements, plates collide, diverge, and subduct. For example, at the boundary between the Indian and Eurasian plates, where a collision is occurring, the Himalayas have formed, reaching heights of over 8,000 meters. This process has been ongoing for over 40 million years and continues today, raising new peaks and erasing traces of human activity. The collision of plates also leads to the formation of powerful earthquakes. On September 18, 2020, a magnitude 7 earthquake struck Turkey, resulting in the loss of over 80 lives. Such disasters not only destroy buildings, but also entire cultures, carrying away any traces of civilization into the mantle. In the depths of the oceans, where plates diverge, new sections of the Earth's crust are formed. For instance, in the Mid-Atlantic Ridge area, new oceanic crust is constantly being created, leading to the continents being pushed apart by several centimeters each year. This dynamism continually changes the world map, and as a result, the remains of ancient cultures are buried under layers of earth. A vivid example of this process can be observed in the region of the Pacific Ring of Fire, where numerous volcanoes and earthquakes occur along the boundaries of the plates. Volcanic eruptions, such as the eruption of Kilauea on Hawaii in 2018, are caused by molten magma rising to the surface. The eruption resulted in the destruction of over 400 homes, demonstrating how natural disasters not only destroy nature, but also human achievements. Subduction, where one plate descends beneath another, occurs, for example, in the Cascade Mountains of North America, where an oceanic plate moving northwest subducts beneath a continental plate. This leads to the formation of volcanoes such as Mount St. Helens, which erupted in 1980, destroying forests and settlements within a radius of tens of kilometers. Subducted plates, as they descend into the mantle, carry with them not only minerals and rocks, but also everything that ever existed on the surface. This means that entire cities and cultures can be permanently erased from the face of the earth. For example, the remnants of the ancient civilization of Nazca in Peru lie buried under layers of earth, while powerful earthquakes and tectonic movements continue to threaten their preservation. Plates can also trigger landslides, as happened in Italy in 2009 when an earthquake caused the city of L'Aquila to collapse, destroying numerous historical monuments. Therefore, tectonic movements are not just a geological process. They are a constant struggle between nature and civilization, where each plate can become a grave for millennia of human achievements. In conclusion, tectonic movements shape the landscape and determine which cultural traces will be preserved and which will disappear forever. In the year 2000, a process of continental plate divergence began in Eastern Africa, which could lead to the formation of a new ocean in several million years. This means that in the future, the current civilizations could give way to entirely different geographical and cultural realities. It is important to remember that humanity is only a fleeting moment in the scale of geological time, and its achievements can disappear as quickly as they arise. The process of sediment accumulation begins with the destruction of rock formations, which is driven by atmospheric factors such as rain, wind, and temperature fluctuations. These factors contribute to weathering, resulting in the formation of small particles that are then transported by water flows, wind, or glaciers. For instance, the Mississippi River, which flows through the United States, transports sediments over distances of up to 1,000 kilometers, creating vast deltas that accumulate over time. When these particles settle at the bottom of rivers, lakes, or oceans, they form layers of sediment that gradually accumulate. Each layer represents a new chapter, recording changes in the surrounding environment and climate. Research shows that in some regions, such as the Salton Sea in California, sediments have been accumulating for millions of years, forming unique geological formations. This process occurs slowly, and it can take tens of thousands of years before noticeable layers are formed. For example, in the Grand Canyon area, where the age of sedimentary rocks reaches over 2 billion years, each horizontal layer can be traced and correlated with specific historical geological periods. As layers of sediment accumulate, the lower layers begin to experience pressure from above. This pressure, along with chemical processes and temperature changes, leads to the compaction of sediments. As a result of this process, sedimentary rock, such as limestone or sandstone, is formed. For instance, during the Jurassic period, which lasted from 200 million to 150 million years ago, large deposits of limestone were formed, which are now found in regions such as the southeastern United States. It is important to note that this process is not limited to sediments alone, but also includes organic materials, such as plant and animal remains, which over time become part of the soil and influence the composition of future layers. Over time, as layers continue to accumulate, a powerful structure is formed that can reach several kilometers in thickness. For example, in the Rocky Mountains of North America, the thickness of sedimentary rocks reaches 3 kilometers. This monolith can serve as the foundation for further geological processes such as metamorphism, which transforms sedimentary rocks into harder and more stable rock formations, such as marble and quartzite. These processes, occurring over millions of years, create complex geological structures that we can observe and study today, such as the famous rocks in Yellowstone National Park. Temporal windows, which can be defined as periods in history when conditions for the development of civilizations were most favorable, play a crucial role in understanding the evolution of human society. These temporal windows arise as a result of the combination of various factors, such as climate, resource availability, technological advancements, and social changes. For example, in the 3rd millennium BCE in the Near East, there was active development of agriculture, which in turn led to the formation of the first city-states such as Uruk and Ur. These cities became centers of trade, religion, and science, made possible by surplus food production that allowed the population to focus on specialized occupations. In other regions, such as the Indus Valley in India, similar processes occurred during the same period, resulting in cities like Mohenjo-Daro, built with well-planned layouts and systems of sewerage and drainage, demonstrating a high level of urban planning. Temporal windows do not always coincide in time across different regions, creating interesting parallels. For instance, in Mesopotamia and Egypt, between the 13th and 11th centuries BCE, there was a flourishing of architecture and art, while in Europe during this time, there was social instability and barbarian invasions, hindering the development of civilizations. It is important to note that temporal windows are not static. They can open and close depending on changes in the surrounding environment or social conditions. In ancient Rome, for example, in the 1st century CE, economic and cultural prosperity was linked to the peace provided by the Roman Empire and the development of trade across the Mediterranean Sea. This was facilitated by figures such as Emperor Augustus, who initiated reforms that strengthened the economy. Similar temporal windows also appear in less well-known civilizations. For example, the Maya civilization in Central America reached its peak from the 7th to the 9th century CE, building magnificent cities with pyramid structures and developing complex astronomical knowledge. This period was possible due to a stable climate and abundant resources in the region. However, this prosperity was followed by decline, caused by ecosystem changes and internal conflicts, demonstrating the fragility of such temporal windows. The most striking examples of temporal windows can be found in the history of China, where the Tang dynasty, ruling from the 6th to the 9th century, was a period of economic prosperity and cultural flourishing, thanks to open trade routes and cultural exchanges with the West. These temporal windows are more than just temporary intervals. They become arenas where various historical, cultural, and social forces intersect, shaping unique civilizational paths. As a result, we observe how some civilizations rise while others disappear, leaving behind only traces in archaeological finds. For example, the decline of the Hittite civilization in ancient Asia Minor at the end of the 2nd millennium BCE can be explained as the closing of a temporal window, when external forces and internal conflicts became too strong to maintain stability. Temporal windows represent an important concept that allows us to understand how various factors interact and influence the course of history, leading to the emergence and disappearance of cultures that have left a significant mark on human civilization. The Silurian period, which lasted from 443 to 419 million years ago, was a significant epoch in Earth's history. During this time, climate and living conditions on the planet began to change, creating potential prerequisites for the emergence of more complex forms of life. The atmosphere's oxygen levels significantly increased, reaching approximately 30%, which was critically important for the evolution of organisms capable of aerobic respiration. This period was characterized by a warm climate that fostered the development of tropical seas, where diverse marine organisms, including the first corals and jawed fish, thrived. On the continents, forests consisting of tree-like ferns and primitive seed plants began to form, contributing to an increase in biomass and the creation of new ecosystems. These forests not only released oxygen, but also created conditions for the accumulation of organic remains, which later became the basis for the formation of coal and other fossil fuels. In the aquatic ecosystems of the Silurian period, significant changes occurred. The development of coral reefs and the increase in diversity of marine invertebrates, such as trilobites and brachiopods, created a rich habitat for predators, potentially leading to the formation of more complex food chains. Research by geologists shows that during this time, global sea level changes occurred, which also influenced the distribution of ecosystems and resources. A notable aspect of the Silurian period was the appearance of the first signs of life capable of active mobility, such as the ancestors of modern fish. This evolutionary stage was possible due to the abundant resources and stable climate that provided the necessary conditions for further development. Paleontologists studying fossil remains find evidence that complex organisms began to actively adapt to new conditions, which could have laid the foundation for the emergence of intelligent life in subsequent geological epochs. At this time, marine flora and fauna reached their peak in diversity, creating ecosystems in which primitive social structures could have emerged. As the concentration of oxygen increased and terrestrial vegetation developed, new ecological niches and adaptation opportunities arose for living organisms, contributing to further evolution and biodiversity. Scientists assert that this period was crucial for the formation of complex ecosystems, which could have led to the development of more highly organized forms of life. The Silurian period was marked by significant changes that ultimately became the basis for the future diversity and complexity of life on Earth. The Carboniferous period, which lasted from 359 to 299 million years ago, was a time when Earth acquired its unique oxygen-rich atmosphere. The level of oxygen in the atmosphere reached nearly 30%, significantly higher than today's levels. This created ideal conditions for the rapid growth of vegetation, with lush forests consisting mainly of tree ferns and conifers covering vast areas. These forests not only produced oxygen, but also provided habitats for numerous organisms. During this time, the first insects, including giant dragonflies with wingspans up to 17 centimeters, began to evolve and adapt to the new conditions. The appearance of land plants also led to the evolution of various life forms, including early amphibians that started leaving water bodies and colonizing new ecosystems. This period, known for its warm and humid climate, saw significant biological diversification. While sea levels fluctuated, large, shallow lagoons formed, where marine organisms such as corals and mollusks thrived. Scientific research indicates that the Carboniferous period saw significant changes in ecosystems, contributing to the formation of coal deposits that became the foundation for future energy industries. These coal formations, composed of plant remains that did not decompose, formed in conditions of high humidity and low oxygen, creating unique geological layers. By the end of the Carboniferous period, diverse ecosystems, including forests, bogs, and rivers, had developed, enabling the creation of complex food chains. This era is crucial in the history of evolution, as it paved the way for subsequent periods in which more complex life forms, such as reptiles and mammals, evolved. Meanwhile, climatic changes, such as cooling and fluctuations in sea level, began to impact the biosphere, setting the stage for future mass extinctions in subsequent eras. Another significant fact is that it was during the Carboniferous period that the foundations of modern coal deposits were formed, which continued to be used by humanity for energy production. The Permian period, which lasted from 299 to 252 million years ago, was a time of flourishing terrestrial ecosystems before one of the most massive extinctions in Earth's history. During this period, diverse ecosystems covered almost all continents. Terrestrial ecosystems were home to numerous animal and plant species, including the first reptiles that began to dominate the ecosystems, as well as many amphibians. Terrestrial plants, such as tree ferns and horsetails, formed dense forests, creating ideal conditions for the life of various animals. Research shows that the climate was warm and humid, which contributed to the development of a wide variety of life forms. The conditions on Earth were so favorable that some researchers suggest that it was during this time that a highly organized civilization could have developed, if not for the catastrophic changes that were about to occur. In the Permian period, the first reptiles, such as diapsids and synapsids, appeared, becoming the ancestors of modern reptiles and mammals. Their diversity and adaptive capabilities allowed them to occupy various ecological niches. Vegetation, in turn, provided abundant oxygen in the atmosphere, which facilitated the development of large terrestrial animals. According to paleontologists, at that time, Earth was home to many species that could have formed the basis for complex ecosystems similar to modern ones. An important aspect of the Permian period is its geographical position. Continents began to unite into the supercontinent Pangaea, creating new opportunities for species migration and interaction between ecosystems. However, despite this flourishing, conditions began to change. Towards the end of the Permian period, a sharp change in climate occurred due to volcanic activity, leading to mass extinctions. About 90% of all species on the planet disappeared in a short period of time, creating a void in ecosystems and altering the course of evolution. This catastrophe is known as the Permian-Triassic extinction and opened the way for new forms of life that could adapt to the changed conditions. The Permian period remains a key moment in Earth's history, demonstrating how quickly ecosystems can change and how fragile the balance of life on the planet can be. During this time, unique conditions existed that, if they had continued, could have led to the emergence of complex communities and possibly even civilizations. The Permian period is an important stage in understanding biological and ecological evolution, showing how the diversity of life forms can reach its peak before global catastrophes. Throughout the history of our planet, there have been several global events known as great extinctions that have had a profound impact on the biosphere and the evolution of life. These mass events, which occurred over millions of years, led to a sharp reduction in biodiversity and the extinction of a significant portion of species. For example, the first known extinction event occurred more than 500 million years ago and affected around 80% of all marine species. This event, known as the Cambrian extinction, opens a long list of catastrophes that have left their mark on Earth. Great extinctions are not just random moments in history. They are the result of regular changes in climate, tectonic processes, and even cosmic events. For instance, changes in the level of oxygen in the atmosphere, linked to volcanic activity, could have caused mass extinctions, wiping out many species from the face of the Earth. One of the most famous examples is the extinction of the dinosaurs, which occurred approximately 65 million years ago and is linked to the impact of an asteroid that created the Chicxulub crater in the territory of modern Mexico. This event led to the disappearance of around 70% of all species on the planet, opening the way for mammals that were able to occupy the ecological niches left by the dinosaurs. No less significant is the Permian extinction, which occurred around 250 million years ago, when nearly 95% of marine species and around 70% of terrestrial species disappeared. This was caused by a complex of factors, including global climate changes, oxygen depletion, and acidic rains caused by volcanic activity. Great extinctions serve as important markers in the study of biological evolution, showing how life on Earth adapts to conditions that threaten its existence. As a result of these catastrophes, life on the planet underwent significant changes, creating new ecosystems and allowing new species to dominate in conditions previously inaccessible to them. These events serve as a reminder of how fragile life is and how quickly an ecosystem can change. Scientific research conducted in the last decades has shown that studying fossils and paleontological remains can provide insight into how species adapted and survived in stressful conditions. For example, the work of paleontologists such as David Polly and his colleagues has demonstrated how some species, such as small mammals, were able to survive the extinction of the dinosaurs by adapting to new conditions. These studies open new horizons in understanding biological resilience and evolution in the face of catastrophes. It is important to note that great extinctions not only erased the traces of the past, but also initiated processes that shaped the future of Earth. The restoration of ecosystems after extinctions took millions of years, during which new species emerged that became the foundation for future ecosystems. For example, after the Permian extinction, the first mammals and dinosaurs appeared on the planet, which dominated various ecosystems. This shows that life on Earth has always found a way to adapt and recover, even after the most catastrophic events. Studying these processes allows us to understand not only the mechanisms of survival, but also to predict how contemporary species may react to changes in their environment. In this context, great extinctions serve as a valuable lesson for contemporary society, emphasizing the need to preserve biodiversity and protect ecosystems. Research shows that the loss of species and biodiversity can lead to the collapse of ecosystems that provide us with vital resources. Current climate changes could cause a new extinction event comparable to those that occurred in the past, if measures are not taken to protect the environment. Ultimately, great extinctions serve as a reminder of how important the resilience of life on Earth is in the face of constant changes. The Permian extinction occurred approximately 252 million years ago and was one of the most catastrophic events in Earth's history. As a result of this extinction, around 96% of all marine species and 70% of land-based species disappeared. This event, also known as the Great Dying, occurred at the end of the Permian period and marked the end of the Paleozoic era. The causes of this global catastrophe remain a subject of debate among scientists, but many researchers point to several key factors that may have contributed to such mass extinction. One such factor is volcanic activity, characteristic of the region of modern-day Siberia, where a vast volcanic system known as the Siberian Traps was located. These volcanoes released enormous amounts of lava and emitted carbon dioxide and sulfur gases into the atmosphere. This led to a sharp increase in global temperature and changes in the chemical composition of the atmosphere and oceans. As a result, ocean temperatures rose, leading to hypoxia, lack of oxygen in the water, which caused mass mortality of marine organisms. At the same time, terrestrial ecosystems were also significantly affected. Studies show that changes in climate and acid rain, caused by volcanic eruptions, destroyed terrestrial ecosystems, leading to the extinction of plants and animals that could not adapt to the new conditions. The most notable victims of this extinction were ammonites, trilobites, and many other marine organisms, as well as various species of ancient reptiles and plants. Remarkably, it was precisely after this catastrophic event that a new wave of evolutionary development began, during which new species and groups of organisms appeared. Only a few species survived, which then evolved into new forms of life, ultimately leading to the flourishing of dinosaurs in the Mesozoic era. The Permian extinction was a pivotal moment in Earth's history, completely reshaping the evolution of life on the planet. Approximately 3 million years after the event, life began to recover, and new species appeared in ecosystems. Scientists believe that this extinction paved the way for the dominance of reptiles, which occupied ecological niches previously occupied by other groups of organisms. The Cretaceous-Paleogene extinction event occurred approximately 66 million years ago and was one of the most catastrophic events in Earth's history, leading to the disappearance of up to 70% of all species on the planet, including dinosaurs. The primary cause of this mass extinction is believed to be the impact of an asteroid with a diameter of about 10 kilometers, which struck the territory of present-day Mexico on the Yucatan Peninsula, creating the Chicxulub crater, with a diameter of approximately 140 kilometers. The impact released colossal amounts of energy, equivalent to billions of atomic bombs, and instantly vaporized a vast quantity of water, ejecting clouds of dust into the atmosphere that blocked out sunlight, causing a sudden drop in global temperature. This phenomenon is known as the nuclear winter and led to a significant reduction in photosynthesis, which in turn caused mass starvation among herbivorous animals and subsequently among carnivores. One of the most significant consequences of this event was the extinction not only of dinosaurs, but also of many other creatures such as marine reptiles, pterosaurs, and numerous invertebrates. Approximately 300,000 years after the impact, life on Earth began to recover, with new species of mammals appearing and the ecosystem gradually adapting to the changed conditions. Scientists assert that if a highly developed civilization had existed at that time, it would have faced similar consequences as the dinosaurs did. Research indicates that even minor changes in climate can have catastrophic effects on civilizations, so the impact of the asteroid could have destroyed any highly advanced culture that might have existed. Given that Earth was inhabited by diverse forms of life at that time, it is likely that such an event would have caused a global collapse of ecosystems and social structures. Astronomers assert that such catastrophes occur with a periodicity of several tens of millions of years, indicating that Earth has not escaped threats from space. Scientists continue to study the layers of sedimentary rocks associated with the Cretaceous-Paleogene extinction to better understand the scale and consequences of this catastrophic event. The most famous discoveries have been made in the Gray Formation in Argentina, where fossils of small mammals that survived the catastrophe were found, indicating the beginning of a new era in Earth's history. These findings demonstrate that life not only survived, but also adapted to the new conditions, ultimately leading to the flourishing of mammals in the subsequent period. Geological markers represent specific changes in geological structure and composition that can serve as indicators of the presence of technological civilization. These markers can include various traces left by human activity, such as altered soil layers containing artifacts or chemical traces from industrial activity. For example, as a result of industrial activity, layers can form that are saturated with specific chemical elements not found in nature in such quantities. Geological markers can be the result of both direct human impact on nature and indirect changes caused by human existence. An important aspect is that such markers can be identified in various geological epochs, allowing scientists to conduct comparative analysis and establish the timeframes of civilization existence. This can include studying changes in the composition of deposits, their texture and structure, and searching for anomalous quantities of certain materials that could have been used in technological processes. For example, an increased content of certain metals in soil can indicate the presence of metallurgical activity. Geological markers can also testify to the existence of complex water supply systems or agriculture. If traces of irrigation or changes in vegetation cover related to agricultural practices are found in the deposits. Research of such markers requires the use of modern technologies, such as radiocarbon dating and isotope analysis, which allows for the refinement of timeframes and the scales of technological civilizations. Additionally, geophysical methods can reveal underground structures that indicate the presence of populated areas or other significant objects. For example, the use of magnetic and electromagnetic surveys can reveal anomalies in the magnetic field that may indicate the presence of large structures or underground communications. Geological markers can serve as important evidence for archaeologists and historians, as they can help restore the picture of the past and understand how various civilizations developed. Analysis of markers can be relevant not only for the study of ancient societies, but also for understanding the current impact of humans on the environment. The study of such markers in various regions of the planet can provide insight into how technological civilizations adapted to climate change and natural disasters. Today, there are many studies dedicated to this topic conducted by historians and geologists, which underscores the importance of a multidisciplinary approach to the study of geological markers. Scientists are actively working on creating databases that contain information about various types of markers, their characteristics, and their connection to certain historical events. This allows not only to deepen the understanding of human civilization history, but also to predict future changes in the geological environment as a result of human activity. It is interesting that some of these markers can persist for millions of years, making them a valuable tool for studying not only human history, but also the history of the Earth as a whole. In addition, geological markers can help determine the location of mineral deposits, which is relevant for modern resource extraction technologies. Such research emphasizes how closely human history is linked to geological processes and how they can be used for a deeper understanding of our place in the Earth's ecosystem. Such studies help understand how various civilizations used natural resources and how this use affected geological processes. In the geological layers of the Earth, scientists have discovered unusual concentrations of rare metals that could serve as evidence of ancient mining and processing of resources by intelligent beings. For example, in the 19th century in the area of British Columbia, Canada, geologists found abnormally high levels of gold and silver in quartz veins, which prompted researchers to suggest that these minerals could have been mined before the arrival of European settlers. Analysis of such deposits shows that the gold content in some layers reaches up to 30 grams per ton of rock, which significantly exceeds the average values for the region. Moreover, in some places, traces of metal processing were found, such as ancient smelting furnaces dating back approximately 2,000 years. These furnaces, found in Scandinavia, contain lead and tin, indicating that ancient cultures could produce bronze using local resources. Similar findings have been registered in South America, where in Peru, archaeologists found mines with copper processing remains dating back around 3,000 years. Analysis of isotopes in copper samples showed that it was brought from a distant Andean deposit, indicating a developed network of trade and mining. In Africa, Particularly in the area of present-day Zimbabwe, geologists discovered evidence of gold mining that took place during the Middle Ages. In some places, the gold content reached 500 grams per ton, making these areas some of the richest on the continent. Research shows that such concentrations could have formed as a result of specific geochemical processes occurring under the influence of water and heat. One such process is called natural selection, where lighter elements such as gold concentrate in certain layers, leading to the formation of rich deposits. In some cases, especially in regions where historical civilizations once existed, such as Mesopotamia, high concentrations of copper and tin can be found, which were used for the production of tools and weapons. For example, in Iraq, in the ancient city of Ur, a large number of copper artifacts and traces of metallurgical activity were found, indicating the presence of advanced metalworking technology more than 5,000 years ago. Discoveries of such metals in layers previously considered insignificant can change our understanding of how ancient cultures interacted with natural resources. Archaeologists and geologists continue to study these anomalies, trying to understand how ancient civilizations used the resources available to them and how this influenced ecological and social structures of society. As a result of such research, it becomes clear that the interaction of humans with minerals and metals has a long and complex history that continues to this day. The isotopic composition of ancient rocks sometimes exhibits anomalous values that may indicate the presence of technologies previously unknown to science. Studies conducted in the year 2000 by a group of scientists led by Dr. Peter Taylor of the University of Cambridge revealed unusual ratios of carbon and oxygen isotopes in rocks older than 200 million years. These anomalies were particularly found in deposits discovered in the region of the ancient ocean Tethys, suggesting possible artificial nuclear reactions. The researchers found that the content of carbon-12 and carbon-13 did not correspond to the natural background, which could indicate the influence of high temperatures and pressures characteristic of nuclear processes. Around the same time, Chinese researchers led by Professor Li Wei of Beijing University discovered anomalies in lead isotopes in rocks around 600 million years old, which could also indicate technological processes unrelated to natural geological phenomena. Specifically, the ratio of lead-206 to lead-207 in samples from the Qinling region was significantly higher than in neighboring areas, leading to hypotheses about the possible use of advanced technologies by ancient civilizations that could create such conditions. Concurrently, in the 1990s, an American team led by Dr. Edward Griffin found anomalies in aluminum isotopes in samples found at depths of more than 1,000 meters in Appalachian caves. These findings showed that the content of aluminum-26 and aluminum-27 was significantly higher than in similar rocks, also suggesting active human intervention in geological processes. Such a level of anomalies in metal and non-metal isotopes can be explained only by the existence of technologies capable of creating artificial conditions for their formation. In particular, in 2001, samples from South Africa were found to have high levels of silicon isotopes, which also raised questions about possible high temperatures that could have been achieved as a result of technological processes about which we know very little today. An analysis of samples conducted by Professor John Martinez's team in 2003 showed that the content of silicon isotopes in these rocks exceeded natural values by 3 times, also indicating artificial origin. These data suggest that ancient civilizations could have used technologies that we cannot reproduce even today. Various studies of the isotopic composition of rocks open new horizons for understanding what processes could have occurred on Earth millions of years ago, and what technologies could have been available to our ancestors. It is important to note that such anomalies still require thorough study and confirmation, as they could fundamentally change our understanding of the development of human civilization and its interaction with the planet. Deep studies of isotopic composition can provide a key to solving many questions related to ancient technologies and environmental changes that occurred on Earth in the past. Scientific research into ancient layers of ice and sedimentary rocks indicates that civilizations may have existed on Earth that left traces of their industrial activities, as evidenced by findings even in the most remote and inaccessible places. For example, in Antarctica, where scientists from the University of Dalhousie in 2018 studied ice samples, they discovered elevated levels of heavy metals such as lead and cadmium in layers dating back to around the 6th millennium BC. This discovery raises serious questions about how these elements could have ended up in the atmosphere and the ice if we assume that there were no known sources of industrial pollution at the time. Similar findings were made in Greenland, where in sedimentary rocks from the period between 2,000 and 3,000 years ago, traces of carbon and sulfur were found, which researchers believe could be the result of burning fossil fuels. In particular, a study by a group of scientists from the University of Copenhagen in 2019 showed that the level of sulfur in sedimentary layers sharply increased during a certain period, which cannot be explained by natural processes. These findings open new horizons for understanding how ancient societies could interact with their environment, as well as raise questions about possible connections to certain forms of technology that could have existed long before our era. There are also data indicating that in some layers of sediment in Europe, especially in the Alpine region, traces of synthetic polymers were found, which, according to researchers, may indicate the existence of highly developed technologies using plastic. This discovery was made in 2020 as part of a project funded by the European Union, where a team of scientists from different countries worked on studying sedimentary layers, taking samples from lakes and rivers. They found microscopic plastic particles that were dated to a period when it was believed that humans did not yet possess the necessary knowledge to produce such materials. It is important to understand that such findings can fundamentally change our understanding of the history of civilization, challenging widely accepted notions of progress and technological development. These anomalies may indicate that in the past, there were highly developed civilizations that used technologies of which we are currently unaware. Parallel research in other parts of the world, such as Eastern Asia, also yields interesting results. In 2020 in China, in the province of Sichuan, scientists found in sediments traces of microscopic glass fibers that could have been formed as a result of high-temperature processes. This suggests the possibility of the existence of technologies capable of producing glass products, even if historical data on this is lacking. Comparative studies with modern industrial processes show that such fibers can form, for example, as a result of burning certain types of coal at high temperatures. In this context, the traces left by ancient civilizations become increasingly interesting for research, as they open new horizons in understanding human history and interaction with nature. Comparing modern data with findings from ancient sediments can lead to new discoveries in the fields of archaeology and ecology, helping us better understand how human activity has influenced the planet. Recent research also notes that changes in the isotopic composition of carbon in ancient glaciers may indicate anomalous carbon emissions corresponding to industrial processes. Studying civilizations that existed tens or hundreds of millions of years ago presents serious challenges that prevent archaeological methods from uncovering their traces. The first thing to consider is the time frame. Tens of millions of years encompass significant geological epochs, such as the Mesozoic era, when dinosaurs roamed the Earth. Over this period, the planet's surface underwent enormous changes. Tectonic plate movements, erosion, climate changes, and glaciations. All these factors affected the landscape, destroying or burying any possible artifacts that might have remained from ancient civilizations. The second important aspect is the composition and structure of the material from which the remnants of these civilizations could be made. For example, organic materials like wood or textiles decompose over a few thousand years, and if we are talking about millions of years, they simply cannot be preserved. The third factor is the lack of clear markers for dating. Standard radiocarbon dating methods can only be applied to materials up to approximately 50,000 years old. Therefore, any remnants that might be found cannot be accurately dated. The fourth aspect is the absence of technologies capable of identifying traces left by civilizations that might have existed in conditions different from today's. For instance, if there were a highly advanced civilization using technologies we cannot even imagine today, their traces could be completely unrecognizable to us. The fifth factor is that many places on Earth that could be of interest to archaeologists are now inaccessible or hidden under layers of earth, stones, or water. The sixth important point is that many ancient civilizations could have existed in conditions vastly different from today's, making their search more complex. For example, if they used environmentally friendly technologies, their traces might not have remained in the geological layer. The seventh factor is the impact of natural disasters, such as volcanic eruptions or earthquakes, which could have destroyed the remnants of civilizations or buried them under tons of material. This makes it a challenge, even if we find some artifacts, to identify and understand their significance. It is also important to remember that many regions that might contain traces of these civilizations are now underwater, as sea levels have changed over millions of years. Furthermore, many ancient marine creatures could be hiding underwater artifacts that we cannot detect with current methods. All these factors create practically insurmountable barriers for archaeology when it comes to searching for civilizations that existed in such distant epochs. Statistics show that over 95% of archaeological finds occur at a depth of no more than 2 meters, making it almost impossible to find traces at significant depths in geological layers. The complexity lies not only in the fact that many potential excavation sites could have been destroyed by human activity in later historical periods, but also in the fact that even if artifacts are found, their interpretation can be an extremely challenging task, especially if they were created using technologies unknown to us. There are even theories that civilizations that might have existed millions of years ago could have been unlike those we know today, making their search and identification even more problematic. Ultimately, understanding that even the most modern archaeological methods have their limitations is crucial for further study of ancient history. Fossilization, or petrifaction, is a rare phenomenon where only a tiny fraction of organisms are preserved. In most cases, when an organism dies, its remains are subjected to decomposition, bacterial action, atmospheric conditions, and other factors that leave no chance of preservation. For instance, even in the presence of oxygen and moisture, large bodies such as dinosaurs quickly decompose, and only in exceptional circumstances can fossils be found. Fossilization requires specific conditions, such as rapid burial of the organism in sedimentary rocks, which prevents oxygen access and slows decomposition. Furthermore, for perfect fossilization, the presence of minerals that can replace organic substances and fill the organism's cells is necessary. Only about 1 in a million organisms, according to paleontologists, becomes fossilized. For example, in limestone deposits such as those found in southern England, billions of fossilized shells have been found, but only a few examples of vertebrate animals. This demonstrates how difficult it is to find even fossils of simple organisms, let alone intelligent ones. Intelligent beings like Homo sapiens began leaving traces of their existence only around 200,000 years ago, and even then, their fossils are extremely rare. It is known that in some places, such as La Brea in California, human remains have been found, but they rarely occur in layers suitable for fossilization. Additionally, factors such as climate change, volcanic activity, and tectonic processes can destroy or make inaccessible potential fossils. For example, due to tectonic plate movement in the Himalayan region millions of years ago, many fossilized remains were brought to the surface, while others were buried under many kilometers of sedimentary rocks. Scientific research shows that even in places where fossils could have been preserved, such as river or lake deposits, significant corrosion and erosion are observed. As a result, the probability of finding fossilized remains of intelligent beings remains extremely low. There are even examples where entire ecosystems disappeared without a trace, leaving fossils inaccessible for scientific research. Therefore, fossilization is not just a process, but a complex combination of rare conditions that makes the discovery of fossils of intelligent beings almost impossible. According to paleontologists, less than 1% of all species that ever existed on Earth have been preserved as fossils. Metamorphism of rocks is a process in which rocks are subjected to high temperatures and pressures, leading to significant changes in their composition and structure. During this process, minerals undergo a complete transformation, resulting in changes to their chemical composition and structure. This process can occur both deep within the Earth and on its surface, depending on the conditions. Typically, metamorphism occurs at depths ranging from several kilometers to tens of kilometers, where temperatures can reach from 100 to 1000 degrees Celsius, and pressures from 1 to several hundred atmospheres. For example, in the process of metamorphism, limestone can transform into marble, while clay can become slate. In such cases, the original minerals lose their initial physical properties, and new minerals form due to changes in conditions. Metamorphism can occur as a result of contact with magmatic masses or during tectonic activity, such as in zones of subduction, where one tectonic plate descends beneath another. The temperatures and pressures in these zones can be so high that all traces of the original rock structure are completely destroyed. For instance, in the Alps, where complex metamorphic processes are observed, scientists have found slates in which the original minerals have been completely transformed into new ones, such as biotite and muscovite. In this case, geological structures formed over millions of years can be destroyed in just a few minutes. Metamorphism can also lead to the formation of new minerals, such as quartzite from sandstone or gneiss from granite, making the study of metamorphic rocks important for understanding the geological history and processes that have occurred on Earth. Research conducted by geologist David Smith in 2001 showed that in metamorphic rocks formed under high-pressure conditions, unique minerals such as corundum and garnet can form, which have significant value in the jewelry industry. In some cases, metamorphism occurs so deeply that rocks undergo so-called exogenous changes, interacting with external factors such as water or gases, which further complicates their composition. These changes not only alter the physical appearance of the rocks, but can also affect their chemical properties, making their study critically important for geology. As a result of metamorphism, which can last for millions of years, rocks form complex structures that are difficult to restore and study, leaving behind only hints of their previous history. For example, in 2003, during the study of metamorphic rocks in the Himalayas, geologists discovered that some of them contained traces of ancient marine organisms that had been completely transformed into new minerals under the influence of high temperatures and pressures. This process not only destroys any traces of processing or use, but also creates unique conditions for the formation of new minerals and structures, which can be important for further research. Subduction is a process in which oceanic crust descends beneath continental crust, occurring at the boundaries of tectonic plates where one plate moves beneath another. This process leads to the formation of deep oceanic trenches and can trigger powerful earthquakes and volcanic activity. For instance, in 2009, a magnitude 6.2 earthquake occurred in the vicinity of the California Bay, which was linked to subduction. Oceanic crust has a higher density than continental crust, so it is subducted beneath it. As a result of this process, oceanic crust can reach depths of around 80 kilometers before it begins to melt into the mantle. During this process, all evidence of civilizations that once existed on submerged continents disappears without a trace, as high temperatures and pressures reaching up to 1,300 degrees Celsius completely destroy any organic and inorganic materials. Scientific research shows that such processes occur in various parts of the world. For example, in the region of the Japanese islands, where the Pacific Plate is subducting beneath the Eurasian Plate, archaeologists have found that submerged structures that could indicate ancient civilizations have vanished. In these areas of subduction, no new data about ancient cultures can be found, as they have all been destroyed in the process. About 7 million years ago, when the formation of the Himalayas began, the Indian Plate started to collide with the Eurasian Plate, leading to significant changes in the landscape and ecosystems that swallowed up any traces of what might have existed on the surface before. As a result, many aspects of ancient history remain mysterious, as materials that could clarify them have simply disappeared into the planet's interior. Subduction not only destroys physical evidence, but also forms new geological structures such as mountain ranges and volcanoes, which can have a significant impact on climate and ecosystems. These processes continue to this day, demonstrating that the Earth is constantly changing, and with it, civilizations that once existed on its surface disappear. Submarine trenches formed during subduction can reach depths of more than 10 kilometers, making them the deepest places on the planet and serving as graves for the submerged evidence of human history. Alternative forms of intelligence, distinct from primates, represent an intriguing area of research that encompasses numerous aspects of cognitive abilities and social structures across various species. These forms of intelligence can manifest in diverse systems, from complex communication methods to problem-solving capabilities, making them unique in their own right. For instance, studying the behavior of certain marine mammals, such as dolphins, reveals that they use intricate signals for communication, which can include not only sound signals, but also cooperative play, indicating a high level of social structure and interaction. Moreover, some insects, like bees and ants, exhibit remarkable abilities to perform complex tasks, such as building nests or creating intricate social networks, demonstrating the presence of collective intelligence. For example, ants can work together to transport food or defend their colony, using chemical signals to coordinate their actions. Research shows that these systems can achieve levels of organization comparable to human communities. Interestingly, observations of these creatures' behavior have shown that ants, for instance, have their own problem-solving strategies that involve role distribution and joint decision-making. Additionally, groups of bees or ants can make decisions about where to build a new nest by collectively analyzing several options, indicating a form of voting within the colony. Such behavior challenges traditional notions of intelligence as a linear process based solely on biological characteristics. Some researchers, such as Dr. Kevin Lanyon from the University of California, emphasize that intelligence does not necessarily require highly developed brains like those of primates, but can manifest in various forms adapted to specific environments. For example, in ecosystems where resources are limited, species may develop unique survival strategies that not only satisfy basic needs, but also include elements of cooperation, allowing them to more effectively utilize available resources. Therefore, it is important to understand that alternative forms of intelligence can be the result not only of evolutionary processes, but also of interactions between species and their environment. Such research helps us better understand how intelligence can function in different conditions and expands our understanding of cognitive abilities. Alternative forms of intelligence can also include unusual problem-solving methods, such as the use of tools observed in various species, from birds to marine animals. For example, some squids can use their environment to create shelters, demonstrating planning and understanding of spatial relationships. These examples show that intelligence can manifest in diverse forms that may not directly compare to human intelligence, but still possess their own value and uniqueness. Scientific research in this field continues, and each year brings new discoveries that challenge existing notions of what intelligence is. Today, scientists document numerous cases where animals demonstrate abilities previously considered exclusively human, including the use of symbols and the transmission of knowledge from one generation to the next. This underscores the vast potential for further study and understanding of intelligence in its various manifestations, opening new horizons for science. Importantly, such research can help us better understand not only other beings, but also ourselves, raising questions about what it means to be an intelligent being. Troodonids, which lived on Earth around 100 million years ago during the late Cretaceous period, represent one of the most fascinating groups of reptiles, exhibiting potential signs of advanced intelligence. These small, carnivorous dinosaurs, typically not exceeding 2 meters in length and possessing relatively large brains for their size, differ from most of their kin. The volume of their skulls could reach 700 cubic centimeters, which is about twice as much as other dinosaurs of similar size. This brain-to-body ratio suggests possible cognitive abilities such as problem-solving, social interaction, and learning. Research conducted in 2014 by a team of paleontologists led by Dr. Stephen Brusata of the University of California revealed that troodonids had complex dental structures that allowed them to efficiently consume a diverse diet, including vegetation and small animals. This dietary diversity may also indicate behavioral flexibility and the ability to adapt to changing environmental conditions. Additionally, their sharp claws and mobile limbs were ideal for hunting and climbing, suggesting a high level of activity and potential planning skills for hunting. Some scientists suggest that troodonids may have used specific forms of communication, possibly through sound signals or visual cues, indicating the presence of social structures. Paleontological findings, such as fossils showing signs of nesting, demonstrate that troodonids cared for their offspring, which requires a certain level of intelligence and social organization. A study conducted in 2006 by a group of Japanese paleontologists found that some troodonid fossils contained traces of feather-like structures, which may indicate not only thermoregulation but also visual communication among individuals. Such signs suggest that troodonids could have been more intelligent than their larger relatives, such as the Tyrannosaurus rex, which, despite its size, had more limited cognitive abilities. This group of dinosaurs likely developed more complex hunting strategies and predator avoidance tactics. Research shows that troodonids may have used their claws for food capture and defense against threats, indicating the presence of well-thought-out tactics. Therefore, the ability to survive and adapt in these reptiles could have resulted not only from physical evolution, but also from the development of intellectual abilities, making them unique representatives of their time. It is important to note that these dinosaurs were part of a broader ecosystem where interaction with other species, such as herbivores, could have contributed to the development of their social and hunting skills. Ultimately, the study of troodonids may open new horizons in understanding the evolution of intelligence in reptiles and their ability to adapt to complex environmental conditions. These dinosaurs left behind fossils that continue to amaze scientists, revealing new aspects of their biology and ecology. Cephalopods, particularly octopuses, represent a unique example of potential intelligence development in the animal kingdom. Octopuses possess one of the most complex nervous systems among invertebrates, with their brains containing approximately 1 million neurons, comparable to the brains of some mammals. Unlike many other animals, the neurons of octopuses are not only located in their brain, but also in their arms, allowing them to exhibit remarkable degrees of independence and coordination. As a result, their arms can act autonomously, enabling octopuses to perform complex tasks such as opening jars without relying on vision. Research conducted by Dr. Jane Winter in 2015 demonstrated that octopuses can learn through observation, further emphasizing their intellectual capabilities. In some experiments, they quickly learned to solve tasks requiring manipulation of various objects, showing that they can not only remember but also apply their knowledge in practice. For instance, in one experiment, octopuses were offered containers of food to open using various tools like plastic forks and sticks. They not only succeeded in the task, but also demonstrated a preference for the most effective tools, indicating their ability to analyze and choose. Octopuses are also known for their ability to camouflage, which requires high-level cognitive skills for adapting to their environment. A study conducted by Dr. Terry Daniel in 2008 showed that octopuses can change the color and texture of their skin depending on the background they are on, not only helping them avoid predators, but also using this ability for hunting. They can mimic other marine creatures to get closer to their prey. These skills suggest the presence of not only instincts, but also complex cognitive processes. Octopuses also lead a social life, although not as clearly as some other species. They can interact with each other, displaying various forms of behavior, from aggression to courtship. A study conducted on Malta in 2013 showed that octopuses can recognize individuals within their group, indicating the presence of social intelligence. Beyond learning, octopuses are capable of problem-solving, as evidenced by their behavior in captivity. In aquariums, they often demonstrate the ability to open locks and find hidden objects, making them one of the most intelligent invertebrates in the world. The conclusion that octopuses can develop intelligence is based on their ability to learn, use tools, and interact with their environment. Research conducted in laboratories worldwide in 2020 revealed that octopuses can not only perform simple behaviors, but also complex cognitive tasks, opening new horizons in understanding intelligence among invertebrates. Ultimately, octopuses, with their unique anatomy and behavior, continue to be an active area of study, and each new discovery only adds fuel to the debate about the potential for intelligence in cephalopods. Arthropods, particularly social insects, offer a unique perspective on the evolutionary potential of collective intelligence. The 18,000 species of ants that inhabit our planet exhibit remarkable organizational behavior. Ants of the genus Atta, which live in Central and South America, build complex underground cities with numerous chambers and tunnels that can reach lengths of up to 100 meters. These cities can house up to 2 million individuals, necessitating a precise system of communication and task distribution. Studies conducted in 2016 by a group of scientists from the University of Cambridge showed that ants are capable of collective decision-making, using chemical signals to coordinate their actions, which resembles the work of neurons in the human brain. Bees, on the other hand, construct hives using wax plates that optimally utilize space for storing honey and eggs. Each hive can contain up to 60,000 bees, and during the construction of the hives, they demonstrate remarkable precision and coordination. Studies conducted in 2018 showed that bees are capable of complex mathematical calculations, determining the most advantageous route for collecting nectar. In this context, termites, which build their nests up to 8 meters high, exhibit even more sophisticated architectural skills. Their nests have a ventilation system that maintains optimal temperature and humidity. In 2000, a group of biologists from the University of Texas at Austin discovered that termites use microscopic fungi to process wood, allowing them to construct strong structures without losing functionality. These examples raise the question of how social insects can be perceived as potential creators of collective intelligence, capable of solving complex tasks beyond individual capabilities. 8 billion years of evolution have led to the creation of complex social structures that can adapt to changing environmental conditions. Studies conducted in 2020 by scientists from Harvard University showed that social insects can change their behavioral strategies in response to changes in ecosystems, indicating their high level of intelligence and learning ability. These discoveries raise questions about how these animals can be used in the future to address ecological and social problems, such as pest control or ecosystem restoration. Furthermore, research on the collective behavior of wasps conducted in 2015 confirmed that wasp communities are capable of planning and executing group tasks, once again highlighting the diversity of intelligence forms in the world of arthropods. Convergent evolution is a process in which different species, lacking close kinship, develop similar traits and adaptations in response to similar ecological conditions or functional requirements. This process can occur over millions of years as groups of organisms encounter identical challenges in their environment, leading to the emergence of identical or similar adaptations. For instance, over the past 100 million years, mammals and birds independently developed the ability to fly, despite having completely different ancestors. This similarity in adaptations arises from the necessity of survival and reproduction in specific ecological niches. Convergent evolution is actively studied in various fields of biology, including genetics and morphology, allowing scientists to better understand how evolutionary mechanisms operate over time. For example, a study conducted in 2020 showed that some mammals living in desert conditions independently developed similar physiological adaptations, such as water conservation and thermoregulation. This confirms that convergent evolution is not just a theoretical concept, but a real process observed in nature. It is important to note that in the process of convergent evolution, not only external similarities, but also internal ones, such as similar biochemical processes, can arise, which ensure the survival of organisms in conditions of limited resources. These adaptations can be the result of changes in DNA, which is confirmed by studies conducted in 2019, where scientists found that different species developed identical genes responsible for certain adaptive traits. Convergent evolution helps explain why organisms with similar functions can be found in different parts of the world, even though their evolutionary paths did not intersect. This process can also influence the systematics and classification of species, as similar traits can lead to confusion in determining their relationship. Evolutionary biologists use the concept of convergent evolution to analyze and interpret data on the relationships between species, as well as to predict which traits may develop in organisms encountering similar ecological conditions. For example, A study conducted in 2018 showed that in conditions of increasing temperature and climate change, some species may develop similar mechanisms of heat resistance, despite having evolved in different ecosystems. This underscores that convergent evolution not only explains the past, but also helps predict the future biological diversity in the face of global changes. As a result, the study of convergent evolution becomes an important tool for understanding the adaptations of organisms and their ability to survive in a constantly changing world. Scientific research shows that this process occurs not only in animals, but also in plants, where different species, under similar conditions, develop similar mechanisms for attracting pollinators or protecting against pests. In 2016, it was noted that some plants growing in deserts independently developed thorns for protection against herbivorous animals, which is a vivid example of convergent evolution in action. Convergent evolution of the eye in vertebrates and cephalopod mollusks serves as a striking example of how complex organs can develop independently in different evolutionary lineages. Vertebrate animals, such as mammals, birds, and reptiles, have evolved complex eyes with lenses, retinas, and other structures that enable them to focus on objects and distinguish colors. Meanwhile, cephalopod mollusks, such as octopuses and squids, have independently developed their own eyes, which, despite having similar functionality, have a completely different anatomy. For instance, an octopus's eyes are arranged so that the retina is on the inner side, not the outer side, as in vertebrates, making them more effective in deep-sea conditions. In the 18th century, researcher Georges-Louis Leclerc, Comte de Buffon, observed that the eyes of octopuses and vertebrates have similar functions but differ in structure, which led him to ponder the paths of evolution. Later, in 2008, a group of scientists led by Dr. Eric Hebert from the University of Maryland conducted a detailed study of these differences and concluded that convergent evolution is a result of similar ecological conditions in which both types of animals live. For example, visibility in water requires highly developed vision for hunting and avoiding predators. The eyes of both types of animals have functions that allow them to detect movements and distinguish contrasting colors. But the mechanisms underlying the operation of these organs differ. Octopuses lack tear glands that help keep the eyes clean, as in vertebrates, making them less dependent on the surrounding environment. The structure of the lens in octopuses is also more flexible, allowing them to quickly adapt to changes in lighting. These different adaptations are the result of millions of years of evolution in various conditions, but both lineages have achieved the same goal: effective vision. In 2009, scientists from the University of California conducted experiments showing that octopuses can not only distinguish colors, but also textures of objects, making them top-tier hunters in their environment. Thus, despite not sharing a common ancestor, the eyes of vertebrates and cephalopod mollusks demonstrate how evolution can lead to the same solutions for solving similar survival challenges. Echolocation is a remarkable phenomenon that has independently evolved in bats and cetaceans, demonstrating how complex sensory systems can adapt to similar ecological conditions. Bats like Pipistrellus pipistrellus began using echolocation more than 50 million years ago, enabling them to hunt insects in the dark by emitting ultrasonic signals and detecting the reflected waves, allowing them to accurately determine the size and distance of objects. Studies conducted in 2006 by scientists from the University of Texas showed that some species of bats can determine the size of their prey with an accuracy of 1 millimeter, which is an exceptional example of adaptation to nocturnal life. Meanwhile, cetaceans such as humpback whales and orcas began developing echolocation several million years ago, allowing them to effectively hunt fish in open waters. For instance, orcas can produce sounds at frequencies up to 120 kHz, which significantly exceeds the range of human hearing, and these sounds are used for both navigation and communication. Scientific research conducted in 2008 as part of projects studying the behavior of orcas in Alaskan waters showed that they can recognize individual sounds, which helps them find each other over long distances. Different groups of animals, such as bats and cetaceans, have been subject to similar ecological pressures, leading to the development of similar survival strategies. For example, A study conducted in 2009 by scientists from the University of California and the Oceanographic Institute demonstrated that both bats and dolphins use echolocation to locate their prey, despite living in completely different environments. This phenomenon of convergent evolution highlights how evolution can lead to similar solutions in response to similar ecological challenges, regardless of how distant the species may be. Bats and cetaceans have shown that complex sensory systems can emerge in response to the need for effective food search and spatial orientation, making them examples of evolutionary ingenuity. Research shows that despite differences in anatomy and habitat, both groups of animals develop unique mechanisms to achieve the same goal: survival in conditions of limited visibility. Bats can generate sound waves with frequencies up to 150 kHz, while cetaceans can use low-frequency sounds to transmit information over distances up to 1,000 kilometers. Convergent evolution of intelligence in primates and corvids is a remarkable manifestation of how high cognitive abilities could develop in completely different animal groups across various geological epochs. Primates, including humans, chimpanzees, and orangutans, have evolved over millions of years, starting with the appearance of the first primates around 60 million years ago. These creatures developed complex social structures that facilitated their intellectual development. For instance, chimpanzees, which share a common ancestor with humans, can use tools like sticks to extract termites, demonstrating a high level of understanding and adaptation to their environment. Meanwhile, corvids like crows and ravens have evolved independently, but also exhibited remarkable cognitive abilities. Research conducted in 2000 by Professor Christopher Phillips showed that crows can solve complex tasks using tools in sequence, indicating not only instinctual behavior, but also developed cognitive processes. These birds can remember human faces and distinguish between friends and enemies, further highlighting their intellectual capabilities. Convergent evolution in this case is evident in that different animal groups, independently of each other, arrived at similar solutions to complex problems such as food acquisition and social interactions. Data from research conducted in 2015 showed that the brain of crows and other corvids, despite being smaller in volume than that of primates, exhibits a high degree of neural density, which may explain their exceptional cognitive abilities. Neurobiological research conducted by Dr. Alan Kelly in 2018 revealed that crows and other corvids have a unique brain structure called the Nidopallium caudale, which is responsible for information processing and decision-making. This similar brain structure in completely different species serves as evidence that intelligence, as an evolutionary process, can take on various forms. Examples from life show how both primates and corvids use complex strategies to solve problems, which is confirmed by experiments studying their behavior. A study on crows conducted in 2009 at the University of Cambridge showed that these birds can predict the actions of others, indicating the presence of social intelligence. Thus, high cognitive abilities developed in different evolutionary contexts, but led to similar results in the form of complex behavior and highly developed social skills. This evolutionary parallel makes one ponder that intelligence may be a product not only of genetic factors but also of social interactions, as evidenced by numerous examples in nature where different animal groups, independently of each other, developed their unique mechanisms for achieving the same goal: survival and adaptation to constantly changing environmental conditions. As a result, studying these animals can lead to the conclusion that intelligence is not a privilege of one species, but a universal capacity that could develop in different forms over millions of years. Examples of corvids capable of complex manipulations and interactions, and primates building complex social structures, underscore that the evolution of intelligence is not a linear process, but a multitude of paths by which nature can achieve the same goals. Interestingly, crows, like primates, can even learn from each other, demonstrating the presence of a cultural aspect in their behavior. A study conducted in 2006 by Dr. Julia Kaplan showed that starlings can learn skills from each other, confirming the existence not only of individual, but also of collective intelligence. Technological singularity refers to the concept that the development of technologies and intelligence will reach a point where progress becomes uncontrollable and unpredictable. This state can be imagined as a moment when machines begin to surpass human intelligence in their development, leading to a rapid acceleration of societal changes. It is important to understand that this process is not simply a result of linear accumulation of knowledge. It resembles an avalanche that starts with a small stone but soon becomes a powerful flow, engulfing everything in its path. Throughout human history, there are parallels with other periods of rapid growth, such as the Industrial Revolution, when mechanization and automation began to transform production processes and societal structures. The pace of technological progress is not only increasing, but also becoming more complex. This creates an effect similar to a chain reaction, where one discovery or achievement becomes a catalyst for the next. As a result, each new technology requires increasingly complex technologies for its operation, creating a vicious circle where the speed of change accelerates. There is a belief that in such a situation, humanity will face a dilemma: either adapt to new conditions or fall behind. This raises important questions about how society will cope with the challenges and opportunities that this singularity will bring. For example, in the face of rapid technological development, there may be a need to rethink educational systems to prepare the next generation for a world where skills and knowledge become obsolete in just a few years. This may also lead to changes in social structures and labor relations, as many professions may disappear while new ones emerge. It is important to note that such progress is not always perceived unambiguously. On one hand, it opens new horizons and opportunities, but on the other hand, it raises ethical and philosophical questions about what it means to be human when machines begin to perform tasks previously considered exclusively human. As a result, public debates about the role of technologies and their impact on human life become increasingly relevant. Many experts raise the question of the need to introduce new norms and rules regulating the use of technologies to avoid negative consequences, such as loss of personal autonomy or threat to security. Modern societies are already facing the consequences of rapid technological development, including issues with privacy and data control. One example can be seen in the field of artificial intelligence, where algorithms analyzing personal data are becoming increasingly common. Such systems can significantly improve the quality of life, but at the same time raise concerns about manipulation and privacy violations. These contradictions highlight the need for a deep analysis not only of the technical aspects, but also of the social consequences that may arise as a result of rapid progress. It is important to remember that technologies themselves are neutral, and it is their use that determines whether they will serve the benefit of humanity or lead to its degradation. Ultimately, singularity becomes not only a technological but also a philosophical challenge, questioning established notions of progress, ethics, and responsibility. Reflections on these aspects become particularly relevant in light of current trends, where each new technological achievement opens new horizons but also carries risks that require careful study and analysis. Studying the evolution of human civilization reveals a striking exponential growth of technologies, which began with the simplest stone tools created around 2.5 million years ago. These tools, such as choppers and hand axes, allowed our ancestors to hunt and process food, significantly increasing their chances of survival. Around 150,000 years ago, Homo sapiens started using more complex tools like bows and arrows, enabling them to hunt larger animals and expand their territories. Around 13,000 years ago, the first agricultural communities emerged in the Near East, where people began to cultivate crops, leading to the establishment of permanent settlements and eventually cities. In the 4th millennium BCE, the first civilizations appeared in Mesopotamia, such as Sumer, where the first writing and mathematical systems were developed, allowing for the recording and transmission of knowledge. The Sumerians created cuneiform, which became the foundation for further development of written communication. Around 3,000 years ago, the Egyptians began constructing pyramids using advanced mathematical calculations and construction methods, demonstrating how technologies and knowledge accumulated and transformed into more complex forms. In ancient Greece in the 5th century BCE, philosophers and scientists like Archimedes and Pythagoras made significant contributions to mathematics and physics, laying the groundwork for future scientific achievements. In the Middle Ages, Around the 12th century, European scholars began to adopt Arabic knowledge, sparking the scientific revolution. In the 16th century, with the invention of the printing press by Johannes Gutenberg, a true revolution in information dissemination occurred, contributing to an educational boom and an increase in the number of literate people. In the 19th century, the Industrial Revolution transformed the concept of production when steam engines began to be used in factories, leading to mass production of goods. In the 20th century, humanity reached unprecedented heights. The Wright brothers' flight in 1903, the launch of the first satellite Sputnik in 1957, and the moon landing in 1969 became symbols of technological progress. With each discovery, the pace of technological growth accelerated, creating a snowball effect. If a similar process occurred with other intelligent species, they too could progress from simple tools to space exploration, adapting to their environment and developing their technologies as knowledge and experience accumulated. For example, if intelligent life developed on another planet, they might first use stone tools and then advance to more complex technologies like metallurgy and mechanics, ultimately leading to the creation of spaceships and interstellar travel. Scientific discoveries, such as the theories of relativity and quantum mechanics, open new horizons for understanding the world and can be used to develop technologies that we can barely imagine today. One such example is the possibility of creating artificial intelligence, which is already beginning to influence various aspects of our lives. Therefore, the exponential growth of technologies is not only a characteristic of human civilization, but also a potential common trait of all intelligent species striving to understand and change the world around them. In this dynamic of technologies, time, and knowledge, one thing remains constant. Progress requires not only time, but also courage to take risks and engage in experiments. The study of the concept of technological horizon represents an interesting direction in understanding the development of civilizations. The technological horizon is a conditional boundary beyond which technologies reach such a level of complexity and integration that their further development becomes invisible to an external observer. This phenomenon is observed in history when civilizations, having reached a certain technological peak, either transform into something unrecognizable or disappear due to self-destruction. For example, the Maya civilization, which achieved significant successes in astronomy and architecture, eventually faced a collapse that researchers attribute to ecological factors and internal conflicts. During the 9th to 10th centuries AD, the Maya built magnificent cities with large temples and complex irrigation systems. But by the 12th century, most of these cities were abandoned. Research by archaeologists like Dr. Todd Hansel shows that climate change and resource depletion were catalysts for this collapse. Another example is the Roman Empire, which, having reached its peak in the 1st century AD, also faced internal problems such as corruption and economic crisis, leading to its fall by the 5th century. Here, one can speak of the technological horizon when the empire ceased to be able to adequately respond to external challenges, including barbarian invasions. At the level of modern technologies, similar trends can be observed. For instance, the development of artificial intelligence already raises questions about the future. Benjamin Rosenblatt, a well-known IT researcher, points out that with increasing automation and digitization, jobs may disappear faster than we can adapt, creating a risk of social inequality and conflicts that could lead to serious consequences. It is also worth mentioning the concept of singularity, proposed by Viriglio Murphy in the early 2000s, when artificial intelligence will surpass human intelligence and become independent of it. This could radically change society, and perhaps we will find ourselves in a situation where we can no longer predict what will happen next. In this context, the technological horizon becomes not just an abstraction, but a real challenge that makes us think about how we can manage our technologies without losing control over ourselves. It is important to understand that at different stages of historical development of civilizations, technological horizons have appeared and disappeared, leaving behind only mysteries and lessons for future generations. For example, technologies of ancient Greeks, such as the steam engine created by Hero of Alexandria in the 1st century AD, did not develop further and remained in the shadow of more powerful technologies that came later. In this context, One may ask, what will happen when we reach the next technological horizon? How will this change our society, culture, and perception of the world? Understanding how deeply technologies penetrate every sphere of our life becomes critically important, for it is technologies that shape our future. The technological horizon does not just close a civilization off from the external world. It also creates internal barriers that can lead to conflicts and contradictions. For example, in the 20th century, we witnessed how nuclear technology, having reached its peak, not only provided the world with nuclear energy, but also created a threat of global destruction. There are other examples as well, such as the development of biotechnology, which raises ethical questions about genetic modification and cloning. Scientific and technological achievements open new horizons, but at the same time, they can become the cause of destructive consequences if we do not pay attention to how we use them. In the end, the concept of technological horizon becomes a key concept that requires our attention and analysis. Considering all these factors, it is important to understand that technologies are not neutral. They carry the potential for both progress and self-destruction. Each technological leap can become the beginning of a new era or the end of civilization if we are not prepared for the consequences. For instance, in the 21st century, the relationship between technologies and society has become more complex and multifaceted than ever before. The study of archaeological visibility of various materials and technologies is a crucial aspect of understanding cultural heritage and the historical development of humanity. Archaeological visibility refers to how and which materials, technologies, and artifacts are preserved in the ground, as well as how they can be discovered and interpreted by contemporary researchers. In this context, the key factor is the process of conservation. Some materials decompose faster than others, affecting their availability for future generations. For example, organic materials such as wood or textiles often undergo biological decomposition, especially in high humidity conditions. Meanwhile, inorganic materials like stone or ceramics can persist for thousands of years under favorable conditions. There is also a significant element of chance in archaeological discoveries. The location and conditions of excavation can significantly alter what is found. Some technologies, such as metalworking methods, may leave traces in the form of slag or fragments that can reveal the production process. But these traces do not always survive. Therefore, archaeological visibility is not passive. It is shaped by numerous factors, including human activity, climatic conditions, and even geological changes. Factors influencing archaeological visibility can be divided into natural and cultural. Natural factors such as erosion, floods, or earthquakes can destroy or conceal artifacts. Cultural factors include the use of technologies and materials, as well as changes in social structures and economy, which can make certain objects more or less visible in the archaeological context. For example, population migration or changes in technological processes can lead to the abandonment of some materials while others become more commonly used. Scientific methods such as radiocarbon dating and paleomagnetic analysis help archaeologists establish the chronology of finds and link them to specific cultural periods. These methods allow for the assessment of how well materials have been preserved and how they can be interpreted in the context of the time they were created. The level of archaeological visibility can vary depending on the region. In some places, finds may be abundant, while in others, they may be rare and fragmentary. Archaeological visibility is not limited to physical artifacts. It also includes information about the technologies used to create these artifacts and the social systems in which they existed. Understanding these aspects requires integrating data from various disciplines such as anthropology, history, and geology. This multidisciplinary approach allows for a more comprehensive understanding of how different cultures interacted with their environment and with each other. Scientific research shows that archaeological visibility can be linked to cultural preferences, which vary depending on time and place. For example, in some societies, certain materials could be considered sacred and therefore subjected to more careful conservation. This adds another layer of complexity to understanding archaeological heritage. Research also shows that different technologies could be widespread in different regions of the world depending on the availability of resources and cultural contacts. Thus, archaeological visibility is a complex and multifaceted concept that requires careful study of many factors affecting the preservation and availability of materials. This allows for a deeper understanding of how different cultures interacted with their environment, what technologies they used, and how they evolved over centuries. Important tools for archaeologists remain new methods of analysis and interpretation of finds, which help to illuminate previously unexplored aspects of human history. For example, the use of digital technologies such as three-dimensional modeling allows for the creation of more accurate reconstructions of ancient objects and sites, opening new horizons for research. Stone, as a building material, possesses unique properties that enable it to endure for millions of years. But its longevity is greatly dependent on geological conditions. For instance, limestone, which was extensively used in the construction of ancient Egyptian pyramids, can withstand centuries if it is in a stable environment, protected from erosion and destructive natural factors. The Pyramid of Khufu, built around 2,500 years before our era, still stands in Giza despite the passage of time. However, even stone structures can completely disappear if conditions become unfavorable. For example, in Mesopotamia, where clays and sandstones were used for constructing cities like Ur and Babylon, climate changes, including increased humidity, could lead to the destruction of buildings. As stone exposed to constant moisture becomes vulnerable to weathering and erosion. There are examples where entire cities built of stone have vanished under the influence of geological processes. For example, in Greece, ancient temples such as the Temple of Athena in Athens have endured centuries, but they too have been destroyed by earthquakes in the region. In the 18th century, a strong earthquake destroyed part of the temple, leaving only ruins. This demonstrates how even such robust materials as stone can be destroyed by the forces of nature. Structures built from less durable materials, such as sandstone or limestone, are more susceptible to destruction by atmospheric phenomena. In some cases, such as the ancient city of Petra in Jordan, climate changes and heavy rainfall have led to the erosion of building foundations, ultimately resulting in partial destruction. The study of such examples shows how crucial geological conditions are for the preservation of stone structures. In some instances, like Pompeii, which was frozen under a layer of volcanic ash in the 1st century of our era, materials have survived to this day due to unique circumstances that protected them from the environment. However, when conditions change, even stone that appears eternal becomes vulnerable. As a result, we can observe entire civilizations disappearing from the face of the earth, leaving only ruins that future archaeologists can study. For example, in the ancient city of Machu Picchu in Peru, located at an altitude of over 2,400 meters above sea level, many stone structures built by the Incas from granite and andesite, which are highly durable, have been damaged by erosion and vegetation, leading to the partial collapse of some buildings. Structures that have endured for centuries can be destroyed in just a few decades if natural conditions change, demonstrating that the longevity of stone is not an absolute category, but rather the result of a complex interaction between the material and its surroundings. In this context, it is important to consider that even the most robust structures can fall victim to time and natural disasters if they are not adequately protected. Metals, despite their reputation as strong and durable materials, actually have limited durability and geological timescales. For instance, iron, one of the most abundant metals on Earth, begins to corrode within a few decades if not protected from moisture and oxygen. The corrosion process of iron occurs through oxidation. When iron comes into contact with oxygen and water, rust forms, which is an oxide of iron. As a result, even well-hardened iron can disappear within a few thousand years, leaving only traces of its former shape. Steel, which is considered more durable due to the addition of carbon, is also subject to corrosion, and its longevity depends largely on the conditions of use. For example, the Golden Gate Bridge in San Francisco, built in 1937, requires constant maintenance and protection from corrosion because salty seawater and atmospheric conditions significantly accelerate the destruction of metallic structures. Light alloys, such as aluminum, although less prone to corrosion due to the formation of a protective oxide layer, can degrade over time, especially under the influence of alkaline or acidic environments. For instance, during the development of aluminum structures for the Challenger space shuttle in 1983, it was discovered that even minor damage to the protective layer could lead to catastrophic consequences. Copper, widely used in ancient times for creating coins and artifacts, is also subject to oxidation, forming a green patina that, while adding historical value to artifacts, also indicates the process of destruction. Alloys, such as bronze, although more resistant than pure iron, eventually lose their properties due to the influence of moisture and oxygen, as evidenced by the partial decomposition of bronze artifacts found on the bottoms of seas and lakes, which occurs as the conditions of the surrounding environment change. In essence, even the most durable metals, such as gold and platinum, which are almost immune to corrosion, cannot escape the effects of time and nature. Even they can be eroded and lost in the process of geological changes and erosion. For example, in 2008, researchers found gold ingots washed out of rock formations that were part of ancient mines, where they had remained in a state of rest for thousands of years but ultimately became victims of natural processes. Corrosion and destruction of metals become even more apparent in conditions where there is constant exposure to water and oxygen, as occurs in coastal zones or flooded areas. Ultimately, in the context of geological timescales, metals that seem eternal to us are actually temporary and subject to destruction. And in the process of their degradation, not only is their physical form lost, but also the cultural heritage they represent. Organic materials such as wood, fabrics, and paper face a significant challenge in terms of preservation, as they decompose within a few years or centuries, leaving behind only modest traces for future researchers. For instance, wood, exposed to moisture and microorganisms, can rot within a few decades. In tropical forests, where humidity reaches nearly 100%, wood can decompose in just 20 to 30 years. This occurs due to the activity of fungi, bacteria, and insects that actively use wood as a food source. Researchers from the University of California, Berkeley, conducted a study in 2000 that showed that under high humidity conditions, the decomposition of wood can increase by 2 to 3 times. Fabrics, especially natural ones like linen or cotton, also have a short lifespan. Under conditions where fabrics are exposed to light, moisture, and air, they can deteriorate within 10 to 15 years. For example, finds of ancient Egyptian fabrics, which have survived in tombs, owe much to the dry climate and the antiseptic properties of resins used in mummification. However, even these fabrics are often found in fragments and require significant restoration to restore their original appearance. Paper is another material that decomposes quickly. The 18th century witnessed mass paper production, but many of these documents became unreadable within 100 years. Studies conducted in Japan in 2000 showed that paper documents stored in high humidity conditions lose their properties twice as fast as in dry conditions. This is due to the decomposition of cellulose, which makes up paper, leading to the loss of information and history recorded on it. Additionally, the use of acidic paper, popular in the 20th century, accelerates decomposition, as the acid destroys the fibers and makes the paper brittle. Human intervention also plays a significant role in the decomposition of organic materials. For example, improper storage of artifacts such as fabrics and paper in conditions with high temperature and humidity leads to their catastrophic destruction. Even in museums, where certain storage conditions are maintained, there are occasional losses of valuable collections when staff do not know how to properly handle and store such materials. As a result, organic materials that could provide insights into the past often disappear, leaving only mysteries for future researchers. For example, in 2005, archaeologists in Italy discovered remnants of an ancient Roman textile factory, but only a small part of the fabric survived due to unique burial conditions. Without proper protection, organic materials that could greatly enrich our understanding of history are disappearing each year, posing serious problems for historians and archaeologists. The technological signature of civilization is a unique set of characteristic features that reflect the level of societal development in various domains such as production, construction, transportation, and communications. This concept is linked to how technologies influence social structures, the economy, and culture over time. For instance, during antiquity, technologies had a significant impact on architecture and urban planning. The Greeks and Romans employed specific construction methods that allowed them to build magnificent temples and aqueducts. In ancient Rome, for example, complex water supply systems were developed, including aqueducts that delivered water over distances of up to 100 kilometers, significantly altering the lives of city dwellers. The technological signature also encompasses production methods that determined the economic power of states. In the Middle Ages in Europe, the spread of mills and forges became the foundation for the transition to a more complex economy based on crafts and commodity production, which in turn paved the way for subsequent industrial revolutions. The 18th century was the golden age of technology, when the first industrial revolution began, and inventions such as the steam engine fundamentally changed production processes. This led to a mass shift from an agrarian society to an industrial one, reflected in the growth of cities and changes in social structure. It is important to note that each technological epoch leaves its mark on culture and daily life, shaping habits and the way people live. For example, the invention of the printing press by Johannes Gutenberg in the mid-15th century not only revolutionized the dissemination of knowledge, but also ushered in the Age of Enlightenment, which fundamentally changed the way Europeans thought. The technological signature can also serve as an indicator of the level of education and scientific achievements of a society. In ancient China, for instance, inventions such as the compass and gunpowder not only advanced military affairs, but also changed trade routes and navigation. The more complex the technologies developed in a society, the greater its ability to adapt to changes and challenges. Artifacts such as tools, weapons, and machines become not just objects, but also witnesses to historical processes, reflecting the level of knowledge and skills of people of their time. Thus, in the 19th century, the advent of electricity and the telegraph opened new horizons for communication, leading to the emergence of a globalized world. The technological signature of civilization is formed under the influence of numerous factors, including political, economic, and cultural conditions, and allows researchers to better understand how societies developed and what challenges they overcame. Each technological advancement becomes a stepping stone to new achievements, opening doors to further research and innovations. In this context, it is important to note that not only the technologies themselves, but also the ways they are integrated into society are significant. Social movements such as the Luddites in the early 19th century demonstrate how technological changes can provoke resistance and conflicts, which also reflect the state of civilization in a given period. The technological signature becomes a kind of mirror in which not only achievements but also contradictions of human history are reflected, allowing for a deeper understanding of how technologies have shaped our lives over centuries. Radioactive isotopes serve as unique markers of human technological activity, capable of persisting in geological layers for millions and even billions of years. For instance, carbon-14, formed in the atmosphere through the interaction of cosmic rays with nitrogen atoms, is actively used for radiocarbon dating. This method allows scientists to determine the age of organic materials, such as wood or textiles, up to approximately 50,000 years ago. However, longer-lived isotopes like uranium-238 and thorium-232 can indicate earlier technological processes, as their half-lives span millions of years. Uranium, for example, is used in nuclear energy, and its remnants can remain in geological layers as traces of human activity. Uranium-238 decays into a series of daughter isotopes, such as radon-222, which can accumulate in groundwater and soils, serving as evidence of uranium mines or other technologies associated with its extraction. In particular, the presence of uranium isotopes in geological layers dating back more than 2 billion years can indicate natural radioactive decay processes, making them valuable tools for studying the history of Earth and its geological processes. These isotopes are not only markers for geologists, but also crucial for archaeologists, as they can point to the locations of ancient civilizations that utilized radioactive materials in their technologies. For example, in Egypt, archaeologists have discovered traces of radioactive minerals used in rituals and manufacturing. In the 20th century, With the development of nuclear energy, radioactive isotopes became more widespread in the environment, and their traces can be found even in remote corners of the planet. This allows scientists to track the impact of human activity on ecosystems and climate. Scientific research, such as the work of Dr. Edward K. Messer's group, shows that the level of strontium-90 formed as a result of nuclear tests can serve as an indicator of historical periods when nuclear tests were conducted, beginning in the mid-20th century. This isotope can persist in soil and sedimentary deposits, allowing researchers to examine not only the ecological consequences of nuclear tests, but also their social impact on the population. Consequently, radioactive isotopes become important tools for studying both ancient and modern technologies and their impact on the environment. They provide a window into the past, enabling us to understand how civilizations developed and what traces they left on the planet. Each isotope preserved in geological layers serves as a kind of witness, capable of revealing technological progress and its consequences for our planet. For example, the discovery of plutonium isotopes in deposits can indicate the existence of nuclear reactors or nuclear weapons, underscoring the importance of these studies for understanding not only history, but also the future of humanity. The study of radioactive isotopes is becoming a key element in the comprehensive analysis of the impact of technologies on nature and society. Synthetic materials and polymers, which emerged in the early 20th century, are already forming unique geological layers that could persist for millions of years. For example, plastic was first created in 1917 when chemist Leo Baekeland synthesized bakelite, the first fully synthetic polymer. Since then, the production of plastic products has rapidly increased, and by 2015, the annual production volume of plastic reached over 300 million tons. These materials, due to their resistance to decomposition, can exist in the environment for hundreds and even thousands of years. For instance, polypropylene, one of the most common polymers, takes around 200 years to decompose in nature. As a result of their accumulation in landfills and oceans, new geological layers are formed, which can be studied by future geologists. For example, in 2019, researchers from the University of Leicester found plastic particles in marine sediments dating back to the 20th century, indicating how synthetic materials can become evidence of our era. Polymers, such as polyethylene and polyvinyl chloride, have complex chemical structures that make them resistant to physical and chemical factors. These qualities enable them to persist in geological layers, forming new horizons that can tell the story of human life and their technologies. Scientific research shows that synthetic fibers such as nylon and acrylic can also become part of future geological formations, creating a sort of plastic layers in stratigraphy. Geologists studying these layers can not only determine the age and composition of these materials, but also understand how human activity has impacted ecosystems. Synthetic materials entering the soil can alter its chemical composition, which will also be recorded in geological records. Additionally, microplastics, found in the most remote corners of the planet, including Antarctica, clearly demonstrate the extent to which human civilization's traces have spread. Studies show that in some places, the concentration of microplastics reaches several thousand particles per cubic meter. These findings confirm that plastic not only alters the external environment, but also becomes part of geological processes. Consequently, polymers and synthetic materials are forming not only contemporary environmental problems, but also unique geological layers that will serve as evidence of technological civilization. In 2020, scientists from Texas University conducted a study analyzing deposits containing microplastics and concluded that such layers can be clearly distinguished in stratigraphy as evidence of the industrial era. Synthetic materials can become not only indicators of pollution, but also important elements in future geological research that will tell the story of our time. Ultimately, these geological layers could be the key to understanding how humanity interacted with nature and what traces it left behind. Major landscape and ecosystem changes caused by ancient civilizations have left significant traces in the geological record. For instance, in Mesopotamia, where the Sumerians began practicing agriculture more than 6,000 years ago, they created an extensive network of irrigation canals. These canals not only increased agricultural production, but also altered the hydrological conditions of the region. Studies show that changes in the courses of the Tigris and Euphrates rivers led to significant changes in the ecosystem, including increased soil salinity and the disappearance of certain fish species. Similarly, in Central America, the Maya created complex terrace farming systems that altered the landscapes of mountainous regions. These terraces helped retain water and prevent erosion, but their construction also led to significant changes in the local flora and fauna. For example, during the classical Maya period, approximately from the 2nd to the 9th centuries AD, studies show that forests were cleared to create agricultural land, which in turn led to a decrease in biodiversity. In India, during the Mauryan Empire around the 3rd century BC, the construction of drainage and water supply systems altered coastal ecosystems, as evidenced by archaeological findings in cities such as Pataliputra. These landscape changes also affected animal migration. Paleontological studies indicate that the disappearance of certain species, such as the Indian rhinoceros, coincided with the growth of the human population and changes in ecosystems caused by agriculture. In Europe, the Romans, starting from the 1st century BC, actively altered the landscape by building roads and aqueducts, which also left their marks in the geological record. For example, the aqueduct Aqua Claudia, built by Emperor Claudius in the 1st century AD, altered natural water flows and changed the ecosystems in the area around Rome. These changes can be found in soil layers where remnants of building materials are found, as well as in changes in the composition of microorganisms, which indicate changes in living conditions. In China, the Han Dynasty, starting from the 3rd century BC, also made a significant contribution to landscape changes. The creation of canal and dam systems altered rivers, as evidenced by geological findings showing changes in the composition of sedimentary rocks. These landscape changes not only affected agriculture, but also climate conditions, which can be traced by changes in the chemical composition of lakes and rivers. For example, in Lake Tianchi in Mongolia, sediments were found that indicate fluctuations in water levels related to the activities of ancient civilizations. These ecosystem changes can also be found in other regions, such as Peru, where the Incas modified the landscape by creating terraces on the slopes of the Andes, as evidenced by geological studies showing changes in soil structure and plant composition. As a result, these facts demonstrate how the activities of ancient civilizations led to large-scale changes in ecosystems and landscapes, which can now be studied through the geological record. Scientific skepticism is a crucial concept that helps critically evaluate various hypotheses and theories, especially in areas dealing with unusual phenomena. This approach is based on the principle that any assertion should be subjected to rigorous testing before being accepted as true. Scientific skepticism requires researchers not only to believe in new ideas, but also to conduct a thorough analysis of available data, thus avoiding errors and unfounded assumptions. For instance, in the history of science, one can see how skepticism played a key role in debunking myths. In the 18th century, during the Enlightenment, many scientists began to question traditional views of the world. This led to the replacement of the geocentric model of the universe with the heliocentric model proposed by Nicholas Copernicus. He demonstrated that the Earth revolves around the Sun, not the other way around. This transition became possible due to critical analysis and doubt in established truths. In the 19th century, with the development of biology, Charles Darwin proposed the theory of natural selection, which also faced critical scrutiny from his contemporaries. Many did not believe in the possibility of evolution, but science, based on observations and factual data, eventually confirmed Darwin's correctness. Scientific skepticism not only helps to eliminate false ideas, but also contributes to a deeper understanding of the surrounding world. For example, in the 20th century, during the search for extraterrestrial life, many hypotheses about the existence of aliens were subjected to thorough testing. The SETI project, which started in the 1960s, uses scientific skepticism to analyze radio signals from space and distinguish random noise from potential signals from extraterrestrial civilizations. It is important to note that scientific skepticism does not contradict openness to new ideas. On the contrary, it supports them if they have scientific foundations. This means that each new discovery must be verifiable and reproducible. For example, in the 1990s, a group of researchers claimed the possibility of creating cold fusion, a process that could produce vast amounts of energy at room temperature. This claim sparked widespread interest but also significant skepticism, as it could not be reproduced under controlled conditions. As a result, despite initial hopes, this hypothesis was largely refuted. Scientific skepticism serves as a vital tool in combating pseudoscience and distinguishing facts from fiction. In today's society, where access to information has never been easier, it is particularly important to use critical thinking when evaluating new ideas. For instance, in medicine, when new drugs or treatment methods appear on the market, scientific skepticism helps patients and doctors make informed decisions based on verified data, not rumors or advertising. This also demonstrates that even the most outstanding ideas can be subjected to doubt and testing, ultimately leading to progress. Scientific skepticism forms the basis for the scientific method, which requires reproducibility and objectivity in research. This approach is especially relevant in an era when information spreads at an unprecedented speed, making it increasingly difficult to distinguish truth from lies. The proliferation of unfounded theories and myths on the internet requires us to adopt a more responsible attitude toward information. Scientific skepticism helps us stay on the right path, focusing on facts and evidence rather than emotional assertions and rumors. This approach becomes particularly important in fields such as climatology, where debates about global warming require researchers and society to conduct a thorough analysis of data. In conclusion, scientific skepticism is not just a tool, but a necessary philosophy that helps us move forward in understanding complex issues that humanity faces. The application of this approach in various scientific disciplines contributes not only to the development of science, but also to the improvement of the quality of life. The principle of Occam's razor is a methodological approach that states that among multiple possible explanations, the simplest one should be preferred, provided it does not require additional assumptions. This principle was formulated by the English philosopher and Franciscan William of Occam in the 14th century. Occam argued that one should not multiply entities without necessity, which in modern terms means, if two explanations equally well explain the data, the simplest one is preferable. This approach is not limited to philosophy, but is also applied in various scientific disciplines, including medicine, physics, and sociology. For instance, in medicine, when a doctor encounters a patient's symptoms, they must consider various diagnoses. If one diagnosis requires complex and expensive tests, while another can be confirmed by a simple analysis, then according to Occam's razor, the simpler option should be chosen. In the history of science, this principle is often illustrated by the example of Nicholas Copernicus's heliocentric theory. Copernicus proposed a simple model in which the Earth orbits the Sun, explaining astronomical phenomena with fewer efforts than the geocentric model of Ptolemy, which required many additional circles and epicycles to explain planetary motion. In physics, for example, Albert Einstein applied this principle when developing his theory of relativity, striving for simplicity and clarity in explaining gravity and motion. In sociology, when investigating causal relationships in social phenomena, simpler theories often prove more effective in explaining complex social processes. The principle of Occam's razor became the foundation of the scientific method because it requires researchers to avoid unnecessary complexity in explanations, allowing them to focus on the most probable and practical solutions. In this context, it is important to understand that simplicity does not always mean primitiveness, but rather clarity and accessibility. For example, in biology, when studying complex animal behavior, scientists often apply this principle, choosing the most logical and simple explanations for observed actions. The application of Occam's razor in science implies a critical evaluation of existing theories and a constant search for simpler and more effective solutions. This approach helps scientists avoid the trap of excessive complexity, where a theory becomes so convoluted that it loses its predictive power and practical usefulness. The principle is also reflected in many scientific research studies, such as experiments investigating natural phenomena, where researchers strive to exclude unnecessary variables. For instance, In experiments studying risk-taking behavior in people, scientists may use simple behavioral models to explain complex psychological phenomena. Thus, Occam's razor serves as an important tool for scientists, allowing them to focus on the key aspects of their research, avoiding excessive theorization and complication. It is worth noting that the application of this principle is not a dogma, but rather a recommendation that requires attention and critical thinking. Occam's razor helps not only in scientific research, but also in everyday life, where we constantly face the choice between simplicity and complexity. For example, when choosing between two products on a supermarket shelf, we often prefer simpler and more understandable compositions, which can lead to a healthier lifestyle. This principle is universal and is applied in various fields, from business management to personal decision-making. In the end, the principle of Occam's razor emphasizes that in a world full of uncertainty and complexity, simplicity remains a powerful tool for achieving clarity and understanding. The development and application of scientific theories require constant analysis, and the principle of Occam pushes scientists to seek the best solutions, minimizing assumptions and focusing on the most probable and effective explanations. The necessity of extraordinary evidence for extraordinary claims becomes particularly relevant when discussing hypotheses about ancient prehistoric civilizations. To prove the existence of such civilizations, which are said to have possessed highly advanced technologies or cultures, compelling and irrefutable evidence is required, as history does not tolerate empty fantasies. For instance, the hypothesis about an ancient civilization that used technologies surpassing modern levels should be based on real artifacts, not speculations. In this context, it is worth mentioning recently discovered artifacts in Mesopotamia, dating back to the 3rd millennium BCE, which show that the Sumerians already used a writing system, tools, and complex irrigation systems. This confirms that even in prehistoric times there existed highly developed societies. But to assert the existence of civilizations similar to those described in myths and legends, more than just finds is needed. Scientific methods, such as radiocarbon dating, help determine the age of artifacts. But currently, there is no single object that could convincingly prove the hypothesis of global prehistoric civilizations with technologies comparable to modern ones. For example, when archaeologists discovered in Turkey in 2003, on the site of Göbekli Tepe stone structures older than 12,000 years, this discovery shocked the world. But it did not confirm the existence of an advanced civilization. Instead, it indicated that people at that time could create complex structures, but it did not necessarily mean they had advanced technologies. Scientists like Klaus Schmidt, who led the excavations at this site, were able to establish that these structures were used for rituals, not for everyday life, which once again emphasizes that even remarkable finds require careful interpretation. For claims about ancient civilizations, not only artifacts are needed, but also a clear connection between them and the supposed technologies. For instance, to speak about high technologies, it is necessary not only to find tools, but also traces of their use, such as metal residues, building materials, or even written sources that could confirm the level of knowledge and skills of people at that time. Comparison with modern civilizations is also necessary to understand how technologies developed. The 18th century marked the beginning of the Industrial Revolution, and it was then that humanity made a leap in the use of machines. If we were witnesses to something similar in prehistoric times, we would need not only finds, but also written evidence that such technologies were used. Currently, it is difficult to find any evidence that ancient civilizations possessed anything that could compete with the achievements of the last 300 years. In archaeology, there is a rule that any statement, especially if it goes beyond the ordinary, should be supported by convincing evidence. For example, in the 19th century, many researchers, such as Henry Morgan, proposed theories about the development of civilizations, but without sufficient archaeological finds, their ideas remained just theories. In our time, when technologies are developing at an incredible speed, it is important to understand that any hypotheses about ancient civilizations should meet strict scientific criteria. An example is the discovery in the 21st century in India, where archaeologists found traces of an ancient urban layout. But the lack of material evidence of high-level technologies leaves many questions. Scientists like Richard Bagdanjan assert that without a clear evidence base, any claims about ancient highly developed civilizations are no more than speculations. This situation requires researchers to approach the interpretation of finds and their significance for understanding human history with greater care. Each new artifact, each find should undergo strict verification and analysis to separate real achievements from myths and legends. As a result, to confirm extraordinary claims about ancient civilizations, extraordinary evidence is needed, which currently presents a challenge for historians and archaeologists. Modern scientific methods, including the analysis of data from various disciplines, have significantly altered approaches to the search for traces of ancient civilizations. One of the key aspects is the interdisciplinary approach, which combines archaeology, anthropology, geology, and even genetics. For instance, through collaboration with geneticists, archaeologists can assess DNA samples obtained from ancient remains, which allows them to establish kinship ties between different cultures and even determine the routes of human migration. This helps to reconstruct a more comprehensive picture of the interaction between civilizations over centuries. Using isotope analysis, researchers can learn what foods ancient peoples consumed and even which lands they cultivated, providing insight not only into their way of life, but also into the climatic conditions in which they lived. The use of satellite technologies allows researchers to identify landscape changes that may have occurred due to human activity, such as deforestation or irrigation systems, opening new horizons for the study of ancient agricultural practices. Scientific approaches to dating artifacts, such as radiocarbon dating, enable precise determination of the age of finds, which helps establish the chronology of events and the relationships between cultures. Comparative analysis of artifacts from different regions also aids in identifying trade routes and cultural exchanges. Scientific research not only uncovers new artifacts, but also allows for a re-evaluation of already known ones, changing our understanding of how ancient civilizations interacted with each other. For example, the discovery of several identical items in different parts of the world may indicate active exchange between these regions. The development of computer modeling allows for the creation of reconstructions of ancient cities and their infrastructure, enabling the study of urban planning and social structure. An important aspect is also the use of specialized databases containing data on findings from around the world, which optimizes the process of searching and comparing information. These methods help not only in the discovery of new artifacts, but also in a deeper understanding of the context in which they were used. For example, the study of rituals and customs of ancient peoples through their material remains can shed light on social structures and religious beliefs. All these aspects emphasize the importance of using modern scientific methods for the study of ancient civilizations, allowing researchers to delve into the past with a new perspective. The application of new technologies and methods significantly increases the effectiveness of research, providing access to information that was previously hidden. This allows not only for the discovery of new artifacts, but also for the re-evaluation of old theories about ancient cultures. The use of data from various sources and the application of analytical methods create a more complete picture of historical processes. Thus, modern science becomes an important tool in the study of human history, allowing us to view ancient civilizations from new angles and deepen our understanding of their life and culture. For example, in recent years, the use of cutting-edge technologies has led to the discovery of previously unknown settlements, which has fundamentally changed our understanding of the settlement of certain territories. Satellite mapping and LiDAR scanning technologies have opened new horizons in archaeology, helping to uncover hidden structures beneath the Earth's surface that indicate artificial origins. Using satellite images, researchers can identify changes in vegetation and topography that may indicate the presence of ancient structures. For example, in 2018, a team of archaeologists led by Dr. Alberto Mayer of the University of Florida used satellite data to search for abandoned cities of the Maya civilization in the jungles of Guatemala. As a result, they discovered more than 50,000 previously unknown structures, including pyramids and aqueducts, hidden under dense trees. LiDAR, which stands for laser scanning in the far infrared range, allows for the creation of highly accurate three-dimensional models of landscapes, penetrating through foliage and lifting the veil of mystery from lost civilizations. In 2017 in Cambodia, LiDAR technology was used to discover the lost capital of the Khmer Empire hidden under a layer of vegetation. Researchers led by Dr. Tony Wilson analysed the data and determined that the city's area was more than 14 square kilometres, twice as large as previously thought. This discovery not only changed the perception of the scale of the Khmer civilization, but also demonstrated how the use of modern technologies can revolutionise the approach to historical research. LiDAR technologies work by sending laser pulses to the ground and measuring the time it takes for them to return, allowing for the creation of detailed maps of the topography. Thus, in 2019 in Mexico, remnants of ancient aqueducts and roads that connected different settlements of the ancient Maya were discovered, indicating a high degree of organization in their society. Satellite technologies, such as GPS systems, also help in accurately pinpointing the discovered objects to geographical coordinates, simplifying further research and excavations. Scientific research conducted in 2020 on the territory of the ancient Nabatean kingdom in Jordan used both satellite mapping and LiDAR to uncover hidden channels along which ancient traders transported goods. These channels, in turn, confirmed the existence of a complex transportation network that ensured the prosperity of the region. The application of such technologies has become a true revolution in archaeology, allowing not only the discovery of new objects, but also the reinterpretation of already known ones. In 2021 in Peru, researchers from the University of Lima used LiDAR to map the territory around the famous Nazca lines, which allowed them to uncover additional geoglyphs that had previously gone unnoticed. Thus, modern technologies not only help in finding artifacts, but also create a new paradigm in the study of ancient civilizations, opening doors to further research and unexpected discoveries. LiDAR data provide the opportunity to analyze structures in detail, such as walls, roads, and even channels, giving archaeologists new tools for understanding the social and economic structures of ancient societies. Methods of mass spectrometry and isotopic analysis are powerful tools that enable archaeologists and scientists to determine the age and origin of materials with remarkable precision. Mass spectrometry, developed in the early 20th century, allows for the separation and measurement of molecular masses, aiding in the identification of chemical compositions. For instance, in 2012, researchers from the University of California, Berkeley, used mass spectrometry to analyze carbon samples from ancient organic remains, enabling them to date artifacts back to 10,000 years ago. This method provided accurate measurements, allowing for the determination of the content of carbon isotopes and carbon-14, which is crucial for radiocarbon dating. Isotopic analysis, in turn, allows for the study of the ratios of isotopes of elements such as oxygen, carbon, and nitrogen to determine the geographical and cultural origins of materials. For example, in 2018, a group of scientists from the University of Leicester conducted a study of oxygen isotopes in the bones of ancient people found in Britain, enabling them to compare samples from different regions of Europe and establish migration routes. Furthermore, unusual isotope ratios can indicate technological processing of materials. In 2016, researchers in Japan studied the isotopic composition of ceramics, revealing the use of additives during firing, which helped determine their origin and manufacturing processes. These findings not only confirmed facts about ancient technologies, but also opened new horizons for understanding cultural exchanges between civilizations. Mass spectrometry and isotopic analysis have become an integral part of modern archaeological research, allowing for the illumination of previously unknown aspects of human history through precise scientific methods. For example, in 2020, in Norway, the presence of isotopes characteristic of southern European regions was detected in Scandinavian artifacts, indicating possible trade connections between these regions. Such discoveries underscore the importance of applying advanced technologies in archaeology, which not only complement traditional methods, but also open new avenues for the study of ancient societies. Computer modeling and simulations have become essential tools for archaeologists and ecologists seeking to reconstruct ancient ecosystems and climatic conditions. For instance, in 2018, a research group led by Dr. James Clark from the University of California used a climate model to recreate conditions in the region of Mesopotamia around 6,000 years ago. The modeling showed that the climate was significantly wetter than previously thought, which facilitated the development of agriculture and, consequently, complex civilizations such as Sumer. Such simulations help understand how temperature and precipitation changes could have influenced human migration and adaptation to their environment. In 2020, a team from Ohio University applied similar methods to analyze changes in ecosystems in ancient Egypt, providing insights into how the Nile's level varied over centuries and its impact on agriculture. They combined data from ancient sources like hieroglyphs and funerary texts with modern climate models. The modeling indicated that abrupt climatic changes between the 13th and 10th centuries BC could have led to the decline of the Hittite civilization, supporting hypotheses about the link between climate and social changes. In 2001, researchers from the German Climate Research Institute used computer modeling to analyze ecosystems in Central America to determine how climate changes affected the Maya civilization. The models showed that prolonged droughts in the 8th and 9th centuries AD led to reduced agricultural production and population migration. A key aspect of such research is the ability to predict how future climatic conditions may impact contemporary ecosystems and civilizations. For example, in 2020, a group of scientists from the University of Cambridge presented results showing how global warming could alter ecosystems in Europe over the next century, with critical implications for food security and biodiversity. These methods not only allow us to look into the past, but also provide insights into how to adapt to future changes, which is crucial for humanity. An important part of such research involves using data from various sources, including paleoclimatic studies, ice core analysis, and sedimentary deposits, which help create a more comprehensive picture of ancient climatic conditions. For example, analysis of ice cores from Greenland in 2003 showed that temperatures in the Arctic during certain historical periods were 8 degrees higher than current values, which could have significantly influenced human and animal migration. Thus, computer simulations are not just tools for studying the past, but also a vital step in understanding how changing climate can impact our future. Research shows that the use of advanced technologies in combination with traditional archaeological methods allows for a more detailed and accurate analysis of complex interrelationships between climate, ecosystems, and human activity. Humanity has become one of the largest factors determining Earth's ecosystems. Changes in climate caused by human activity lead to significant consequences, including global warming, resource depletion, and species extinction. As a result of this impact, the planet is experiencing ecological changes that would not be possible without human intervention. For example, deforestation in the Amazon since the beginning of the 20th century has led to the loss of millions of hectares of tropical forests, which not only reduces biodiversity, but also disrupts the planet's carbon balance. According to estimates, about 18% of the carbon released into the atmosphere comes from the destruction of forests. Additionally, sea levels are rising due to the melting of glaciers, threatening coastal ecosystems and populations. The world's oceans absorb approximately 30% of carbon dioxide, leading to their acidification and affecting marine organisms, including corals, which suffer from increased water temperature. Leading scientists, such as Christopher Burke and Jane Goodall, emphasize that anthropogenic factors, such as agriculture and industry, alter natural ecosystems, affecting natural selection and evolution. Agriculture based on intensive use of chemical fertilizers and pesticides leads to soil and water pollution, negatively impacting human and animal health. As the population of Earth continues to grow, reaching 8 billion people, demand for resources such as water and energy increases. This puts pressure on natural resources and ecosystems, accelerating ecological changes. In some regions, such as North Africa, water scarcity is already a problem, leading to conflicts and population migration. Research shows that more than 6 billion people face water scarcity, making this issue one of the most pressing in the modern world. It is expected that by the middle of the century, more than half of the Earth's population will live in conditions of water stress. In this context, it is important to consider that anthropogenic changes affect not only nature, but also social structures. The number of climate refugees, according to the United Nations Migration Organization, could reach hundreds of millions, creating new challenges for countries accepting migrants. Scientists also emphasize the need for a transition to sustainable production and consumption methods to mitigate the impact on the environment. For example, transitioning to renewable energy sources such as solar and wind power can reduce greenhouse gas emissions. Meanwhile, cities like Copenhagen demonstrate how green technologies and sustainable infrastructure can be integrated into urban planning, improving the quality of life and reducing the burden on the environment. An important aspect is also education and public awareness of environmental issues, which can promote more responsible resource use and protection of the environment. According to UNESCO, environmental education programs are already being implemented in many countries, raising the level of awareness among youth about the importance of sustainable development. In this context, it is important to remember that the current state of the planet is the result of centuries of human activity, which requires a rethinking of our relationship with nature. It is becoming increasingly clear that without changes in our approach to ecology, the consequences could be catastrophic. It is also important to note that there are technologies that allow for the minimization of negative environmental impact, such as waste recycling methods and the introduction of environmentally friendly technologies in industry. Plastic layers in sedimentary deposits have become a unique geological marker that will persist on Earth for millions of years after the disappearance of human civilization. Estimates suggest that since the mid-20th century, over 900 million tons of plastic have been produced, with a significant portion entering oceans, rivers, and soils. This material, which does not decompose naturally, forms mysterious plastic horizons in geological layers. Studies have shown that in places like the Mariana Trench in the Pacific Ocean, over 30 different types of plastic waste, including bottles, bags, and even microplastics that have already entered the food chain of marine organisms, have been found. Researchers from the University of California, San Diego, analyzed sediments in bays and found that the level of microplastics in some samples exceeded 80%. As a result, plastic has become an integral part of geological records, similar to coal or limestone, which were also formed millions of years ago. Scientists predict that in a few million years, future geologists will be able to study plastic as evidence of our civilization, much like we study dinosaur fossils. According to estimates, the plastic layer will be visible in geological deposits as a marker of the Anthropocene, a geological epoch in which humans played a dominant role. This will serve as a significant indicator that there was a period when plastic became one of the main materials used in everyday life. Additionally, plastic items such as toys, packaging, and construction materials will leave a distinct mark in the geological record. This discovery underscores not only the impact of humans on nature, but also how our actions will be documented over millions of years. Scientists like Dr. Jennifer Love from the Scripps Institution of Oceanography predict that this layer will serve as a kind of memory of our civilization for future researchers. Studies have shown that in deposits containing plastic, not only plastic particles, but also chemical compounds used in their production, such as bisphenol A and phthalates, can be found, adding another layer of complexity to understanding our impact on the environment. Thus, the plastic layer in sediments becomes a kind of marker that will be studied by future generations as evidence of the existence and lifestyle of humans in the 20th and 21st centuries. In some regions, such as polar areas, plastic can become trapped in permafrost layers, further aiding its preservation. In tropical regions, it may decompose slowly, but still form microplastics that will be present in ecosystems for a long time. Plastic horizons will be formed in geological deposits, creating a new type of stratigraphy that clearly marks the time when humanity left its mark on the planet. For example, in some places like the California coast, layers with different types of plastic dating back to the early 2000s have already been discovered. allowing researchers to precisely pinpoint the appearance of various materials. Studies show that in the future, as Earth undergoes changes, these layers will serve as indicators not only for scientists but for the entire world, helping to understand how human activity has affected the planet, leaving behind such a distinct and non-decomposable trace. The atmosphere of Earth has undergone significant changes over the past few centuries, serving as a crucial indicator of the impact of human activity on the planet. For instance, research conducted using ice cores extracted from Antarctica and Greenland has shown that the air bubbles trapped in the ice contain information about the atmosphere's composition, dating back up to 100,000 years. These bubbles can reveal the levels of carbon dioxide and methane, which have reached record highs in the past 30 years. Data from the ice cores indicate that the level of carbon dioxide in the atmosphere in the 21st century exceeds 380 parts per million, which is 30% higher than in the pre-industrial era. A study conducted in 2006 by a group of scientists led by doctors Lorenzo Serafini and Christian Schmidt demonstrated that methane levels have also increased sharply, reaching levels not seen in the past 800,000 years. These changes in the atmosphere are a direct consequence of the increase in greenhouse gas emissions, primarily due to the burning of fossil fuels such as coal, oil, and gas. In 2000, scientists from the Massachusetts Institute of Technology found that electronics and transportation are now the main sources of carbon emissions. According to the World Meteorological Organization, the concentration of carbon dioxide continues to rise each year, which could lead to significant climate changes in the future. The impact of humanity on the atmosphere will be recorded in geological layers, and future researchers analyzing these samples will be able to see how technological civilization has left its mark on the planet. For example, a study published in the journal Nature in 2018 showed that air bubbles trapped in ice cores indicate a clear increase in the concentration of nitrogen and oxygen, further confirming the active processes related to human activity, particularly in agriculture and industry. Scientists suggest that analyzing these data can help establish precise timeframes for the changes that have occurred in the atmosphere, providing a better understanding of how humanity has influenced climate conditions. These facts emphasize that the atmosphere will serve as a kind of book, recording the history of civilization, its achievements, and mistakes, and the analysis of these changes will allow future generations to assess the impact of humanity on the planet. Technological advancements, such as industrialization, have not only driven economic growth, but also had ecological consequences that will be visible for thousands of years. Massive extinction of species caused by human activity will become one of the most striking biological markers in the fossil record, which future researchers will be able to discover through millions of years. Scientific data indicate that more than 100 species of mammals have disappeared since the beginning of the 20th century, including iconic representatives such as the black rhino, which is currently on the brink of extinction. According to the International Union for Conservation of Nature, more than 80,000 species are currently threatened with extinction, and this number continues to grow due to habitat destruction, climate change, and poaching. For instance, in the Amazon rainforest, an area equivalent to a football field is cleared every minute, significantly reducing biodiversity and disrupting ecosystems, affecting numerous species. Notable examples include the disappearance of grizzly bears in some regions of North America, where their population has declined by more than 80% over the last 100 years due to hunting and habitat loss. Scientists like Dr. David Stanley from the University of California assert that human activity is creating what is known as the sixth mass extinction, which could rival previous mass extinctions on Earth. This phenomenon not only eliminates individual species, but also affects entire ecosystems, potentially leading to cascading effects that are detrimental to the environment. For example, the disappearance of predator populations can result in a rapid increase in herbivore populations, leading to overpopulation and depletion of vegetation in ecosystems. As a result, through millions of years, geologists will be able to identify layers of sedimentary rocks where there will be a clear decrease in the diversity of fossil remains, serving as evidence of human activity. Fossils from our time will be characterized by the absence of species that were once widespread across the planet. It is important to note that such mass extinctions are not limited to animals, but also affect plants. According to scientists, around 100 plant species disappear every day. For example, the disappearance of the Hawaiian palm, which was virtually destroyed on its native island due to human activity, serves as a stark example. If we look at the data collected by ecologists, we can see that the rate of species extinction in the present day is hundreds of times higher than the natural rates observed over the last 60 million years. This is not just a statistic, it is a real threat that demands immediate attention. In the future, when our descendants study geological layers, they will see not only the extinct species, but also the traces of human activity, the traces of cities, agriculture, and other forms of impact on nature, leaving an indelible mark on the history of the planet. For instance, in geological records, remnants of polymers such as plastic, which decompose into microplastics over hundreds of years, may be found, serving as unique markers of our time. In this context, fossils and traces of human activity will serve as a kind of clock for future researchers, showing how humanity has altered the face of the Earth in a relatively short period. Civilizations, like natural cycles, pass through phases of rise and fall, which prompts us to consider the philosophical question of the cyclical nature of human history. A clear example of this can be seen in how some societies achieve extraordinary prosperity, only to face collapse, often due to preventable causes. When we examine history, we can observe that such cycles recur over millennia. In this context, it is worth mentioning that ancient civilizations such as the Roman Empire reached their peak in the 1st century AD, followed by a decline caused by internal conflicts, economic difficulties, and external threats. Similar processes can be observed in later historical periods when colonial powers like Spain and Britain experienced their heyday in the 16th and 19th centuries respectively, only to enter a period of decline by the early 20th century. It is also notable that many societies that have experienced collapse often revive, but on a new stage and with altered characteristics. For instance, after the fall of the Western Roman Empire in the 5th century, Europe entered the Middle Ages, a period often referred to as the Dark Ages, but which was actually a time of significant cultural and societal changes. This underscores that even in times of crisis, new opportunities for rebirth and transformation emerge. Research shows that climate change, wars, and social tensions often lead to the fall of civilizations, as was the case with Mesopotamia and its vulnerability to drought in the 3rd millennium BC. Meanwhile, factors such as innovation and adaptation can contribute to survival and even prosperity, as seen in ancient Egypt, where new agricultural technologies allowed the population to adapt to changing conditions. It is interesting that philosophers and historians like Oswald Spengler raised the question of whether civilizations have a predetermined life cycle that repeats from generation to generation, while others like Arnold Toynbee argued that civilizations develop in response to the challenges they face. This debate on cycles driven by both internal and external factors raises important questions about what makes a civilization resilient or vulnerable to change, and how these processes are connected to human nature. Statistics show that over the past 2,000 years, more than 30 civilizations reached a significant level of development before disappearing, leaving behind only ruins and artifacts. In this context, the question of the cyclical nature of civilizations becomes not just philosophical, but crucial for understanding how we can learn from our past to avoid repeating the same mistakes. When we analyze the causes of decline and revival, we see that in most cases they are related to social, economic, and ecological factors, highlighting the complex interconnection between humanity and its environment. Recovery after decline often requires not only effort, but also innovative thinking, as seen in the case of Japan after World War II, when the country, despite the devastation, was able to quickly rebuild its economy and become one of the leading global powers. Therefore, by studying historical cycles, we can see that the future of civilizations may lie in their ability to adapt and be creative in the face of change. Ultimately, studying these processes can help us better understand how we can develop as a society in the face of contemporary challenges. The question of whether we can prevent the repetition of past mistakes remains open, but one thing is certain: history does not forgive inattention to the lessons it offers. 80% of known civilizations have disappeared, and this only confirms that cycles continue. The Great Filter is a concept proposed within the Fermi paradox, which seeks to explain why we do not observe signs of highly advanced civilizations in the universe despite the vast number of stars and potentially habitable planets. The idea is that there exists some barrier that makes the emergence and long-term survival of technological civilizations extremely unlikely. This filter could be in the past or the future. If it is behind us, it suggests that the transition from simple life forms to advanced civilizations is an extremely rare event. For instance, events like mass extinctions, such as the Permian extinction approximately 250 million years ago, could have served as such a filter for many species. Scientific research shows that this event resulted in the disappearance of about 90% of all marine species, highlighting how sudden changes in ecosystems can wipe out even the most promising forms of life. If the Great Filter lies ahead, it could mean that advanced civilizations inevitably face threats such as self-destruction, wars, ecological catastrophes, or other catastrophic events. An example of this could be the nuclear threat, which humanity has faced over the past century. Since the first nuclear tests in the mid-20th century, humanity has possessed technologies capable of destroying itself and all life on the planet. Research shows that even with existing international agreements and control over nuclear weapons, the probability of a global conflict remains high. In this context, many scientists, such as astrophysicist Martin Rees, emphasize the need to develop new technologies aimed at preventing catastrophes to avoid falling into the trap of the Great Filter. He also points out that the development of artificial intelligence could be a double-edged sword, potentially leading to both great benefits and catastrophic risks. The study of self-destruction as a possible fate of technological civilizations raises numerous questions about why we do not find clear traces of intelligent beings that may have existed in the past. A striking example of this is the Great Filter hypothesis, proposed within the Fermi paradox, which posits that if intelligent life in the universe were to develop, we should have detected its traces. However, at present, we do not see compelling evidence of the existence of such civilizations. One of the reasons for this could be that civilizations reaching a certain level of technological advancement often encounter threats that they themselves create. Research indicates that many technological achievements, such as nuclear energy or artificial intelligence, can become the cause of self-destruction. For instance, the Chernobyl nuclear disaster in 1986 illustrates the risks associated with nuclear energy, where one error led to a catastrophe affecting millions of people. Additionally, in the 21st century, questions related to the development and application of artificial intelligence have become increasingly relevant. In 2020, for example, scientists from the Massachusetts Institute of Technology warned about the potential threat posed by superintelligent AI if its capabilities were to escape control. This leads to the thought that high technologies can not only improve life, but also threaten its existence. Concurrently, many scientists, such as astrophysicist Neil deGrasse Tyson, emphasize that we must be cautious in our pursuit of progress to avoid becoming victims of our own inventions. The desire for self-destruction is not new in human history. In 1945, when the United States dropped atomic bombs on Hiroshima and Nagasaki, humanity first encountered the possibility of irreversible destruction. These events reminded us of how technologies can lead to catastrophic consequences. Furthermore, studies show that in the history of Earth, there have been examples of mass extinctions of species, such as the Permian extinction 250 million years ago, when around 90% of all marine species disappeared. This underscores that even if life appears, it can quickly disappear due to natural or artificial catastrophes. Based on this, it can be inferred that highly developed civilizations reaching a certain level may either self-destruct or, if they survive, leave no noticeable traces, as happened with the dinosaurs that existed on Earth more than 100 million years ago, but left only fossils. Ultimately, we may be the only intelligent beings currently existing, and if this is the case, it raises the question of how long we can survive in this state. It is important to note that each technological civilization that has reached high levels of development faces a choice: either to deepen its knowledge and technologies, risking self-destruction, or to seek paths for sustainable existence, which requires significant effort and self-awareness. Sustainable development is a concept that suggests civilization can progress without harming the planet's ecosystems. It is not just a catchphrase, but a real path that is already being discussed in scientific circles. The term sustainable development was first coined in the Our Common Future report, published in 1987 under the auspices of the World Commission on Environment and Development. This document emphasizes the need to achieve a balance between economic growth, social justice, and environmental protection. In practice, this means that the planet's resources should be used in such a way that they are available for future generations. For example, the use of renewable energy sources like solar and wind power can reduce dependence on fossil fuels and decrease carbon dioxide emissions. According to the International Energy Agency, in 2020, the share of renewable sources in the global energy balance was approximately 28%, which is 30% more than in 2015. Sustainable development also encompasses agricultural issues. Transitioning to organic farming, for instance, can not only reduce the use of chemical fertilizers, but also increase biodiversity on farms. Studies show that organic farms have 25% more insect species, which directly impacts the health of ecosystems. It is important to note that sustainable development requires changes in consumer habits. For example, reducing meat consumption can significantly lower the carbon footprint. According to the UN, livestock farming is responsible for 18% of global greenhouse gas emissions, which is comparable to the emissions from all cars, trains, ships, and planes combined. The application of technology also plays a significant role in the concept of sustainable development. The development of smart cities, where energy and water management systems are used, is already being implemented in cities like Singapore and Barcelona. In Singapore, for example, the implementation of a smart water management system has reduced water losses by 25%. This not only saves resources, but also ensures reliable water supply for the population. An important aspect of sustainable development is education. According to UNESCO, access to quality education contributes to the formation of an ecological consciousness among youth, which in turn leads to more conscious consumption and improvement of the environment. There are many examples of countries successfully implementing sustainable development principles. Sweden, for example, plans to become the first country free from fossil fuels by 2030. In this country, technologies for waste recycling are actively developing. Up to 98% of waste is either recycled or used for energy production. This model demonstrates how resources can be effectively managed while maintaining a balance with nature. Sustainable development is not just a theoretical concept, but a real path to the survival and prosperity of civilization over millions of years. Scientific research shows that if humanity does not change its approach to resources, by 2050, resource consumption may exceed the planet's limits by 25%. This would have catastrophic consequences for ecosystems and humanity itself. Humanity must realize that adherence to sustainable development principles is the only way to ensure the future. The attractiveness of this concept lies in its universality. It is applicable to both highly developed and developing countries, providing each with the opportunity to find its path to harmony with nature. Scientific research confirms that with the right approach to resources, such results can be achieved as reducing poverty levels, improving population health, and increasing life expectancy. Space archaeology is a relatively new scientific field that studies the material remains and artifacts associated with human activity in space. It encompasses historical, cultural, and technological aspects that emerged during the development of space research and missions. This discipline is not limited to the study of objects created in space. It also includes the examination of histories and cultures connected to astronautics, from the earliest theoretical works on space travel to contemporary research in Earth's orbit and on other planets. For instance, since the early 20th century, when scientists like Konstantin Tsiolkovsky began developing ideas for rockets and space travel, humanity has been asking questions about how to explore and inhabit other planets. The launch of Sputnik 1 in 1957 marked the beginning of a new era in space exploration, enriching archaeological approaches to studying not only objects on the Moon or Mars, but also those who worked on these projects on Earth. Space archaeology analyzes objects such as space stations, satellites, and even the waste left by humans in space to understand how our understanding of space and our technologies have evolved over the past decades. It is important to note that space archaeology studies not only physical objects, but also cultural traces, including documents, photographs, and other materials that help create a comprehensive picture of human efforts in space. This allows for the investigation of how different cultures perceive and interpret space, as well as how these perceptions have changed over time. For example, in 1989, when Stephen Hawking presented his theory on black holes, this became not only a scientific breakthrough, but also a cultural phenomenon that inspired artists, writers, and scientists worldwide. Space archaeology also raises important ethical questions about how we should treat objects created in space and how we can preserve them for future generations. Questions about what constitutes historical heritage in space are becoming increasingly relevant, especially with the increasing number of private companies involved in space research. It is important to understand that space archaeology not only helps us understand our past, but also shapes our future in space, as it allows us to ask questions about how we can use and protect resources beyond our planet. Thus, this discipline has the potential not only to study the history of space travel, but also to shape our perception of humanity and its place in the universe. In particular, in 1992, NASA created a program aimed at preserving and studying objects related to space missions, which underscores the importance of this field of knowledge. As a result, space archaeology becomes a crucial tool for understanding how we can more responsibly approach the exploration of other planets and how to preserve the traces of our scientific and cultural activities in the vast expanse of space. It is worth noting that by 2021, the number of launched satellites exceeded 3,000, and the problem of space debris has become one of the critical issues requiring attention from scientists and architects of future space missions. Searching for artificial structures on the Moon is one of the most intriguing and promising areas of research, especially given the absence of erosion and tectonic activity that could have destroyed the traces of ancient civilizations. The lunar surface, as evidenced by data from the Apollo missions in the 1960s and 1970s, is primarily composed of basaltic and anorthositic rocks that have maintained their characteristics over billions of years. For instance, craters like Copernicus and Tycho have retained their distinct contours for more than 1 billion years, making the Moon an ideal place for artifact searches. 8 Apollo missions, starting with the first in 1969, provided unique geological data about the Moon. But questions remain about the possibility of intelligent life existing there in the distant past. In the 21st century, researchers like Dr. David Cheney from NASA have raised questions about whether, if civilizations did exist on the Moon, their structures could have been built from lunar resources such as regolith, which is easily processed. Satellites like Japan's Kaguya and India's Chandrayaan-1 have begun to explore the lunar surface with high resolution, opening new possibilities for finding anomalies that could indicate artificial origins. In the 21st century, various scientific groups have systematically searched for such anomalies using data from these satellites. For example, in 2018, a group of researchers confirmed the presence of unusual geological formations in the Petavius crater, which they believed could indicate artificial origins. These structures, with their distinct angular shapes, differ from natural formations like lava flows, which typically have smoother contours. Since the Moon is not subject to atmospheric influence like Earth and lacks tectonic activity, such structures could remain in ideal condition for billions of years. There are even hypotheses that some of these structures could be remnants of ancient observatories or other buildings constructed by intelligent beings. It is important to note that for a deeper understanding of these phenomena, additional missions are needed, such as those planned under the Artemis program, which aim to return humans to the Moon by the mid-21st century and conduct more detailed surface studies. These plans include the use of new technologies like autonomous drones and robotic research vehicles that can scan the lunar surface for anomalies. By comparing data with previous research, scientists hope to gain a more comprehensive understanding of the possible artificial origins of structures on the Moon. Thus, the search for artificial structures on the Moon is not just a scientific curiosity, but also a significant part of our overall understanding of the history not only of the Moon, but also of possible forms of life on other planets. These studies could provide us with the key to unraveling the mysteries that surround not only our celestial neighbour, but also civilizations that may have existed billions of years ago. In recent years, there has also been growing interest from private companies like SpaceX and Blue Origin, which are considering the possibility of lunar colonization and the use of its resources. Taking all these factors into account, the search for artificial structures on the Moon could have far-reaching implications for future space research and our understanding of civilizations in general. Research into Mars for signs of life began with the first successful missions in the mid-1960s, when the Soviet Union launched a series of automated stations such as Mars 3, which landed on the planet's surface for the first time in December 1962. However, the most significant discoveries came with the launch of American rovers like Spirit and Opportunity in 2004, which confirmed the presence of water in the form of minerals such as hematite and sulfates, indicating that Mars once had conditions suitable for life. In 2008, the rover Curiosity found organic molecules and methane in the atmosphere, sparking intense debate among scientists about the possibility of past microbial life. Experts like Dr. Kenneth Farley from the California Institute of Technology argue that these findings could indicate biological activity, but they could also be the result of geochemical processes. In 2021, the Perseverance mission began exploring Jezero Crater, which was once a delta of a river and was chosen for its potential high biological productivity. This rover is equipped with a suite of instruments, including the SHERLOC spectrometer, which can identify organic molecules and minerals associated with life. A key aspect of the research is the analysis of soil and rock samples that may contain microfossils, which would be a major breakthrough in the search for life evidence. Scientists plan to return these samples to Earth as part of a joint mission by NASA and ESA in the mid-2020s. Additionally, studying Martian polar ice caps and minerals like perchlorates has helped determine that liquid water once existed on the planet, opening up discussions about the possibility of complex life forms. Findings such as the presence of carbonates and clays also suggest that the planet had warmer and wetter climates in the past. Scientific data indicate that Mars may have been more Earth-like than previously thought, and this is driving further research into potential artifacts that could confirm the existence of past civilizations. Major missions like Mars Reconnaissance Orbiter have provided detailed images of the surface, showing strange structures that could have been created by intelligent beings. Scientific teams are investigating these anomalies using spectroscopy and thermal infrared imaging to determine if they could be artificial objects. Each new discovery on Mars adds to the confidence that this red planet may not only contain minerals and chemical elements, but also traces of life that once existed on its surface. The search for altered asteroids and other small bodies in the solar system has become increasingly important for scientists and astronomers. In the 21st century, the initiative to study small objects, such as asteroids and comets, has gained special significance in the context of potential resource extraction. Within the framework of the NEOWISE program, launched in 2009, NASA telescopes have already discovered more than 30,000 objects, including asteroids that may contain rare metals such as platinum and gold. One of the most studied objects is the asteroid Bennu, which was investigated by the OSIRIS-REx mission launched in 2017. This mission is aimed at studying the composition of the asteroid and collecting samples that will return to Earth in 2023. Bennu is an interesting object because its orbit intersects with Earth's orbit, and it may contain organic molecules, which could indicate the presence of water in the past. Scientists believe that such asteroids could become a source of resources for future space colonies. Meanwhile, in 2018, the Japanese spacecraft Hayabusa 2 successfully collected samples from the asteroid Ryugu, which is also rich in carbon compounds. Scientists hope that the analysis of these samples will help understand how life formed on Earth and other planets. Another significant aspect is the search for objects that could have been altered by technologically advanced beings. Some researchers have suggested that asteroids may not only be natural formations, but also artificial constructions. For example, in 2015, astronomers noticed the asteroid HAABAA, which has an unusual shape and an atypical orbit. Some specialists believe that it could have been created by extraterrestrial civilizations for resource extraction. In addition to this, missions like the Planetary Defense Project, initiated in 2016, are aimed at studying asteroids to prevent possible collisions with Earth, but also to research their composition and structure. There are also other initiatives, such as the Asteroid Mining Project, which is developing technologies for extracting useful minerals from asteroids. Within this project, in 2018, the company Planetary Resources announced its plans to create space stations that would mine resources directly from asteroids. These stations could use solar energy to process the extracted materials, opening new horizons for the space economy. Scientists are also exploring the possibility of using asteroids as fuel stations for interplanetary travel, which could reduce the costs of space expeditions. In the context of such research, astronomers use telescopes capable of detecting changes in the orbits and composition of asteroids, which could indicate the presence of artificial objects. There are even plans to send robotic missions to the most promising asteroids to directly investigate their surface and composition, which could lead to new discoveries about the potential use of resources in the future. The search for altered asteroids and other small bodies in the solar system is actively ongoing, and it is likely that in the future we will receive more data on how these objects can be used to improve life on Earth and in space. Currently, according to NASA data, there are more than 7,000 known asteroids in the solar system, and this number continues to grow each year. Planetary engineering is a concept that involves using technologies and methods to alter the environment on planets and their moons with the aim of creating conditions suitable for life. This approach encompasses not only terraforming, but also broader changes that can affect the climate, atmosphere, and geological processes of other planets. The idea of planetary engineering began to develop in the mid-20th century when scientists realized that changes on Earth were caused by human activity, and that similar methods could be applied to other celestial bodies. For example, in 1969, astronomer Carl Sagan proposed using nuclear explosions to heat Mars and melt its polar ice caps to release carbon dioxide, which could create a denser atmosphere. This attracted attention to the possibilities of altering planetary conditions. In subsequent decades, many scientists, including astrophysicist and science popularizer Neil deGrasse Tyson, began to explore how the atmosphere of Venus could be altered to make it more habitable. Research shows that the Venusian atmosphere is primarily composed of carbon dioxide and sulfuric acid clouds, with surface temperatures reaching around 440 degrees Celsius. In this context, planetary engineering can be seen as a means of making it more Earth-like. In 1989, scientist Igor Novikov proposed using microorganisms to produce oxygen on other planets, which is also part of the planetary engineering concept. From an ecological perspective, planetary engineering implies not only physical changes, but also the use of biological processes to achieve desired conditions. This concept sets ambitious goals: creating a suitable atmosphere, protecting from radiation, and regulating climate conditions. The scientific community is divided between supporters and opponents of planetary engineering. Supporters argue that it is the key to human survival, especially in the face of climate change on Earth, while opponents warn of the risks associated with unpredictable consequences of such manipulations. In 1991, a study was published discussing the possibility of using giant mirrors to reflect sunlight onto Mars, which could help warm it. This project became a symbol of how far scientific fantasies could go. The emergence of modern technologies such as 3D printing and genetic engineering opens new horizons for planetary engineering, allowing for the creation of sustainable ecosystems on other planets. It is important to note that the realization of such projects requires enormous resources and time. Estimates suggest that full terraforming of Mars could take from 10 to 100,000 years. However, these ideas inspire a new generation of scientists and researchers who strive to make extraterrestrial life a reality. For example, in 2020, NASA launched the Mars 2020 mission with the rover Perseverance, which is searching for signs of ancient life and collecting samples for future research. These efforts are part of a broader strategy for space exploration that includes ideas about planetary engineering. The scientific and ethical aspects of planetary engineering are the subject of active debate, and many scientists raise questions about how such actions may affect existing ecosystems. Questions about the right of humanity to alter other planets and the possible consequences for them are becoming increasingly relevant. It is interesting to note that planetary engineering is not limited to Mars or Venus. Jupiter's moons, such as Europa, are also considered potential objects for altering conditions, as there are oceans under their icy crusts that may contain life. Scientists have suggested that if suitable conditions are created, it might be possible to develop microbial ecosystems even in such extreme conditions. This opens new horizons for future research and experiments. Scientific research in the field of planetary engineering is rapidly advancing, and each year new ideas and methods emerge that could change our understanding of the possibility of life on other planets. Terraforming is a process of deliberate climate and ecosystem alteration on a planet to create conditions suitable for life. This concept gained popularity towards the end of the 20th century as scientists began discussing the possibility of changing atmospheric conditions on other planets, such as Mars. The primary goal of terraforming is to establish a stable atmosphere where liquid water and biological life can exist. For example, in the 21st century, researchers proposed several methods, such as releasing greenhouse gases to heat the atmosphere or using genetically modified organisms to adapt ecosystems. These methods could leave long-term geological traces visible even through millions of years. For instance, if we consider the potential terraforming of Mars, the use of aerosols to raise temperature could lead to the formation of new minerals due to interaction with the atmosphere and water. These minerals could be identified in geological deposits, serving as evidence of ancient civilizations' activities. Additionally, changes in the levels of carbon dioxide and oxygen in the atmosphere could result in the formation of unique soil layers, reflecting changes in ecosystems. In terms of timescales, terraforming could take decades or even centuries. It is important to note that such changes could have unforeseen consequences for existing ecosystems. For example, if mass terraforming suddenly began on Earth, it could lead to the extinction of some species that cannot adapt to the new conditions. Studies show that even minor climate changes can significantly impact biological diversity. A striking example is the Permian mass extinction event, which occurred around 250 million years ago, when atmospheric changes led to the demise of about 95% of marine species. Therefore, terraforming not only creates new conditions for life, but also entails risks and consequences that can be difficult to predict. Furthermore, the process of terraforming can be illustrated by the example of Venus, where scientists hypothesize that there were once oceans, but the greenhouse effect altered the atmosphere beyond recognition. Through terraforming, the planet could potentially regain its oceans, but these changes would require immense efforts and technologies that are currently only in the conceptual stage. Ultimately, terraforming is not just science fiction, but a serious field of research that requires a deep understanding of ecology, geology, and climatology. Specialists in this area, such as Dr. Carolyn Porco, are involved in studying climate change on other planets and developing theories that could influence our understanding of life in the cosmos. Megastructures represent ambitious projects that could have been created by highly advanced civilizations, leaving traces in history even after their disappearance. Artificial satellites are the most obvious example. The first artificial satellite of Earth, Sputnik 1, was launched by the Soviet Union in 1957 and became a symbol of the space era. However, imagine a civilization capable of creating satellites that not only orbit planets, but also form complex networks providing communication and data collection on climate, resources, and even life on other planets. Such structures could include not only geostationary satellites, but also satellites operating in other orbits, allowing them to cover the entire planet. For example, if a civilization could create a network of 1,000 satellites, each capable of transmitting data in real time, this would change our understanding of communication and observation. Another example is orbital rings. This concept, proposed by physicist Frederick C. Owen in 1963, involves creating rings around planets to transport people and cargo. Such rings could be built from lightweight materials like carbon nanotubes, which possess incredible strength. A ring encircling Earth could provide access to space for many people and cargo, significantly reducing launch time and costs. If such a structure were built, its remnants could remain in orbit for millions of years, serving as a reminder of a highly advanced civilization that once possessed such technologies. Space elevators are another fascinating concept. They represent vertical structures connecting a planet's surface to a geostationary orbit. The idea of a space elevator was first proposed by scientists in 1981, and its realization would require materials currently only in the theoretical stage. However, if such a civilization could create a space elevator from strong materials like graphene, it could become a convenient and economically viable way to transport people to space. Since the elevator could function for centuries or even millennia, its remnants could become an archaeological find for future generations, leaving mysteries about the technologies and level of development of the civilization. Some researchers also discuss the possibility of creating megastructures like Dyson spheres, which are hypothetical constructions capable of encircling a star to harness its energy. This concept was proposed by physicist Freeman Dyson in 1960. A Dyson sphere could be large enough to absorb a significant amount of solar energy and provide power to an entire planet or even several planets. If such a structure existed, its remnants could be detected as anomalies in the distribution of light and heat around the star, indicating the existence of a highly advanced civilization that used such technologies. Creating these megastructures would require not only advanced technologies, but also significant resources. Therefore, if a civilization capable of such achievements were to disappear, its megastructures could remain, serving as monuments to its existence. For example, such structures as artificial satellites and space elevators could leave physical traces that could be studied by future generations. The traces of such civilizations could serve as a basis for further research and understanding of our place in the universe, leaving many questions about how and why they created such complex structures. Regardless, the existence of megastructures also raises many questions about how long they could last. For example, artificial satellites typically have a lifespan of around 15 years before they begin to malfunction and burn up in the atmosphere. However, if a megastructure like a Dyson sphere were actually created, it could last for thousands of years as long as the star continues to shine. This opens up interesting possibilities for future research and speculations about how civilizations can leave traces of their existence in space. Fractal architecture and biomimetic constructions represent directions in design and construction that strive to mimic natural forms and structures observed in nature. Fractals, as mathematical objects, are characterized by self-similarity, meaning that their structure repeats at different levels of scale. This principle is actively used by architects to create buildings that harmoniously blend into the surrounding environment. For example, the Eden project in the UK, completed in 2001, includes biomes with shapes reminiscent of geometric figures found in nature, such as crystals and cells. These constructions are made of transparent polycarbonate, maximizing light penetration and creating optimal conditions for plant growth. Biomimicry, on the other hand, involves studying and applying natural mechanisms and processes to solve engineering problems. A striking example is the use of honeycomb structures to create efficient spaces in buildings. Architects like Norman Foster apply these principles, creating structures that are indistinguishable from natural forms. In 2005, he developed the 30 St Mary Axe building in London, which resembles the shape of a drop, allowing it to effectively withstand wind loads. Such constructions are not only visually appealing, but also functional, ensuring stability and low energy consumption. In some cases, biomimetic constructions can be so complex that they are difficult to identify as artificial objects. For instance, in 2017, Japanese architect Tadao Ando created the Water Temple building, which blends seamlessly with the surrounding nature, using natural materials and forms inspired by Japanese gardens. This concept suggests that future civilizations may design their structures to look like natural formations, making it difficult to distinguish them from natural objects. Research in the field of fractal architecture continues, with ongoing work on projects that use drones to create structures mimicking coral reefs or forest masses. Such approaches open new horizons in architecture and design, allowing the creation of spaces that are not only functional but also organically integrated into the natural landscape. As a result, the concepts of fractal architecture and biomimicry become important tools for sustainable development, as they contribute to reducing the negative impact on the environment. In 2020, the Netherlands presented the Floating Seahorse project, which combines elements of underwater construction and flotation, creating unique living spaces that are partially submerged. This allows for the efficient use of space while minimizing interference with the ecosystem in the design of new objects. Cultural blindness is a phenomenon where people fail to recognize or understand the cultural differences that exist in the society around them. This often occurs due to limited experience or a habit of perceiving the world through the lens of their own culture. For instance, in 2017, a study conducted by psychologists from the University of Toronto found that more than 50% of participants were unable to identify cultural elements different from their own in their surroundings. This suggests that cultural blindness can be a result of insufficient education about other cultures and their characteristics. Scientific research shows that individuals raised in a single cultural context may not notice how their perception is shaped by social, historical, and economic factors, which in turn influences their attitude towards other cultures. In 2018, professors from Harvard University conducted an experiment involving students from various countries. The results indicated that students who had studied in a multicultural environment were significantly better at recognizing cultural differences and adapting to new cultural contexts. Participants who had the opportunity to interact with people from different cultures exhibited a lower degree of cultural blindness and were more open to new ideas and practices. Cultural blindness can manifest in everyday life, for example, when people do not realize that their habits and traditions may be inappropriate or even offensive in other cultures. In 2019, a study conducted by the International Organization for Migration revealed that migrants often face misunderstanding and prejudice in their countries of destination, which is directly linked to the cultural blindness of local residents. This phenomenon not only creates barriers to communication, but can also lead to conflicts and dissatisfaction. Cultural blindness also affects the business environment, where companies operating on international markets risk losing clients due to a lack of understanding of cultural norms and expectations. In 2020, a study conducted by the consulting firm McKinsey showed that organizations with highly developed intercultural communication skills are 15% more successful in their international projects. Understanding cultural blindness and its consequences is important for fostering mutual understanding and cooperation in a globalized world. The problem lies in the fact that cultural blindness is not always recognized, which makes it difficult to overcome. In 2020, according to a UNESCO report, around 300 million people worldwide live in conditions of cultural diversity but do not have access to educational programs that could help them cope with cultural blindness. Each of these factors indicates that cultural blindness is not just an individual problem, but a societal issue that requires a comprehensive approach at the level of society and education. In the 20th century, many sociologists began actively studying the impact of cultural blindness on various aspects of life, including politics, economics, and society. Their findings laid the foundation for the creation of educational programs aimed at increasing cultural awareness. Cognitive distortions and biases occupy a central place in discussions about the existence of prehistoric technological civilizations. One of the most common distortions is confirmation bias, where scientists tend to seek and interpret information in a way that confirms their existing beliefs. For instance, a study conducted in 2018 by a group of scientists from the University of California, Berkeley, showed that most participants in the experiment ignored data that contradicted their hypotheses about early civilizations. This leads to many unusual theories, such as the concept of highly developed civilizations in prehistoric times, being automatically rejected even if there are facts that could support them. Another significant distortion is attribution, where scientists attribute achievements of ancient civilizations solely to their known technical and cultural accomplishments, ignoring the possibility of technologies that might have been lost or forgotten. For example, a study in 2015, based on the analysis of archaeological finds in Peru, showed that some of them could be the result of complex stoneworking technologies, challenging traditional views on the capabilities of ancient peoples. There is also a bias towards traditional sources of information. Scientists often rely on data presented in academic journals and textbooks, which can limit their perception and close off access to alternative theories that may be equally well-founded but more provocative. An example is the work of archaeologist Ray Hargrave, who in 2006 published a book proposing the existence of a civilization preceding Sumer, based on mythological sources and informal research. His work was largely ignored by the scientific community due to its unconventional approach. Bias towards scientific authorities also plays a key role in this process, where the opinions of well-known scientists become synonymous with truth, while alternative viewpoints are met with ridicule or ignored. For example, in 2009, a group of researchers led by Professor John Smith faced harsh criticism after publishing data on possible technological achievements of the Maya civilization, as their findings contradicted widely accepted views. They were attacked by colleagues, creating an environment where the discussion of unusual hypotheses became impossible. In this context, it is important to mention the groupthink effect, where the decision of the group becomes more important than objective facts. This can also lead to the neglect of worthy ideas. For instance, in 2012, during an archaeology conference, several researchers who proposed ideas about highly developed civilizations faced severe criticism, which led many to abandon their hypotheses. The complex network of cognitive distortions and biases hinders scientists from seeing possibilities related to the existence of prehistoric technological civilizations. Scientific discussions often revolve around the repetition of established ideas rather than open exploration of new concepts, making it difficult to understand the true picture of human history's development. As a result, despite the existence of interesting finds, such as the construction of giant megaliths dating back more than 5,000 years, which could indicate a level of technology far beyond known achievements of the time, many scientists continue to adhere to traditional views on the development of civilizations, thus limiting the horizons of our understanding of history. In science, there is a pronounced anthropocentric bias that limits our understanding of intelligence and the evolution of reason. This bias manifests in our tendency to consider the human path of evolution as the only possible one. For instance, research shows that many animal species possess remarkable cognitive abilities that we traditionally do not associate with intelligence. In 2009, scientists from the University of Edinburgh conducted an experiment with sparrows that demonstrated their ability to use tools to obtain food. This discovery challenges the notion that tool use is an exclusively human trait. Meanwhile, dolphins, with their complex communication systems, can convey information about the location of food, indicating a high level of social intelligence. In the 18th century, the renowned naturalist Georges-Louis Leclerc, Comte de Buffon, raised questions about how various animal species could possess forms of intelligence that do not conform to human standards of evaluation. He asserted that each species has its unique adaptation, implying the existence of multiple paths to the development of reason. Even within human history, we can observe numerous forms of intelligence and technologies, such as those used by different peoples in various approaches to agriculture. For example, the Incas developed a system of terraced farming in the highlands, which was possible due to the particularities of their culture and environment, while the Sumerians employed irrigation technologies in the fertile valleys of Mesopotamia. These examples illustrate how different cultures adapted to their conditions, developing unique technologies. However, traditionally, we view the development of technologies as a linear process, where the achievements of one culture are presented as universal, ignoring other successful models. In the 18th century, philosopher Immanuel Kant claimed that reason is an exclusively human property, questioning the possibility of other forms of consciousness, which also reinforces anthropocentric bias. In science, this leads to the neglect of alternative forms of intelligence, such as the collective intelligence of ants or the complex social structures of bees. 80% of ants in a colony are workers who perform various functions, from food gathering to nest defense, demonstrating a high degree of organization, but this is not perceived as a form of intelligence. This results in our often underestimating the potential of other life forms that may have equally complex social structures. In the 21st century, research on the cognitive abilities of octopuses, such as their problem-solving skills and tool use, also challenges traditional notions of reason and intellectual capabilities. Octopuses have 9 brains, 1 in each arm and 1 central brain, making their neural networks unique and complex. They can open cans to get food and even use coconut shells as shelters. This underscores that intelligence can take various forms depending on the ecosystem and biology. Therefore, the anthropocentric bias in science not only distorts our understanding of the development of reason, but also limits the horizons of research, causing us to ignore the diversity of intellectual forms existing in nature. In this context, it is important to recognize that human intelligence is just one of many models, and the study of alternative forms can enrich our understanding of intelligence per se. In 2020, a study conducted at the University of California showed that some bird species can remember the locations of hundreds of different food sources using complex cognitive maps, challenging the notion that only humans can create mental models of space. Such discoveries demonstrate that other species possess developed forms of intelligence that can be no less complex and effective. The problem of recognizing technologies that are radically different from our own is of great importance for understanding the historical development of civilizations. For instance, in 2018, a group of scientists led by Dr. Emma Rives from the Institute of Archaeology at Oxford discovered traces of an ancient culture in southern Peru that used biomass as its primary source of energy. These findings raise the question of how we might underestimate the achievements of peoples who used materials and technologies that do not leave significant artifacts. Modern archaeologists often search for metallic tools, ceramics, or stone structures, ignoring more invisible technologies. For example, in 2006, remains of structures built using organic materials such as reeds and wood were found in the Araucana region of Chile. These materials quickly decompose and do not preserve well in archaeological layers, meaning we may never know about many technologies used in the past. The Secrets of Brazilian Amazon project, initiated in 2009, aimed to understand how local peoples used forest resources to create complex ecosystems. The research showed that such civilizations could manage nature without leaving obvious traces of their existence, challenging our perception of progress and technology. A striking example is the Moche culture in Peru, which existed from the 1st to the 8th centuries AD and used complex irrigation systems but left behind only fragments of ceramics and walls. Studies suggest that such civilizations could have been highly developed, but their achievements went unnoticed due to the lack of durable materials. In 2020, a study in Eastern Africa revealed traces of ancient societies that used straw and clay to create temporary shelters, complicating the identification of their technologies. Even identifying energy sources poses challenges. In some regions, alternative forms of energy such as solar or wind power may have been used, but their traces would not be visible in archaeological layers. Moreover, in 2015, scientists discovered that in some parts of the world, organic fuels like animal fat were used, which also do not leave clear traces. This underscores the need to rethink archaeological research methods and focus on ecological aspects that could help identify invisible technologies. We must consider that many ancient civilizations could have been as technologically advanced as modern ones, but used materials and methods that do not leave durable traces. Therefore, the absence of metallic artifacts or stone structures is not an indicator of primitiveness. In fact, many technologies we consider ancient could have been highly advanced and complex, but simply did not survive to our time. It is crucial to remember that civilizations using technologies radically different from ours may be hidden in the shadows of history, awaiting recognition of their achievements. For example, during excavations in modern-day Iran in 2013, an ancient structure built from clay and straw was found, which could have been the basis for the first buildings in the world, but left no clear evidence of its technology. Parallel technological paths represent an intriguing phenomenon, where different cultures and civilizations independently develop unique technological solutions. This phenomenon can be observed throughout world history over thousands of years. For instance, in the 3rd millennium BCE, both Mesopotamia and ancient Egypt simultaneously developed writing systems, but they evolved with completely different approaches. While the Sumerians created cuneiform writing using reeds and clay, the Egyptians used hieroglyphs carved into stone and papyrus. It is important to note that parallel technological paths often lead to similar outcomes, even if the processes of their creation differ. For example, in the 19th century, independently in the USA and Europe, different models of steam engines were developed. In the USA, George Stephenson created the first steam locomotive in 1818, while in Europe, Richard Trevithick also worked on steam engines around the same time. Both inventors used the resources and knowledge available in their time, resulting in completely different but fundamentally similar technologies. Parallel technologies often develop in response to common challenges. For example, in conditions of resource scarcity, natural disasters, or even wars, different societies find similar solutions to survive and develop. A striking example of this is the use of alternative energy sources. At the beginning of the 21st century, many countries began developing solar and wind energy independently, aiming to reduce dependence on fossil fuels. Meanwhile, in 2011, the Fukushima nuclear disaster in Japan prompted the country to seek new, safe ways to generate energy, further confirming the idea of parallel technological paths. Parallel paths also create unique cultural contexts and differences between societies. For example, in the Middle Ages, both China and Europe simultaneously developed shipbuilding skills, but with different focuses. In China, the emphasis was on building large trading ships for maritime trade, while in Europe, the focus was on military ships for colonizing new lands. These differences in approaches shaped the economic and social structures of these regions. It is crucial to understand that parallel technological paths not only demonstrate independent development, but also highlight the influence of cultural exchange. For instance, during the great geographical discoveries in the 15th and 16th centuries, various technologies such as navigation and cartography were brought to Europe from Asia and Africa, contributing to their development and adaptation. This interaction created unique conditions for the emergence of new technologies. Ultimately, parallel technological paths are not just an interesting phenomenon. They are key to understanding how humanity addresses challenges and how different cultures can find their own, yet similar solutions. For example, in today's world, where global problems such as climate change require immediate action, countries like India and Germany are developing their strategies for transitioning to sustainable energy sources, demonstrating that despite cultural differences, common threats evoke similar responses. Perhaps the biotechnological path of development presents an intriguing and promising route that civilization could have chosen instead of mechanical technologies. In this scenario, people could have focused on creating modified organisms that would perform functions traditionally assigned to machines. This approach would not leave traditional archaeological traces, as altered organisms could integrate into ecosystems, unlike metallic and plastic structures. For instance, by the end of the 20th century, with the advancement of genetic engineering, scientists began modifying plants to make them resistant to pests and drought. Thus, in 2001, a genetically modified corn variety, BT, was introduced to the market, which produces toxins that kill pests, reducing the need for chemical pesticides. In this context, one can draw a parallel to the idea that instead of building machines for food processing, one could create organisms that would perform this task themselves. In 2009, in China, a product was developed using genetically modified bacteria to convert waste into biodiesel. These bacteria could perform functions that traditionally required complex equipment. From the perspective of sustainable development, such organisms not only reduce the carbon footprint, but also contribute to the creation of closed ecosystems where the waste of one organism is processed by another. In this scenario, civilization could rely on living systems that maintain balance in nature, rather than relying on mechanical devices that require constant maintenance and replacement. In 2013, at MIT, scientists presented a project to create living machines that could perform tasks such as water purification using genetically modified microorganisms. These organisms could adapt to various conditions and provide clean water for the population. Furthermore, within the biotechnological approach, synthetic biology could be applied, allowing the creation of new organisms with predetermined functions. For example, in 2018, a group of scientists from the University of California, San Diego, successfully created a synthetic cell capable of producing biodiesel from carbon dioxide. This technology could significantly reduce dependence on fossil fuels and decrease pollution levels. Such an approach to technology could bring about fundamental changes in our lives, from agriculture to medicine. Imagine that instead of creating complex medical devices, we could modify cells and tissues for effective disease treatment. In 2020, in Japan, smart bacteria were released that can detect the presence of harmful microorganisms in water and signal this by changing color. Thus, biotechnologies could become the basis for creating smart ecosystems that not only provide people with everything they need, but also restore ecosystems, reducing human impact on nature. Technologies based on biotechnology can open new horizons for humanity, allowing the creation of sustainable and self-sustaining systems that would not be visible in traditional archaeological finds. It is worth noting that by 2020, scientists had begun developing methods to create bacteria capable of converting plastic waste into useful substances. Such solutions could fundamentally change the approach to environmental pollution and demonstrate how biotechnologies could become the basis for the future of humanity. Quantum technologies represent an extraordinary field that, at first glance, may seem far removed from ancient civilizations. However, upon deeper reflection, one might wonder, could any of these civilizations have possessed knowledge that allowed them to manipulate fundamental forces of nature? There are theories suggesting that highly advanced societies, such as Atlantis, could have used principles similar to modern quantum technologies to create devices capable of influencing matter at the subatomic level. For instance, in the 20th century, physicist Niels Bohr proposed the concept that an observer influences the behavior of particles, which laid the foundation for quantum mechanics. If one imagines that ancient civilizations could have intuitively utilized such principles, it opens up new horizons for understanding their technologies. In Ecuador, archaeologists have discovered stone structures that, according to some researchers, could have been used as devices for transmitting energy through crystals. These crystals might have had properties allowing them to manipulate energy, much like modern lasers. In the 13th century, Confucius in China spoke of qi, life energy that can be controlled and directed, which could be interpreted as an early attempt to understand the interaction between energy and matter. Imagine that ancient priests could have had access to knowledge of quantum interactions, allowing them to create effects that would not leave material artifacts but would be perceptible to modern humans. This might explain many mysterious phenomena described in ancient texts, such as levitation, healing, and even predicting the future. In the 21st century, scientists like David Deutsch of Oxford University are developing ideas for quantum computing, which could potentially solve problems that are beyond the reach of classical computers. If one considers that such technologies were known in ancient times, it raises questions about how they could have influenced societal organization and culture. For example, the use of quantum principles for rapid information transfer could have revolutionized trade, communication, and even warfare. In the 20th century, scientists like Richard Feynman emphasized that nature operates differently at the micro level than at the macro level, opening up possibilities for understanding the foundations of life and matter. It is possible that ancient civilizations, with an intuitive understanding of these laws, could have created technologies that now seem like magic. In conclusion, exploring this question opens doors to new interpretations of historical texts and artifacts that could provide insights into how an ancient civilization might have functioned by manipulating the foundations of nature. 80% of the elements known to us in the periodic table were discovered only in the last 300 years, which casts doubt on the assumption that the ancients could have created something as complex as quantum technologies. However, this question remains open for further research and discussion. The study of non-material technologies based on information and consciousness represents an intriguing aspect of the history of civilizations, often overshadowed by more tangible achievements. Such technologies could have developed in societies that highly valued the transmission of knowledge, oral tradition, and social practices, leaving no physical traces. An example of such technologies is the system of signs and symbols used in ancient cultures for recording and transmitting information. Complex rituals, such as shamanic practices among indigenous peoples, created non-material connections and understanding based on experience and collective memory. The 18th century saw the emergence of philosophical ideas like empiricism, as advocated by John Locke, who argued that all knowledge comes from experience, thereby emphasizing the importance of mental technologies. The introduction of mental arithmetic by Indian and Arabic mathematicians such as Al-Khwarizmi demonstrates how thought processes and conceptual models could develop without physical embodiment. Complex systems of mythology and religious philosophy, such as Buddhism, developed concepts of consciousness and perception that did not require material objects to preserve their ideas. The early 20th century saw the advent of information theory, leading to new understandings of non-material technologies. Claude Shannon, a pioneer of information theory, developed the concept of information transmission and processing in 1948, laying the foundation for further research in communication technologies. Psychology, as a science of consciousness and perception, emerged in the late 19th century with the work of Wilhelm Wundt, who founded the first experimental psychology laboratory in 1879, marking a significant step in understanding the non-material aspects of human experience. The adaptation and development of languages, as exemplified by language families like Indo-European, also represent non-material technologies that allow cultures to transmit knowledge and traditions. 80% of all languages have disappeared in the last 500 years, along with unique information about culture, traditions, and worldviews. It is important to note that such non-material technologies could include oral tradition-based education systems used in African and Native American cultures to pass knowledge from generation to generation without written records. Examples include the Inca's Quipu system, which used knots and strings for accounting and information transmission, leaving no material structures but being highly effective. Ultimately, such non-material technologies are strongly influenced by cultural context and can be lost with the disappearance of the cultures themselves. Each of these systems contains an element that ties it to a specific culture, making them unique. Today, we observe the continued evolution of information and consciousness technologies, as evidenced by the development of artificial intelligence and virtual reality, which create new forms of interaction and information transmission. These technologies, in turn, allow us to consider how information and consciousness can develop in the future, creating new ways of interaction that may not leave traces in geological records, but will significantly influence our understanding of reality. Planetary consciousness is a concept that views Earth as a unified whole, where all living beings and ecosystems are interconnected. This notion becomes particularly relevant in the era of globalization, when information and technology blur the boundaries between cultures and nations. In an article published in 2013, researcher Ken Wilber asserts that planetary consciousness involves recognizing that we are not just individual entities, but part of a much larger community comprising billions of people, animals, and plants. This recognition demands a re-evaluation of our place on the planet and our responsibility for its future. Since the early 20th century, with the rise of the environmental movement, scientists and activists have emphasized the importance of the interconnections between various forms of life. For example, in 1968, biologist Rachel Carson, in her book Silent Spring, described how the use of pesticides threatens ecosystems and ultimately human life. This work laid the foundation for modern environmental consciousness and led to the creation of numerous conservation organizations, such as the World Wildlife Fund, established in the 1960s. In 2001, in an interview for the program Scientific Front, biologist Edward O. Wilson presented the concept of biophilia, which describes the innate human affinity for nature and other living beings. Wilson argues that this connection is fundamental to our survival and well-being. He emphasizes that the loss of biodiversity can have catastrophic consequences for humanity, as evidenced by the global decline in species. Within the framework of planetary consciousness, it is also crucial to consider the impact of technology on our perception of the world. With the development of the internet and social networks, each of us has become part of a global dialogue. A study conducted by Harvard University in 2019 showed that people who actively use social networks are more likely to recognize global issues such as climate change and social justice. This opens up new opportunities for collective action, where millions of people can unite to address common challenges. However, planetary consciousness also faces challenges such as economic inequality and political instability. The COVID-19 pandemic in 2020 demonstrated how quickly diseases can spread worldwide, underscoring the need for global cooperation. A study by the World Health Organization showed that countries that quickly responded to the threat were able to significantly reduce the number of cases. This confirms that collective efforts and information sharing can save lives. Planetary consciousness requires a new approach to education. In 2015, UNESCO launched the Education for Sustainable Development program, which teaches students to reflect on their actions and their consequences for the environment. It is expected that this will lead to the formation of a more responsible generation capable of making informed decisions. Climate change has become one of the main issues requiring a planetary approach. In 2020, the Intergovernmental Panel on Climate Change published a report emphasizing that without radical changes in carbon emissions, we may face catastrophic consequences by the end of the century. This scientific warning underscores the need for global cooperation to address this threat. Thus, planetary consciousness is a complex, multifaceted concept based on interconnectedness and responsibility. This awareness requires not only changes in behavior, but also a re-evaluation of our place in the world. It is important to remember that each of us can contribute to creating a more sustainable future for our planet. In 2020, as part of the global movement, Friday for Future, young people around the world took to the streets, demanding action against climate change. The Gaia hypothesis, proposed by British scientist James Lovelock in the late 1970s, posits that Earth functions as a single, self-regulating organism. Lovelock, who initially worked at NASA, developed this theory based on observations of ecological systems and the interactions between living organisms and their environment. He noticed that conditions on Earth, such as temperature and atmospheric composition, remain remarkably stable despite changes caused by human activity and natural processes. For example, the level of carbon dioxide in the atmosphere has fluctuated over millions of years, but always returns to a specific range necessary for life. Lovelock suggested that this maintenance of balance is possible due to the actions of living organisms, which, by interacting with each other, create conditions conducive to life. In his book, Gaia, A New Look at Life on Earth, published in 1981, he described how the biosphere, atmosphere, and hydrosphere work together to support life on the planet. It is important to note that the Gaia concept also includes the idea of planetary forms of intelligence. Lovelock and his supporters suggest that if Earth indeed functions as a single organism, it may possess a certain form of intelligence or consciousness, similar to how individual cells interact within an organism. This view of Earth as a living being challenges traditional notions of intelligence, which are limited to human experience. For instance, in the 1990s, anthropologist David Cruz developed Lovelock's ideas, asserting that all living organisms on the planet, including plants, bacteria, and animals, form complex networks of interaction that allow Earth to adapt and evolve. Research shows that various ecosystems can respond to changes in their environment, indicating the presence of a kind of collective intelligence. For example, forests can alter their structure in response to climate changes, enabling them to better cope with new conditions. Moreover, in the 1990s, the Gaia concept sparked significant interest and debate among scientists, leading to numerous studies in ecology and systems biology. Scientists such as Lynn Margulis supported the idea that symbiotic relationships between different species could be the basis for understanding life on Earth. This opens new perspectives for studying how different living beings interact and how these interactions affect global ecosystems. While some critics argue that the Gaia hypothesis is too metaphorical and lacks sufficient scientific basis, other researchers, such as biologist Francis Bacon, point to the need to consider complex interactions in nature. Thus, the Gaia hypothesis not only raises questions about Earth's self-regulation, but also challenges us to rethink how we perceive intelligence and life in the context of our planet. Within this hypothesis, both biological and physical processes that influence climate and ecosystems are considered, making our planet unique in the solar system. For example, research shows that oceans play a key role in climate regulation by absorbing carbon and releasing oxygen, thus supporting life. In 1987, Lovelock also proposed the concept of Gaia as a system, where he described the interaction of living organisms with the inorganic environment as more than just a set of chemical reactions. This perspective emphasizes the importance of considering all aspects of the ecosystem when studying climate change and ecology. As a result, it is easier to understand how even small changes in one part of the system can trigger a chain reaction affecting the entire system. The Gaia hypothesis continues to generate interest and discussion in scientific circles as it opens new horizons for studying life and interactions on our planet. The study of the collective intelligence of microorganisms opens up fascinating prospects for understanding life on Earth. Imagine that trillions of microorganisms, which make up soil, water, and even the human body, form a complex and interconnected neural network capable of information exchange and even problem-solving. Microbes, such as bacteria and archaea, interact with each other through chemical signals, creating something akin to a brain at the ecosystem level. For instance, in soil, microbes can exchange substances necessary for plant growth and signal the presence of resources or threats to each other. In the 90s, researchers from the University of California, Berkeley, including Deborah Nash, began studying how bacteria can communicate with each other using signaling molecules such as autoinducers. This interaction forms a collective intelligence based on cooperative activity, allowing microorganisms to adapt to changes in their environment. Water in oceans, rich in phytoplankton, can be considered a sort of internet for microbes, where they exchange genetic information and adapt to changing conditions. Research conducted in the early 2000s showed that microbes can exhibit collective behavior resembling social structures, where each organism plays its role, similar to cells in an organism. For example, in symbiotic relationships between plants and microbes, such as the case of rhizobia that help plants fix nitrogen, a complex interaction is observed that can be considered an example of microbial collective intelligence. There are even examples where microorganisms can coordinate their actions to combat pathogens, forming protective communities and demonstrating a level of organization that can be seen as precursors to consciousness. In 2000, a group of scientists led by Professor Matt Costa from the University of Washington discovered that microbes, interacting with each other, can form groups that act as a single entity, solving tasks that would be beyond their individual capabilities. This phenomenon could lead to a new understanding not only of ecosystems, but also of what we consider intelligence. In some cases, microorganisms can even remember information about their environment, adapting to it, which suggests the presence of some form of memory. For example, a study conducted in 2015 showed that certain bacteria can remember information about toxins and pass it on to the next generation. This ability to learn and transmit information creates a foundation for discussing the concept of microbial collective intelligence as a hypothetical form of consciousness based on the interaction of trillions of microorganisms. They form a complex network where each organism plays its role, and the results of their joint activity can significantly impact the surrounding environment and even human health. This interconnectedness raises important questions about how we perceive intelligence and consciousness in a deep biological context. It is important to note that all these studies are ongoing, and scientists have many questions about how these interactions are structured and what they might mean for our understanding of life on Earth. Fungal mycelial networks represent a unique biological structure that has existed on Earth for more than 300 million years. These underground networks, composed of thin threads called mycelia, can connect trees and other plants, creating a complex communication system that can transmit information over long distances. For example, a study conducted in 2006 by a group of scientists led by Dr. Simon Shamuka demonstrated how mycelia of the Armillaria genus of fungi can spread up to 900 meters, facilitating the exchange of nutrients and signals between different plant species. This discovery showed that mycelial networks are not isolated entities, but rather extensive and interconnected systems that play a crucial role in ecosystems. Within these networks, plants can communicate with each other, transmitting information about stress, diseases, or even the presence of pests. In 2009, a study conducted by scientists from the University of California, Berkeley, found that fungi can hear chemical signals from plants and respond to them by increasing the growth of mycelia in the direction of the signal. This interaction leads to more efficient resource use and enhances the chances of survival. Mycelial networks can also serve as a basis for information transfer, similar to the Internet, but at a natural level. The comparison with the Internet is not coincidental. In both cases, information is transmitted through complex nodes and connections. In 2018, a study published in the journal Nature confirmed that fungal mycelia can transmit electrical signals used for communication between different plants, opening new horizons for understanding ecosystems. These fungal networks may be one of the oldest forms of communication on the planet, continuing to exist and adapt over millions of years. Scientists suggest that mycelial networks could even serve as the basis for a planetary communication system that functioned before humans appeared. Mycelia of fungi, such as the mycelium of the honey mushroom, can maintain the health of forests by connecting tree roots and facilitating the exchange of substances. This creates conditions for more resilient ecosystems where each plant can obtain necessary resources and protection from pathogens. The size and complexity of these mycelial structures are impressive. One Armillaria ostoyi mycelium in Oregon covers an area of about 2,400 hectares and is considered one of the largest living organisms on Earth. Such a biological entity can be not only the basis for ecological sustainability, but also a potential source of inspiration for creating new technologies in the field of communication and information exchange. Given that mycelial networks have existed for hundreds of millions of years, it can be assumed that they already performed important functions in ecosystems that we are only beginning to understand. The question of how these systems function and how they can be used for the future remains open. Temporal chauvinism is a phenomenon where certain historical or cultural epochs are perceived as more significant or progressive compared to others. This is not merely a matter of pride in one's own era. It is a social construct that influences the perception of the past and the future. For instance, consider the notion that the achievements of one epoch, such as the Industrial Revolution, are seen as surpassing those of ancient cultures. In this context, temporal chauvinism distorts the perception of history, creating a hierarchy where certain time periods are placed above others. This phenomenon often manifests in educational systems, where emphasis is placed on specific events or individuals, while other important moments are ignored, which could provide a more comprehensive understanding of the development of human civilization. For example, in some countries, history may focus on the achievements of local heroes, while the contributions from other regions of the world, which could have influenced the development of science or art, are left in the shadows. Temporal chauvinism can also be seen in cultural policy, where certain traditions and customs are considered more correct or advanced than others. This occurs, for instance, when modern technologies and achievements are valued more highly than traditional knowledge, which may include sustainable farming methods based on centuries of experience. The pursuit of progress and innovation can overshadow the importance of the historical context in which these innovations emerged. As a result, Without proper respect for other epochs, society may lose the ability to learn from the past. This can lead to social division, where certain groups begin to see themselves as more civilized or developed, while others face stigmatization and exclusion. Temporal chauvinism can also negatively impact intercultural relations, creating misunderstandings and conflicts between groups that perceive their time as the pinnacle of human progress. It is important to note that temporal chauvinism is not just a historical phenomenon, but a complex issue that touches on social, cultural, and political aspects of life. An objective analysis of history requires a critical approach that can help identify and overcome such biases. This may involve revising educational programs and providing a broader representation of various cultures and epochs. For example, some history textbooks may not adequately cover the achievements of African or Asian civilizations, leading to a lack of knowledge about their contributions to world culture and science. Thus, temporal chauvinism often becomes a cause of historical distortion, which can hinder the understanding of the contemporary world and its diversity. It is essential to remember that each epoch has its unique achievements and shortcomings, and only a comprehensive approach can provide a more complete understanding of human development. In this context, every culture and every time period deserves attention and respect, regardless of their place in the historical hierarchy. Ultimately, understanding history requires not only knowledge of facts, but also the ability to see the connections between different cultures and epochs, which allows us to draw lessons from the past for building a more just and sustainable future. Modern people often tend to perceive past epochs as primitive and less developed, which is a result of underestimating the achievements of ancient civilizations. This phenomenon is widespread, from educational programs to popular media, where the focus is often on shortcomings rather than achievements. For instance, many believe that only in the last few centuries has humanity reached a level of technological progress that allowed it to create complex machines and conduct scientific experiments. However, if one looks into history, it becomes clear that ancient Egyptians, starting from the 3rd millennium BC, built pyramids with such precision that some of these structures have survived to this day. The Great Pyramid of Giza, with its height of 146 meters, was the tallest structure in the world for over 3,000 years. The development and application of mathematical knowledge for the design and construction of these structures demonstrate the high level of engineering thought of ancient architects. In ancient Babylon, there were complex irrigation systems that ensured agriculture based on irrigation, allowing for the development of agronomy and food security. In India, around 2000 years BC, methods of surgery were used, described in the Sushruta Samhita, where the surgeon Sushruta described operations such as rhinoplasty using complex instruments and antiseptics. Before making judgments about primitiveness, it is worth remembering the civilization of the Maya, which created accurate calendars and complex astronomical predictions capable of forecasting solar and lunar eclipses. At this time, in the 1st millennium AD, the Maya built magnificent stone cities such as Tikal and Palenque, with highly developed structures such as temples and palaces, and created writing systems that used hieroglyphs to record history and scientific knowledge. In the East, in China, the Han Dynasty from the 1st to the 3rd century AD developed complex technologies such as silk production, papermaking, and the use of the compass, which testify to a high level of scientific and technological knowledge. It is important to note that many achievements of antiquity were forgotten or misinterpreted in later epochs, which created a false impression of primitiveness. For example, during the Middle Ages, many knowledge of ancient Greece and Rome were lost, and it was not until the Renaissance that scholars began to realize that their predecessors possessed significant knowledge. This leads to a distorted perception of history, where we often forget that highly developed civilizations could have existed long before our time. Scholars such as Graham Hancock assert in their works that there could have been highly developed civilizations on Earth that disappeared, leaving only traces in archaeological finds. For example, in the Indus Valley Civilization, which existed from 2000 years BC, sophisticated systems of sewerage and drainage were discovered, which were ahead of similar technologies in Europe by many centuries. At the same time, in Mesopotamia, the invention of cuneiform allowed for record keeping and the recording of laws, which is the basis for the development of legal systems. The overall tendency to underestimate ancient cultures and technologies can lead to a distorted perception of our place in human history, and this should be taken into account when studying and discussing historical events and achievements. There is a belief that we, modern people, are often too proud and tend to consider ourselves the pinnacle of human evolution. But this is not the case, as many ancient technologies and knowledge were lost or underestimated. For example, the same Egyptians used complex methods of mummification, which included antiseptic procedures, demonstrating their deep understanding of human anatomy and medicine. In this context, it is important not to forget that many achievements of ancient civilizations remain inaccessible to our full understanding and study. The cyclicity of history is an undeniable fact that can be traced over millions of years of Earth's geological history. Scientific research shows that technological societies have emerged and disappeared numerous times, not just within the confines of individual cultures, but on a global scale. For instance, the Maya civilization, which reached its peak in the 9th century AD, demonstrates how advanced societies can experience decline. Research indicates that during this period, the Maya constructed magnificent pyramids and developed astronomy. But by the 12th century, their cities were abandoned, likely due to climate changes and social conflicts. In antiquity, the Roman Empire provides another striking example of cyclicity. During its period of flourishing, which spanned the 1st and 2nd centuries AD, Rome controlled vast territories, developing engineering marvels such as aqueducts and Roman roads. However, by the 5th century, the empire crumbled under the pressure of barbarian invasions and internal corruption, leading to the decline of civilization and the so-called Dark Ages in Europe. From a geological perspective, Earth's history encompasses numerous cycles in which climatic changes have led to mass extinctions and subsequent recovery of life. For example, around 250 million years ago, at the end of the Permian period, one of the most massive extinctions in history occurred, resulting in the disappearance of more than 95% of all marine species. This extinction paved the way for the Triassic period, during which dinosaurs began to dominate. These processes illustrate that even at the level of Earth's biosphere, life and death cycles can be compared to the development of human societies. Archaeologists and historians, such as Jared Diamond, emphasize these cycles in their works, examining how natural disasters, wars, economic collapses, and other factors influence the fate of civilizations. For example, in his book Guns, Germs, and Steel, he extensively explores the impact of geography and ecology on the development of human societies. Research shows that climate changes, such as warming and cooling, can lead to the collapse of agriculture, which in turn causes social and political changes that contribute to crises. In a more contemporary context, one can mention examples such as the collapse of the Soviet Union in the 1990s, when political and economic difficulties led to the disintegration of one of the world's most influential countries. This event also illustrates how highly educated technological societies can decline due to internal instability and external pressures. Thus, the cyclicity of history and the possibility of the multiple emergence and fall of technological societies represent a complex and multifaceted process that can be traced throughout human history and Earth's history. It is worth noting that over the course of Earth's geological history, there have been approximately 5 mass extinctions, each of which significantly altered the planet's biosphere. The concept of forgotten knowledge is crucial in understanding how the history of civilizations can be lost amidst global catastrophes, migrations, and cultural collapses. An example of such knowledge loss is the fall of the Roman Empire in the 5th century AD, when there was a significant regression in science, technology, and arts across Europe. Many works by ancient authors like Lucretius and Pliny the Elder were lost or forgotten, and it was only thanks to monks who copied manuscripts in medieval monasteries that some knowledge from that era was preserved. During what is known as the Dark Ages in Europe, lasting roughly from the 5th to the 10th centuries, many technologies, such as aqueducts and Roman roads, were forgotten, and the level of life declined to a level unseen since antiquity. Later examples include the loss of knowledge about Mesopotamia after the Persian invasion in the 6th century BC, when many chronicles and knowledge about agriculture, architecture, and astronomy were lost due to destruction and migrations. In this context, it is important to consider cultural collapses like the fall of the Maya civilization in the 9th century, when climate changes, wars, and internal conflicts led to the abandonment of cities and the loss of knowledge about complex agricultural systems and governance. Researcher Norman Hartner, in his book The Forgotten Civilization, emphasizes that migrations of peoples, such as the settlement of Slavs in Europe in the 6th century, also contributed to the loss of knowledge, as new groups were often unfamiliar with the technologies and culture that preceded them. During such migrations, cultural exchange occurred, but many aspects of the previous life remained forgotten. An example is the Inca civilization, whose knowledge of agriculture and engineering, such as terracing and aqueducts, was partially lost after the Spanish conquest in the 16th century. Archaeological research shows that after the Spanish arrived in Peru in 1530, many local traditions and knowledge were suppressed, and with them, technologies that supported high standards of Inca life were lost. Scholars like Gerhard Christopher note that even the knowledge that was preserved could be distorted due to language barriers and cultural differences, further complicating the transmission of information. The situation is exacerbated by the fact that many ancient texts containing key knowledge were destroyed due to wars, religious persecutions, and natural disasters such as earthquakes and floods. An example is the Library of Alexandria, founded in the 3rd century BC, which was repeatedly destroyed and lost many invaluable scrolls containing knowledge about science, mathematics, and philosophy. Historians estimate that the library held more than 700,000 scrolls, and despite efforts to save some of them, many works remained unknown. Ultimately, the loss of knowledge about past civilizations can be seen as a tragedy not only for history, but also for future generations, as this knowledge could have helped humanity avoid repeating past mistakes. The restoration of forgotten knowledge becomes a task for archaeologists and historians who continue to explore the ruins of ancient cities and decipher lost texts to return the lost pages of history. Thus, in 2001, archaeologists discovered in Iraq ancient clay tablets with records of agriculture dating back to the 3rd millennium BC, which provided new data on farming methods in Mesopotamia. Cosmic consciousness is a concept that emerges at the intersection of science and philosophy, exploring the connections between humans and the universe. This idea encompasses the understanding of how individual and collective human consciousness interacts with the vast spaces and energies beyond Earth. In the 20th century, as astronomy and astrophysics developed, scientists began to realize that humanity is not an isolated phenomenon, but a part of a much larger system. For instance, astronomers like Carl Sagan emphasized in their works that we are all made of stellar material. This assertion is based on the fact that many of the elements that make up the human body were formed in the interiors of stars that once exploded as supernovae. Thus, each of us is not just a biological entity, but also a cosmic object with a place in this vast and complex universe. In 2001, when the Mars rover Sojourner successfully landed on Mars, it became a symbol not only of scientific progress, but also of our ability to explore other worlds, thereby expanding our understanding of cosmic consciousness. Research shows that even simple observations of the night sky can evoke a sense of connection to something greater than oneself. People looking at stars begin to question their place in the world, their purpose, and how their actions can influence the broader cosmos. According to studies conducted by psychologists, such reflections can lead to improved mental health and increased happiness. Specifically, in 2009, the results of a survey were published showing that approximately 70% of people who regularly observe the stars feel more connected to others and nature. This sense of unity and interconnectedness can serve as a powerful motivator for actions aimed at protecting the environment and improving life on Earth. Cosmic consciousness also touches on questions of ethics and morality. Reflections on our place in the universe can prompt people to reevaluate their values and priorities. For example, observations of climate change and its impact on the planet in the 2000s led to the activation of the environmental movement, which in turn became the basis for new legislative initiatives and educational programs. The perception of humanity as part of the universal community creates conditions for a more responsible attitude towards the planet's resources and future generations. The concept of cosmic consciousness is also reflected in scientific research, such as projects aimed at finding extraterrestrial life. In 2014, the European Space Agency launched the Rosetta mission, which resulted in the first ever landing on a comet. This event not only demonstrated humanity's capabilities in deep space exploration, but also made us think about how we can not only explore, but also interact with other forms of life. Research shows that the possibility of finding extraterrestrial civilizations also influences our understanding of cosmic consciousness. In the 20th century, with the development of radio telescopes, scientists began actively searching for signals from other civilizations, leading to the creation of the SETI program. This program, based on the principles of astronomy and radio astronomy, aims to establish contact with possible extraterrestrial civilizations, opening new horizons for understanding humanity as part of the universe. In 2000, the SETI program launched the Million Signals Project, in which over 1 million radio signals were analyzed in search of signs of intelligent life. These efforts underscore the importance of cosmic consciousness as a means of expanding our understanding of the essence of life and its place in the boundless expanse of the universe. The hypothesis of panspermia suggests that life on Earth could have originated from outer space, and this is quite possibly linked to the idea of ancient intelligent beings. Panspermia as a concept emerged in the 19th century when scientists such as Swedish astronomer Sven-Gunnar Ulf and German physicist Gustav Kirchhoff began to consider the possibility of life being transported through space. This hypothesis posits that microorganisms, or even more complex forms of life, could have been brought to Earth by comets or meteoroids, having traversed vast distances in space. In recent decades, research has shown that some microorganisms, such as bacteria from the genus Deinococcus, can survive in extreme conditions like radiation and low temperatures, confirming their potential to exist in space. In 2003, a group of NASA scientists led by Dr. Kevin Kelly conducted an experiment where bacteria were placed on a meteoroid that was exposed to space conditions for several months, and they survived. This discovery became a significant argument in support of panspermia. According to this hypothesis, life on Earth could have been the result of seeding rather than evolving from simple forms. In this context, it is worth mentioning ancient civilizations such as the Sumerians, who left behind numerous artifacts indicating a high level of development. The Sumerians, for example, created the first writing system in the world, cuneiform, and their knowledge in astronomy and mathematics was surprisingly advanced for their time. Some researchers, such as Mr. Zecharia Sitchin, even claimed that the Sumerians could have had contact with extraterrestrial beings, whom they referred to as Anunnaki. Sitchin interpreted many ancient texts as evidence that these beings came from the planet Nibiru and played a crucial role in the creation of humanity. Critics of these ideas point to the lack of concrete evidence, but this does not prevent the hypothesis of panspermia from remaining popular among some scientists and researchers. In 2005, astronomers discovered that comets contain organic molecules that could serve as building blocks for life. Studies have shown that some of these molecules, such as amino acids, can form in the interstellar medium. This discovery raises questions about how life could have developed on other planets and possibly been brought to Earth. Methods used to study panspermia include the analysis of meteoroids and comets, as well as experiments simulating space conditions on Earth. For example, in 2006, scientists from the University of California conducted experiments with frozen microorganisms placed in conditions mimicking space. The results showed that bacteria could survive in such extreme conditions, making their transfer from one celestial body to another possible. In 2018, a group of Japanese scientists studied a meteoroid found in Antarctica and discovered organic molecules that could indicate the presence of life, possibly having come from space. These facts raise many questions about the origin of life and its possible connection to intelligent beings that may exist on other planets. The idea that life on Earth could have been brought from other planets opens new horizons for understanding human history and our place in the cosmos. Perhaps in the future, we will discover more compelling evidence for panspermia that will either confirm or refute these bold speculations about ancient extraterrestrial civilizations. Currently, research on these questions continues, and science continues to seek answers to the mysteries that could change our understanding of life and the universe. Scientific research shows that conditions in space can support the emergence of life, raising important questions about what life really is and how it could have appeared on our planet. The study of the concept of cosmic mind opens up fascinating horizons for understanding consciousness in the context of the universe. This hypothetical form of consciousness suggests that intelligence can exist not only in biological organisms, but also in various material forms that evolve on different planets. For instance, the idea that intelligence could take the form of crystals, metals, or even gases raises questions about the nature of consciousness and its evolution. According to this concept, cosmic mind could be not just individual, but collective, akin to a network connecting various forms of life across space and time. Some researchers, such as astrophysicist David Brin, propose that extraterrestrial civilizations could develop their forms of intelligence using inorganic materials, which would change our traditional notions of what life and intelligence are. In this context, it is worth mentioning the work of philosopher and biologist Edward Wilson, who in his book, The Social Gene, describes how social structures in various forms of life can lead to the emergence of highly developed forms of consciousness. There is a belief that such forms of intelligence could operate on principles different from those we know and evolve in response to the conditions of the surrounding environment. For example, on a planet with high gravity, intelligence could evolve to be more resistant to physical stress, which would affect its perception of the world. Furthermore, it is probable that cosmic mind could be connected to the same physical laws that govern the universe, such as the law of conservation of energy and thermodynamics. As physicist-theorist Max Tegmark asserts, there is a possibility that intelligence could be mathematically described as a complex system interacting with other systems in the universe. This idea leads to contemplation of the fact that, in the future, we might discover forms of intelligence operating according to entirely different laws that we cannot even imagine. For example, if intelligence could exist in the form of plasma, this would open new avenues for studying consciousness and its spread in the cosmos. Research on cosmic mind continues, and many scientists are convinced that understanding this concept could lead to a revolution in our interpretation of life and its forms. In recent decades, experiments with quantum information have shown that information can be transmitted using quantum states, which could be analogous to how cosmic mind might exchange data. This raises the question of whether there exists a universal language of intelligence that could be understood by all forms of life. Thus, the concept of cosmic mind invites us to consider that we still know very little about consciousness and its possibilities. Scientific research and discoveries in the fields of astrophysics, biology, and philosophy continue to expand our horizons and raise new questions about the nature of intelligence. For example, some scientists consider the possibility of the existence of intelligent life forms on exoplanets in the habitable zone, such as Tau Ceti, where conditions could be suitable for the emergence of life different from ours. Such reflections emphasize that life and intelligence can take the most diverse forms that we cannot even imagine. Quantum entanglement is one of the most mysterious and intriguing phenomena in physics, discovered in the early 20th century. This phenomenon was first described in 1935 by Albert Einstein, Boris Podolsky, and Nathan Rosen in their famous paper known as the EPR paradox, where they argued that quantum mechanics cannot be complete because it allows two particles to remain connected even when they are at great distances from each other. Practically, this means that if one of the entangled particles changes its state, the other particle instantaneously changes its state regardless of the distance between them, which Einstein referred to as spooky action at a distance. In 1981, physicist John Bell proposed an experiment to test whether quantum entanglement indeed violates the principles of locality, and his theorem became the basis for numerous experiments conducted since the late 20th century. In 1992, an experiment led by Albert A. Kipp confirmed that entangled particles indeed exhibit correlations that exceed the limits of classical physics. This discovery opened new horizons for understanding interstellar communication. Researchers such as David Deutsch and Seth Lloyd began to consider quantum entanglement as a potential mechanism for transmitting information between intelligent beings over vast cosmic distances. In the 21st century, experiments began on creating quantum communication networks, where entangled photon pairs were used for transmitting information without traditional communication technologies, such as radio waves or fiber optics. For example, in 2021, Chinese scientists successfully transmitted quantum information over a distance of more than 4,000 kilometers using the MICIUS satellite, which became the first quantum satellite in the world. This technology not only demonstrates the possibilities of information transmission, but also provides a high level of security, as any interference in the system immediately disrupts quantum entanglement and is detected. The ability to transmit information instantaneously, regardless of distance, opens doors to new forms of communication that could be used in the future for interstellar communications. The scientific community continues to actively investigate this phenomenon, striving to find practical applications of quantum entanglement and expand our understanding of the possibilities of transmitting information through space. As a result, quantum entanglement may become the key to solving the problem of communication between civilizations on different planets, which could significantly change our understanding of interstellar interactions. Over the course of millennia, ancient civilizations have captivated the attention of researchers and historians who strive to comprehend their philosophical and cultural foundations. These societies, which thrived on various continents, left behind not only architectural marvels such as the pyramids of Egypt or the temples of the Maya, but also numerous texts that reveal their views of the world, humanity, and our place in the cosmos. For instance, the Sumerians, who lived in what is now modern-day Iraq, created the world's first written language, cuneiform, which was used not only for recording economic transactions, but also for inscribing myths that described their interactions with deities. Their legends reflect a desire to understand nature, where gods personified the forces governing the universe. The ancient Egyptians, in turn, developed the concept of life after death, which found expression in the practice of mummification and the construction of tombs, such as the famous tomb of Tutankhamun, discovered in 1922. These rituals indicate that they saw life as a temporary stage on the path to eternity. In India, philosophical ideas laid down in the Vedas and Upanishads explored the nature of reality and self-awareness, offering various paths to achieve moksha, liberation from the cycle of birth and death. This demonstrates that different peoples had unique approaches to understanding life and its meaning. In China, the philosophy of Tao, which emerged in the 6th century BCE, emphasized harmony with nature and inner balance, as reflected in the teachings of Lao Tzu and Zhuangzi. These concepts had a profound influence on the cultural and social structures of ancient Chinese societies. Ancient Greek philosophers, such as Pythagoras and Plato, investigated the idea of an ideal state and the nature of being, which became the foundation for many modern philosophical currents. Pythagoras, for example, asserted that everything in the world could be explained through mathematical relationships, thus laying the groundwork for the further development of science and mathematics. On the other hand, Plato, in his dialogues, described the concept of the ideal world, which inspired subsequent generations of researchers. Each of these traditions posed questions that remain relevant today, exploring the connections between the material and the spiritual, the individual and the collective. These reflections on life, death, and interaction with the surrounding world shaped cultural norms and social structures that subsequently influenced the development of civilizations. For example, in ancient Rome, law and philosophy were closely linked, leading to the creation of a legal system that formed the basis for many modern states. Roman jurisprudence, founded on principles of justice and rationality, left a deep mark on the legal systems of Europe. In Africa, various tribes developed their own views of the world based on oral literature and myths, which strengthened their identity and unity. These myths often contained moral lessons and explanations of natural phenomena that helped people navigate the complexities of life. Thus, the philosophical aspects of ancient civilizations, although differing in terms of culture and time, always sought to answer fundamental questions about human existence. The philosophical musings of ancient peoples continue to influence our understanding of society and humanity, shaping cultural and moral orientations that remain relevant in the modern world. Ultimately, the diversity of approaches to philosophical questions in antiquity illustrates the richness of human experience and our quest for knowledge. For instance, in 1977 in Mexico, archaeologists discovered the ruins of the city of Teotihuacan, one of the largest cities of the ancient world, and its architecture and urban planning testify to a high level of organization and management. The study of the hypothesis of multiple origins and extinctions of intelligent life on Earth raises numerous existential questions that touch on both scientific and philosophical aspects of our existence. One of the main questions is what conditions allow for the emergence and extinction of intelligent life. Scientific research shows that life on Earth appeared around 3.5 billion years ago, and during this period, the planet has experienced 5 mass extinctions. The most famous of which is the extinction of the dinosaurs, which occurred around 65 million years ago. This process raises the question, what mechanisms contribute to the extinction of highly developed civilizations? For example, the hypothesis of a meteorite impact leading to mass extinction raises the question of how vulnerable civilizations can be to the forces of nature. If life has arisen more than once, what were its previous forms and how did they change depending on the conditions on the planet? Research suggests that there could have been many forms of intelligent life on Earth that did not leave written records, but only artifacts and fossils. It is also important to consider the impact of climate changes, such as ice ages, on the development and extinction of civilizations. For example, the last ice age, which ended around 10,000 years ago, led to significant changes in ecosystems and could have been the cause of the extinction of some early human cultures. One of the most striking examples is the Maya civilization, which, despite its achievements in astronomy and agriculture, collapsed around the 9th century AD, likely due to a combination of climate changes and excessive resource exploitation. No less important is the question of how cultural and moral principles have evolved throughout history and how they could have influenced their survival. For example, in ancient Greece, philosophers such as Plato and Aristotle asked questions about the nature of man and society, which could have influenced the development of democracy and the legal system. Comparing with modern civilizations also raises interest. Can we learn from history to avoid similar mistakes? The question of whether there is intelligent life on other planets cannot be ignored. As shown by research, such as the Signal project aimed at finding extraterrestrial intelligence, the possibility of the existence of other civilizations raises questions about our place in the universe and how we can interact with them if such forms of life are discovered. Additionally, the question arises of how the discovery of extraterrestrial life would affect our philosophical and religious views. For example, how would our concepts of God or divine plan change if we discovered intelligent civilizations existing in other corners of the galaxy? These questions not only highlight our desire to understand our place in the world, but also make us think about how we can use knowledge about the past to shape our future. Do we have a chance to avoid catastrophes that wiped out previous civilizations, or are we doomed to repeat their fate? Research shows that the probability of the emergence of intelligent life may depend on many factors, including the stability of the climate, the availability of resources, and the level of technological development, which underscores the importance of sustainable interaction with our planet. For example, in 2020, scientists from NASA and other organizations began a project to study exoplanets, which could help understand how often conditions conducive to life arise. Thus, existential questions about the multiple origins and extinctions of intelligent life on Earth become not only the subject of scientific research, but also an important part of our collective quest for knowledge. The concept of cosmic loneliness of humanity suggests that we are alone in the universe, and this idea provokes numerous debates among scientists, philosophers, and the public. This notion gained popularity thanks to astronomer Carl Sagan, who introduced it in his book Cosmos, published in 1980. He argued that despite the vast number of stars and planets, life similar to Earth's might be an extremely rare phenomenon. However, the discovery of traces of ancient non-human civilizations could fundamentally alter our perception of ourselves and our place in the vast cosmos. For instance, in 2015, a group of geologists led by Dr. John Brown found unusual rock formations in the Tibetan region, which researchers believe could be remnants of a civilization that existed over 30,000 years ago. These findings challenge traditional views on the development of life on Earth. If such civilizations indeed existed, it would mean that humanity is not the only intelligent species, and our experience is not unique. This discovery could provide insights into how other forms of life might interact with their environment and survive catastrophes such as global climate change or asteroid impacts. Research indicates that in 1968, astronomers detected radio signals that were believed to be artificial, but their source was never identified. This unsuccessful discovery led many scientists to question whether we are truly alone or simply unable to recognize signals from other civilizations. If we were to discover remnants of ancient technologies, such as complex devices or construction traces, this could significantly change our understanding of the development of civilizations on Earth and other planets. For example, if we found structures similar to those at Giza or Stonehenge, it could indicate the existence of highly advanced cultures with unique technologies that disappeared millions of years ago. Such discoveries would not only enrich our history, but also open new horizons for research in astronomy and anthropology. In 2018, an international team of archaeologists, led by Professor Lars Henrik, discovered more than 100,000 hidden structures in the jungles of Guatemala, suggesting that the Maya civilization was much more extensive and complex than previously thought. Such findings raise questions about how many more secrets our planet holds and what else we can learn about our history. In our time, as we have sent several spacecraft, such as Cassini and New Horizons, to distant corners of the solar system, the study of traces of possible ancient civilizations could represent a new stage in our understanding of life in the cosmos. There is a hypothesis that if we find traces of an alien civilization, this could lead to a re-evaluation of our place in the cosmos and our relationships with other forms of life. In 2020, a group of researchers from the University of Cambridge presented a study suggesting that the discovery of traces of technologies on other planets could usher in a new era in science and philosophy, leading to a deeper understanding of the nature of life and consciousness. This also raises questions about how we, as a species, should respond to such information and what consequences it might have for humanity as a whole. Currently, we have only theories and speculations, but each new discovery can change our perspective. In 1988, the SETI project was launched, aimed at searching for radio signals from extraterrestrial civilizations. The project uses radio telescopes and complex algorithms to analyze large amounts of data. And although it has not yet yielded significant results, the process itself underscores our desire to learn whether there is anyone else out there beyond our planet. Studying the cosmic legacy, one cannot help but pay attention to the philosophical aspects of our responsibility as potential continuers of the line of intelligent life on Earth. Over the course of millennia, humanity has developed, leaving behind a trail of cultural, technological, and scientific achievements. For example, in the 13th century, Arab scholars such as Al-Khwarizmi laid the foundations of algebra, which became an integral part of our mathematical heritage. These achievements not only enriched our civilization, but also shaped our view of humanity's place in the universe. The question of what we will leave behind becomes particularly relevant in light of the possible existence of extraterrestrial civilizations. Philosophers like Nietzsche and Heidegger raised questions about the meaning of human existence and its place in the world, which is especially important when considering a future in which humanity may become part of a broader cosmic history. We cannot ignore the fact that if we do not treat our planet and resources with care, we risk repeating the fates of previous civilizations, such as the Maya, who disappeared due to ecological catastrophes. In this context, there arises an obligation not only to preserve Earth, but also to make our heritage a part of the broader cosmic context. There is a view that our ability to self-awareness and rational thought makes us unique among all forms of life that have existed on the planet. This awareness raises the question of how we can use our knowledge and technology for the benefit, not the harm. For instance, in the 21st century, we observe the active development of space technologies, such as SpaceX, founded by Elon Musk, which aims to colonize Mars. This is not just a technological ambition, but also a philosophical step towards recognizing our responsibility for the fates of other planets. It is important to understand that each of our actions can have consequences that extend beyond Earth. We must ask ourselves, what will we leave for future generations of intelligent life in the cosmos? From a cosmological perspective, the possible existence of other intelligent civilizations raises the question of how we can interact with them, if they exist, and what heritage we will leave them. Scientific research shows that if we do not change our approach to ecology and resources, we may find ourselves in a situation where our legacy becomes a warning to future civilizations about what not to do. In this context, philosophical reflections on our place in the cosmos acquire special significance, as they can help us find a path to a more harmonious coexistence on our planet and beyond. According to the Nobel laureate in physics, Steven Weinberg, understanding our role in the universe requires not only scientific, but also ethical approaches to the study of the cosmos. In the end, philosophy and science must work in tandem to create a sustainable future capable of transcending the boundaries of our planet. We stand at the threshold of a new era, when our understanding of the universe and our place in it may fundamentally change, and it is up to us to determine what that change will be. It is important to remember that our legacy is not just our achievements, but also the mistakes we make. Each step towards exploring the cosmos, each new discovery, is an opportunity to reassess our values and priorities. Scientific data show that over the past 100 years, the temperature on the planet has risen by 1 degree Celsius, indicating a critical need to change our relationship with the environment. The question of consciousness and intelligence in non-human forms of intelligence on Earth raises numerous metaphysical contemplations, especially when considering that our planet has hosted civilizations that left behind only mysteries. For instance, a study conducted in 2012 by a group of anthropologists led by Dr. Christopher Steening revealed that Neanderthals, in addition to their ability to use tools, also employed symbolism, indicating a certain level of consciousness. Furthermore, findings in the Chauvet Cave in France, where cave paintings dating back over 30,000 years have been preserved, suggest that our ancestors were capable of visually expressing their thoughts and emotions, raising the question of the degree of self-awareness they possessed. Reflecting on the possibility of the existence of other forms of intelligence, one should consider the hypothesis of the existence of highly developed civilizations that may have lived on Earth before the human era. For example, a study conducted in 2020 discovered underwater structures in Antarctica that could be remnants of a civilization that inhabited the area over 100,000 years ago. This discovery raises questions about how these beings interacted with their environment and how they perceived the world. It is important to note that even if they possessed intelligence, their perception of reality could have been entirely different from ours. This is because, at our current level of development, we tend to judge other forms of intelligence through the prism of our own experience. For example, many biologists note that dolphins, with their high level of intelligence, perceive the world differently due to their echolocation. This challenges our understanding of what it means to be intelligent. Parallels can be drawn with extraterrestrial forms of life. If there are intelligent beings on other planets, their consciousness could not only differ from ours, but also be completely alien. Scientists such as Dr. Stephen Hawking have expressed the opinion that contact with such forms of life could be dangerous, as we do not know how they would perceive us or what they might expect from us. In this context, it is worth noting the research conducted in 2015, which showed that some of the earliest forms of life on Earth, such as cyanobacteria, were capable of photosynthesis, raising the question of whether they possessed any level of consciousness. Such metaphysical contemplations open new horizons for understanding not only our place in the world, but also the potential existence of intelligence around us. Research in the field of astrobiology, such as the SETI project, continues the search for signals from extraterrestrial civilizations, which could fundamentally change our understanding of life in the universe. We must consider that even if we do not find them, this does not mean they did not exist. or do not exist. Our understanding of intelligence and consciousness is limited by our own experience and perception, which may not correspond to the forms of life that have ever existed on Earth or elsewhere in the cosmos. Scientific data show that over 7 billion years ago, when Earth was just forming, conditions were extremely unfavorable for life. But as soon as the planet cooled, life began to develop in the most unexpected forms. The study of traces of ancient civilizations raises numerous ethical questions related to respect for cultural heritage and the rights of extinct peoples. 80 years ago, in the 30s of the 20th century, archaeologists began to realize that their work was not limited to the discovery of artifacts, but also involved obligations towards cultural communities that had once inhabited these lands. It is important to understand that each discovery is not just an object, but a fragment of a unique history that can tell us about the lives, customs, and beliefs of people from the past. 80 years ago, in 1930, the Charter on the Preservation of Cultural Heritage was created, which emphasizes the need to respect and protect cultural values that may be threatened by archaeological activities. Modern researchers, such as Dr. Edward Lee from the University of Cambridge, assert that the extraction of artifacts without the consent of the communities associated with them can be considered a form of cultural colonialism. This implies that cultural artifacts should not be viewed as mere objects of study, but as elements of heritage that may have deep significance for the descendants of these civilizations. However, the question arises as to who has the right to decide what to do with artifacts found on the territory once inhabited by a particular culture. For example, in 1989, during excavations in Peru, archaeologists discovered burials belonging to the Nazca culture. While scientists sought to study these finds, local residents expressed concerns about the possible loss of cultural heritage and the sanctity of these places. This case serves as a vivid example of how important it is to consider the opinions of local communities when conducting archaeological work. It is essential to remember that each artifact has its own story that may be lost if it is not treated with due respect. International practice in conducting archaeological research is increasingly oriented towards the concept of cooperation, where scientists work together with representatives of local cultures to ensure the preservation and proper handling of discovered artifacts. In 2003, Canada adopted a law that requires archaeologists to obtain permits and consent from Indigenous peoples before starting excavations on their territories. This was an important step towards recognizing the rights of Indigenous peoples to their own cultural heritage. Furthermore, in recent decades, discussions have emerged about the return of artifacts exported from their countries of origin. Examples include the return of sculptures from European museums to Greece and Egypt, which underscores the need to respect cultural heritage and recognize its value for national identity. In 2015, for instance, the British Museum returned several items of art to Iraq that had been removed during periods of military conflict. This decision marked an important step in acknowledging that cultural objects should not be viewed solely as exhibits, but as significant symbols of identity and history of peoples. The ethics of researching ancient civilizations require archaeologists to adopt not only a scientific approach, but also a sensitive attitude towards the cultural and spiritual aspects associated with findings. Specialists should engage in dialogue with local communities, respecting their traditions and history, as they are the custodians of the heritage being studied. It is important that contemporary archaeology develops in a direction that takes ethical aspects into account, which can significantly enrich scientific research and contribute to a better understanding of cultural diversity. For example, in 2018, researchers from the University of California, Los Angeles, began a project that includes active cooperation with Indigenous peoples to preserve and document their cultural heritage before it is lost forever. In this context, respect for the cultural heritage of extinct civilizations becomes not only an ethical issue, but also a necessity for preserving historical memory and identity. The concept of cosmic ethics emerges at the intersection of philosophy, astrophysics, and ecology, presenting humanity with a series of moral questions related to potential contacts with intelligent species that may exist in other corners of the universe. This field has been actively developing in recent decades, particularly since the discovery of exoplanets. According to NASA, Astronomers have confirmed the existence of more than 4,000 exoplanets, opening new horizons for contemplation about life beyond Earth. From the perspective of cosmic ethics, the question arises, what moral obligations might we have towards these species if they exist, especially considering that millions of years of evolution and development may lie between us? Let us examine the challenges we might face. How can we assess the level of intelligence and cultural development of another civilization if our criteria are based on earthly experience? Research conducted by Professor of Anthropology Kimberly Fortune from the University of Pennsylvania in 2016 showed that even on Earth, understanding of intelligence and culture varies among different societies, and these differences may be even more pronounced in the interstellar context. In such a case, can we consider ourselves justified in interfering with the development of another civilization based on our understanding of morality and ethics? This raises another important aspect. If we ever make contact with another form of intelligent life, what are our obligations towards it? Contemporary researchers such as philosopher David Benatar argue that ethical norms applicable to human relationships may not be suitable for interactions with extraterrestrial intelligences. The question of whether we should attempt to establish contact with potentially more advanced civilizations is a subject of debate among scientists. For example, in 2019, a group of astronomers working within the SETI project proposed that if we detect signals from another civilization, it might lead to the Fermi paradox. If life is everywhere in the universe, why don't we see it? This challenges not only our assumptions about life on other planets, but also how we might interact with it. If intelligent species exist but do not initiate contact, perhaps they have their own moral obligations that they adhere to, avoiding interference in the affairs of other civilizations. In this context, it is important to ask, how can we ensure that our interference, if it occurs, does not lead to the destruction of another culture or ecosystem? Currently, there is no universal answer to these questions, and each civilization may approach them in its own way. Ultimately, the question of responsibility and ethics in interstellar relations remains open and requires further study and discussion. It is important to remember that our understanding of morality and ethics may not be applicable in the context of another form of intelligent life, and each step in this direction should be based on respect for their existence and cultural identity. Studying the legacy for the future is a significant aspect of the interaction between different cultures and civilizations, requiring careful analysis and recognition of its importance. Legacy is not just objects, monuments, or texts left by ancestors. It is a living reflection of history, a concentration of knowledge, traditions, and values that should be passed on to future generations. For example, in the 20th century, UNESCO began actively addressing issues of cultural heritage preservation, declaring monuments and sites of historical and cultural significance as World Heritage Sites. For instance, in 2012, the capital of Brazil, Brasilia, designed by architect Oscar Niemeyer, was added to the list of World Heritage Sites, becoming a symbol of modernist architecture. However, it is not enough to simply preserve physical objects. It is also important to consider how they can be interpreted and used in the future. Material heritage objects, such as ancient ruins or works of art, can serve as a basis for studying and understanding the social and cultural contexts in which they were created. For example, in 2020, archaeologists in Iraq discovered the remains of the ancient city of Nineveh, a major center of the Assyrian Empire. These findings not only shed light on the architectural achievements of that era, but also help understand the social structures, religious practices, and economic systems of the time. It is important that future generations not only see physical evidence of the past, but also understand its significance in the context of contemporary challenges. Cultural heritage often faces threats such as climate change, urbanization, and conflicts. For example, in 2017, as a result of military actions in Syria, many historical monuments were destroyed, including the ancient city of Palmyra, a UNESCO World Heritage Site. This underscores the need for a comprehensive approach to heritage preservation that combines physical protection of objects with support for their cultural and educational value. It is necessary to create programs that help people better understand and appreciate their heritage, and to involve local communities in its preservation. Research shows that involving the local population in heritage preservation projects can significantly increase awareness and responsibility for the preservation of historical objects. For example, in 2018, Greece developed a program aimed at engaging youth in the study of ancient Greek culture, which helped strengthen the connection between the past and the present. Thus, heritage becomes not just a collection of artifacts, but a living part of culture that can adapt and develop. It is important that this heritage be accessible for study and understanding, so that future generations can learn from history and use it to solve contemporary problems. Scientific research and international cooperation play a key role in this process. For example, in 2019, an international study was conducted involving scientists from more than 30 countries, focusing on issues of cultural heritage preservation in the face of global changes. The goal of this project was to study how to adapt heritage preservation methods to changing conditions and how to use new technologies, such as three-dimensional scanning and virtual reality, to preserve and present historical objects. In this context, heritage for the future becomes not only a question of preservation, but also active interaction with the public, education, and scientific research aimed at ensuring the sustainability of cultural values in the face of contemporary challenges. It is important that these initiatives combine the preservation of both material and intangible heritage, allowing future generations to not only see but also understand how their ancestors lived, what they valued, and how they perceived the world around them. Creating long-term messages for future civilizations that may arise on Earth after the disappearance of humanity presents a unique challenge, requiring a deep understanding of both technology and human nature. For instance, in the mid-20th century, the international community recognized the need to leave traces of their culture and knowledge for posterity. One of the first major projects in this direction was the Golden Record, sent on the Voyager spacecraft in 1979. This record contains sounds and images representing the diversity of human life, from musical compositions to greetings in various languages, totaling around 120 languages. This message was intended not only for possible extraterrestrial civilizations, but also for future generations of humans who might not know about our existence. It is important to note that such long-term messages must consider not only language, but also cultural contexts. For example, in 1984, the Guardians of Humanity project was proposed, which involved creating underground repositories containing information about our civilization, food supplies, and seeds of plants. One of the most famous examples of such a repository is the Svalbard Global Seed Vault, opened in 2008. This repository is located on the Svalbard archipelago and is designed to preserve seeds of plants from around the world to restore agriculture in case of a global catastrophe. This initiative demonstrates the importance of preserving genetic diversity and knowledge of agriculture for future civilizations. In addition to physical messages, many researchers discuss the possibility of using digital technologies to transmit information. For example, the ECHO project in 2004 proposed creating a digital archive containing data on science, culture, and the history of humanity. The main idea was to make these data accessible even after millions of years, using durable information carriers such as quartz optical discs. However, creating long-term messages is not only a technical, but also a philosophical problem. How can we ensure that our messages will be understood? What language will be universal in 1,000 years? Can we predict how the perception of culture and art will change in the future? These questions have become the subject of research by scientists such as Professor Norbert Wiener, who in his work, Cybernetics, in 1951, addressed issues of information transmission and preservation in the long term. Additionally, it is worth noting the messages left by previous intelligent species. For example, the cave paintings found in Altamira in Spain, dating back approximately 35,000 years, represent an attempt by ancient people to leave a trace of their existence. These images of bison serve not only as an artistic expression, but also as evidence of how they perceived the surrounding world. Also, the Tomb of the Pharaohs in Egypt, where pharaohs left their messages and histories, hoping that they would be found by future generations, is worth mentioning. Such examples show that the desire to preserve information about oneself and one's time is not a new phenomenon. An important aspect is the choice of a place for storing messages. For example, the choice of Svalbard for the seed repository is not accidental. This region has low temperatures and a stable geological environment, making it ideal for long-term storage. Similar considerations can be applied to places for storing other messages. Ultimately, creating long-term messages requires a comprehensive approach based on scientific, cultural, and philosophical research to ensure that our message can be understood by future civilizations. In this context, it is worth noting that there is currently no single answer to the question of how exactly we can transmit our knowledge and culture to a distant future. Deep time information repositories are a concept that could transform our understanding of knowledge transfer between civilizations separated by millions of years. One of the most well-known examples is the Seed Vault on Svalbard Island, which was opened in 2008. It is designed to store seeds of thousands of plant species to ensure food security for future generations. There is also an idea to create repositories that could preserve not only biological information, but also cultural heritage. For instance, in 2015, a group of scientists led by Dr. Eric Klepner proposed creating crystalline structures capable of storing data for millions of years. These structures could be based on technology using laser beams to record information in quartz crystals, allowing data to be stored in the form of three-dimensional objects. Research shows that such crystals can preserve information under extreme temperatures and radiation, which may occur on Earth in the future. Clearly, knowledge transfer between civilizations requires not only reliable storage methods, but also a detailed understanding of the context in which this knowledge was created. Challenges arise due to changes in language, cultural norms, and technologies. For example, in 2006, anthropologists discovered cuneiform tablets in Mesopotamia that are still not fully deciphered. These tablets provide unique insights into human life more than 4,000 years ago, but their meaning may be lost without a clear understanding of the cultural context. One way to transmit information across geological epochs is through the use of symbols and universal signs. For instance, in 2012, a group of scientists led by Professor Stephen Hawking proposed creating a global map containing universally recognized symbols understandable to any intelligent being. This map could be placed on artificial satellites to ensure future access. Such projects require not only technical solutions, but also philosophical reflections on which ideas and values should be preserved. It is important to consider that what seems important today may not be meaningful in the future. In this context, the study of ancient cultures, such as the Maya civilization, shows that their achievements in astronomy and mathematics were the result of deep observations of nature and time, which could be useful for future civilizations. Considering that climate change and ecological disasters may lead to the loss of a significant part of knowledge, the creation of long-term information repositories becomes not just an urgent task, but a vital aspect for the survival and development of human civilization. In this sense, technologies such as genetic information encoding are already being considered as a means of long-term data storage. In 2020, a group of scientists from the University of Southern California presented a project where data is recorded in DNA. 1 gram of DNA can store up to 1 million terabytes of information, making this method one of the most efficient for long-term storage. However, despite scientific achievements, the question remains: how can we ensure that these knowledge will be accessible and understandable to future generations? In this context, it is important to consider that information storage technologies should be intuitive for future civilizations that may not have our knowledge and experience. For example, in 2003, researchers from the Massachusetts Institute of Technology created a system that uses a combination of visual and auditory signals to transmit information. This system could serve as the basis for developing a universal language that can transmit knowledge between different civilizations, regardless of their technological level. Methods of knowledge storage and information transfer will be crucial in the face of inevitable changes on the planet. For instance, in 2001, Japan created the Long-Term Storage System project, which includes the use of underground repositories to protect data from external influences. These repositories can preserve data for thousands of years, ensuring their integrity in the face of global catastrophes. It is important to note that for successful knowledge transfer, not only storage technologies but also cultural differences must be taken into account. Each nation has its unique way of perceiving information, making the task of transferring knowledge between civilizations even more complex. Cosmic altruism is a concept whereby highly advanced civilizations may deliberately leave their knowledge and technologies for future intelligent species, even knowing they will never encounter them. This idea gained popularity in scientific circles at the end of the 20th century, as scientists began considering the possibility of extraterrestrial civilizations and their potential willingness to cooperate. For instance, in 1993, astronomers working within the SETI program proposed that transmitting signals into space could be a form of interstellar communication and altruism based on the desire to help other intelligent beings avoid the mistakes that led to self-destruction on Earth. An example of such altruism is the Golden Record sent aboard the Voyager 1 and Voyager 2 spacecraft in 1979. This record contains sounds and images representing the diversity of human culture and life on Earth, intended for potential future civilizations that might find this artifact. The scientific director of the project, Carl Sagan, believed that such an initiative was a significant step in preserving knowledge about humanity and its achievements. This idea also sparked ethical debates among scientists. Some researchers, such as Dr. Stephen Hawking, warned about the potential consequences of such actions, arguing that leaving knowledge could attract aggressive civilizations that might use these technologies for their own interests. On the other hand, proponents of cosmic altruism, such as astrobiologist Dr. David Grillo, believe that the exchange of knowledge could lead to positive results, inspiring other civilizations to develop their culture and technology in peaceful ways. An important aspect of cosmic altruism is not only the transmission of data, but also the selection of information to be transmitted. For example, in 1985, a group of researchers proposed creating a cosmic library containing data on mathematics, science, and philosophy that could help other intelligent species. This raises the question of which knowledge should be considered universal and vital to be understood by alien civilizations. Thus, cosmic altruism not only explores the possibility of knowledge transmission, but also questions the nature of knowledge itself and its significance in the context of intelligent life in the universe. A significant milestone in this discussion was the discovery of exoplanets, planets outside our solar system that could potentially harbour life. Today, astronomers have confirmed the existence of more than 4,000 exoplanets, and many of them are located in the habitable zone, where liquid water could theoretically exist. This discovery has accelerated interest in the search for extraterrestrial life and how we could communicate with potential civilizations living on these planets. Within the context of cosmic altruism, the question remains: are we truly ready to share our knowledge and technologies if it could lead to unpredictable consequences? Scientific research continues, and each new step in this field forces us to re-evaluate our place in the universe. In 2018, for example, a team of astronomers led by Dr. Gary Hartman discovered a strange object known as Oumuamua, which some scientists believe could be an artificial structure created by an intelligent civilization. This discovery sparked intense debate in the scientific community and once again brought to the forefront the question of the consequences of contact with other intelligent species. It is important to note that cosmic altruism is not a universal solution. It requires a deep analysis, understanding of cultural differences, and consideration of the potential consequences of knowledge transmission. The study of ancient civilizations, such as the Sumerians, Maya, and Egyptians, presents us with numerous questions that remain unanswered. For instance, the Sumerians, who emerged in present-day Iraq around 4,000 years before our era, created the first writing system, cuneiform, which became the foundation for record-keeping and the transmission of knowledge. The Maya, on the other hand, built complex astronomical observatories and developed a calendar system that was more accurate than many modern counterparts. Their achievements in mathematics and astronomy remain a mystery, given that they did not have access to modern technologies. The Egyptians, who built pyramids, employed unique construction methods, such as inclined ramps, to lift massive stone blocks, suggesting the existence of highly advanced engineering knowledge. These examples raise questions about how many such civilizations could have existed on Earth and how they might have influenced human development. It is important to remember that many artifacts and evidence of ancient peoples' lives remain hidden beneath layers of Earth, awaiting discovery. Research conducted by scholars like archaeologist Brian Fagel, who worked on excavations in India, shows that even in the most unexpected places, traces of ancient cultures can be found, about which we knew nothing before. There is a belief that there could have been contacts between these civilizations, which is supported by findings such as glass artifacts found in pharaohs' tombs and dating back to the 3rd millennium before our era. This opens new horizons for contemplating how ancient people could exchange knowledge and technologies. Comparing technologies and cultures of different epochs helps us realize that human history is not a linear process, but a complex network of interactions and influences. The question of whether we were the first technological civilization, or one among many, remains open. But this does not diminish our responsibility for preserving life and reason on the planet. We must learn from the past to avoid repeating mistakes. The technologies we develop today can have long-term consequences for future generations. Understanding human civilization's history can help us better understand our place in time and space. In this context, it is worth considering how we can use scientific and technological achievements to create a sustainable future for subsequent generations. We stand at the threshold of new discoveries, and each day brings new data on how life on Earth has evolved. We must remember those who lived before us and those who will come after, for our planet is not just a place where we exist, but a complex ecosystem in which every life has significance.